Good morning, everyone. I haven't actually done a welcome to country with this many people, so I may be a little bit nervous. I've been asked to present the welcome to country today, and I thought everybody has a history about who they are and where they come from. And I would like to share my history with you. My mother is fourth generation Australian. Her family are descendants from Scotland, Ireland, and Wales. My father's family are of Aboriginal descent from North Queensland. My grandfather is from Cooktown, and my grandmother is from the Darrell area. On both sides of my family, 3 generations have served in the Australian Defence Forces protecting our country. I identify as an Australian Aboriginal woman. I grew up in Brisbane and moved to Townsville in my teens. And I've been working for the Queensland Public Service now for 23 years. And for about 19 of those years, I've been with the Department of Resources. Though my Indigenous history is hard to trace back, it is not written, but spoken. I know that my people are Yindinji from the rainforests in North Queensland. We feel a strong connection with the land, and we honour that connection today through Welcome to Country. So today I would like to acknowledge the Wulgurugaba and Bindal people who are the traditional owners of this land. I would like to pay my respects to the elders past, present and emerging. And I extend that respect to other Indigenous people who are present. Thank you.
I think it's a testament to the value that we put in this. We do have today registrations control, which is so far, and we have so our job at GSQ is future security and performance of the resources sector. In particular, we want to lay the foundation for exploration success. Political reasons for that are, of course, jobs, economic state, etc. The GSQ, no, geologists, geophysicists. Some of us live in common. So we do understand prosperous and vibrant exploration industry. There are potential discoveries. There we know copper, vegetable resources, gold, silver, tin and tungsten, and all of the other things that keep them alive and feed all of the other industries downstream, some of which are becoming more and more important. But mineral exploration is hard. next generation big deposits are unlikely to come. They will be obscure, they'll be hard to find. It's our job at GSQ to ensure that the baseline data sets are there and they're available to industry. So we can make exploration like this, and of course, possible. Now, the GSQ, as you don't know, works through limited life funding packages. That means they go for a term of 700 years, 4 years. We're awarded that money from the Queensland Treasury. So we need to make a case for that funding. We need to prove that it's worthwhile investment for the state. We're always out for use case examples. So I'm just going to give a little shout out now. Using that data, please let us know. And your ASX announcements so that we use that as evidence to our masters in government. So I'm going to show here the funding programs over the last 4 years. I've arrived at this stage. There were more right. Yeah. So the strategic program, name, it ran for 4 years, 2017 to 2021, and it finished up last year. Focus is very much North Province and it responds to a need by government to bring economic diversity. A big part of that program is also our data systems were ancient and discoverable, it was not easily accessible by industry. And so we undertook the data modernization program, and that's still ongoing today. That group there, you can see more or less where it's today. The European Minerals Initiative was our next one, and that one's still ongoing. That's it does definitely cover electrify without it, and any other commodities that are essential to that industry. So both of these programs include a chunk of money for the Collaborative Restoration Initiatives, CEI, which many of you love, and are recipients of that program. Then in 2020, that's COVID stimulus measure covered $10 million at so in total, and up until last week, funding 2017 to 2004 exceeded $50 million. I think this is pretty good for an organisation that's actually said up until last week. So as many of you are aware, last week okay, last week, Queensland budget was delivered, and you know that there's been a lot of media attention on the increase in coal royalties. It was included in that budget, but I'm not talking about that today. The key message from the minerals sector seems to have been lost. Minerals. So the Queensland Minerals Industry Development Plan was announced by the budget and includes another $37.5 million to kids over the next 2 years. Health position resources, environmental investorships that we all know are going to occur and so need for us and therefore for those. There's a lot of policy government speak, of course, it's a government document, but here's the important stuff. Over the next 2 years, we will be able to spend $10 million on new geophysics. We'll spend $5 million over the next 2 years on mineral systems work and geoscience. We'll spend another $5 million on a new body of work on the circular economy in line. And I should have talked about this with Heather. So she's gonna make more of a detailed announcement about this later on today, but we will also put another CEI over the next 4 years. But I won't say anything more about that, so she can talk about it later today. And all of this is on top of the remaining $5 million that we have in the upcoming minerals initiative over the next 2 years. So we're going to be really busy with a lot of work, and hopefully it's kind of the work that's going to be useful to all of you. We held a advice basically from mineral explorers about what the future direction is using that money of GSQ. We talked about the funding because it hadn't been announced at that point, but we knew that was coming. And then I asked today to do similar feedback, so we'll run a little bit of a poll and questions later on, either today or tomorrow.
I'm so sorry.
Oh.
Microphone problems. Try this one.
Okay, does that? Evan doesn't know. Okay, let me know if that one. Online people, I don't know. They should have been here in person. They're happier? Okay, very good. So in the meantime, we are here to talk about all of the work that's currently underway by all of you. We want to hear from the mineral explorers today. We're going to hear from industry developers. We're going to hear from academic collaborators, and Geoscience Australia is here as well to give us a talk. I've lost where Geoff is. And of course, the GSQ geologists about what's new, what's been happening. We're going to have some talks, workshop style sessions, and of course, there'll be networking and discussion thrown in. You will need to download some links onto your laptops for the workshop components. This QR code will take you to our key GSQ datasets that we're going to be talking about over the next 2 days. But you should have also received an email overnight. Please check your emails and let us know if you didn't. There are some additional links included, which will be for the workshop component run by Steve Nicklethwaite tomorrow. If you didn't receive that email and those links, let us know. Most of us are wearing black Queensland government shirts, and Roger or Evan will come around and make sure that you can get the links and download the data. Programs are on your tables. There is Wi-Fi here. There's the name and the password. If you can't read that, it's also on the little whiteboard over there. So you will need your laptops at some point. First up, we're going to hear from GSQ, largely talking about regional geophysics, regional geology. Then we're going to take a deeper dive into some of the work going on in the northeast of Queensland. We'll break for lunch, and then we're going to have a big session hearing from our fabulous industry colleagues. Unfortunately, we have had a couple of COVID knockdowns. So unfortunately, Jeff Lowe and Simon Beams are not able to be here, but we did figure that there might be a few that would be affected by COVID because it's kind of just the way it is. So we do have a couple of backup talks that we'll slot into there. And then this evening, we will join forces at the quarterdeck at the Ville. And that's going to be hosted very, very kindly and generously by South 32. So everybody go and thank Danny over there. You're a legend, mate. That's good. All right. And I also, before we go any further, I want to say a huge thanks to Evan, who is new to GSQ in the last 6 months or so, but oh my God, it's made life so much easier. He basically organises all of us and gets these events up and going, including the webinars that we run regularly. And we couldn't do this without Rick. You can see his whole DJ setup here with microphones and everything. So the online people can now hear us. South 32, there you go, I did put a logo in there. And then tomorrow we'll continue again hearing from more mineral systems kind of stuff. We're going to have a bit of a session on mine waste and then a workshop in the afternoon on some of our 3D work through the Digital Earth program, which is with Steve and UQ, and then finish up with everybody's favourite Deposit Atlas work with Nathan and Paul. So thank you, everybody. And I am now, if I go back to the program so I can remember who's talking next. Roger, it's all over to you. I'm going to introduce Roger Cant, who is our senior geophysicist, and he's going to give an overview of the regional geophysics work that we've done over the last few years. So I'm going to let you stop sharing, and I'm going to hand the correct microphone to Roger. Oh my God.
Too easy.
So let's go through your slides, forward and back on that.
Great. Cool. And the point?
Lasers, that one, yeah, but then online people won't see that.
Yeah, that's true.
Yeah.
Thanks, Rick. Thanks, Helen. Welcome, everybody. My name is Roger Cant, and I'm going to be talking about the Queensland statewide geophysics. I'm part of the team that undertakes regional geophysical surveys in Queensland. We also have an oversight role in watching the geophysical data that's submitted to the department through the lodgement portal as part of your annual reporting requirements. Alrighty, so I'm going to give an update on the following geophysical data types, which have seen any sort of updates in the last 12 months here in Queensland, not necessarily by the GSQ either, as well as talk about some updates to our front-facing data systems, which are responsible for the delivery and discovery of our geophysical data in Queensland. Sure, by now you're all very familiar with this statewide airborne mag and rad grid merge that's available. Full Queensland coverage was completed, well, almost completed about 10 years ago. There's still that one little hole down there in the Tambo region. If everyone wants to put in a CEI application to fly some mag rad there, that'd be very much appreciated by the geophysical team. Surveying across the state has been completed at 400-metre line spacing. However, it's clear that there was a good case to be made to increase that survey resolution to 100-metre space lines in prospective areas and shallow cover, which leads us to our most recently acquired survey, the Kamilaroi survey. This is located to the north of Mount Isa. It was 61,000 line kilometres flown at a 60-metre terrain clearance, covering 5,000 square kilometres. It was flown in May through to July in 2021 and was published on the Open Data Portal back in September last year. There's the radiometrics to go with that. So the Kamilaroi survey, together with the Cloncurry South and Mary Kathleen surveys acquired in 2018, the Cloncurry North and the Central Isa, which were all flown as part of the Strategic Resources Exploration Program, the previous funding package, have now been merged together with the Kamilaroi survey, together with 20 open file and publicly available exploration surveys that have been flown fairly recently with a spacing of 100 metres or better to create the Mount Isa Regional Airborne Data Merge. This merge still incorporates the MIM Open Range survey as a base, and all surveys have been leveled to the AWAGS datum as well. There'll be a tech note coming out later this year describing the process and the survey, an index of the surveys that we used as well in the merge. You can see it when we produced the whole suite of MAG, 1VDs, radiometrics, as well as the individual channels there as well. So as it stands right now, with the completion of most of the eastern succession and that top bit in the Kalgoorlie-Leichhardt belt, there's no further plans to expand this 100-metre coverage. But if you're adamant that we're still yet to cover the best parts, then we'd be happy to hear your case, I guess. All right, on to Airborne EM. GSQ hasn't done anything recently with the Airborne EM. However, the team down at Geoscience Australia have made some fantastic progress on their Australia-wide Oz AM coverage with the 20-kilometre spaced lines. Data down to the bottom of the state in the southwest has now been acquired and was released earlier this year. And so there's now time for us to consider the opportunity to add further value to the program in filling areas where AM may prove useful, either in these new sections that'll be flown into the east or the north, or indeed filling in areas that have already been completed. Seismic. We now have some standardized images available for the 2019 Camel Wheel Seismic Survey, which are comparable now to those that were produced for the rest of the seismic sections in Queensland and indeed across the whole of Australia. This has led to further work on a new holistic interpretation of the skeletal network of seismic we have here in the Northwest. The program aims to improve understanding of crustal structure and evolution of Northern Queensland. Knowledge of these structures is a vitally important basis for understanding mineral potential across Northern Queensland. This work was led by Karen Connors from UQ, as well as assistance from staff from GSQ. The report, as well as digital geoscience analyst, digital project is available to download, and you can download that by following that link that you see in the QR code earlier. There should be a few around the tables there as well. MT. Last year, after previous campaigns of acquiring semi-regional grid-spaced MT, such as the Boulia and Cloncurry surveys, the GSQ collected its own in-house broadband and audio MT data along the CF2 and 3 deep seismic reflection lines, which are located in the southwest there, centering around Boulia. The project even made it into the local paper here in the Townsville Bulletin, though that might have had something to do with the crew's model-like qualities in some of the photo shoots. Work has been ongoing on processing and real geophysical modelling of the new CF2 and CF3 MT transects, as well as the Cloncurry MT surveys, which Dr. Janelle Simpson will be speaking on after this presentation. All right, on to gravity. Most of the state has been completed with a 4-kilometre regionally spaced surveying. The Mount Isa province, as you can hopefully, oh, it is a bit dark. The Mount Isa province has been covered by 2-kilometre spaced grid spacing regionally though. So what we're looking at here is the Australian National Gravity Database covering Queensland, which is a merge of federal, state and exploration open file data. There's over 300,000 individual gravity data points in Queensland. However, with the sunset clause that came into effect last year and the opening filing of a bunch of annual reports after 5 years of confidentiality now, there are now many gravity surveys which previously had locked away gravity data that can be added into this national gravity database. Now, the quality of some of these surveys varies quite widely, with data ranging from non-machine readable PDFs requiring OCR to original contractor supplied data. In the coming 6 months, we will be collating these surveys, making them individually available through the Open Data Portal and GeoResGlobe, as well as working with Geoscience Australia to add them into the Australian National Gravity Database. And this should add an estimated 75 to 100,000 gravity readings into the database. But we're now being asked for even higher resolution from you in industry. So the previous step change from 11-kilometre to 4-kilometre spaced gravity stations saw a great improvement in quality. So a similar resolution increase will likely be required to make an appreciable difference from what's currently available. However, ground gravity acquisition at 1-kilometre intervals is logistically challenging, as it's very difficult to choose between a vehicle acquisition versus a helicopter assisted program due to the awkward distance that need to be covered. It's almost too far for the vehicle to travel, but too short for the helicopter to go flying. There's also the consideration that we need to increase the resolution. When we increase the resolution from 4K to 1K, the amount of stations required increases by 4-fold too, due to the grid nature. This is on top of the complex stakeholder engagement required over such a geographically large area. The solution to this, of course, is to take acquisition to the sky. And what you're seeing there is some data from a CEI project from round 4 up at Capricorn Copper, the Crystal Creek AGG survey. This has led to the acquisition of GSQ's first airborne gravity gradiometry survey in partnership with Geoscience Australia. The Kenobi AGG survey is located to the north of Cloncurry. It was 4,712 line kilometres, which were acquired at 1-kilometre spacing, as a test of how effective the increase in resolution would be in an area of cover where there was sparse high resolution ground gravity, yet the regional data was still acquired at the higher 2-kilometre spacing in Mount Isa rather than 4K. To determine whether it'd be worthwhile to pursue a program of similar nature to the updated 100-metre mag-rad surveys in the Northwest. Not that we'd be flying 100-metre AGG yet, that'd be pretty cost intensive at the moment. Although there's a slight increase in the resolution, it's clear that the benefits would only be fairly incremental compared to the benefit that would be gained focusing on areas that there's a less existing detailed gravity coverage, and the terrain is, and where terrain is suitable, where we have adequately, where we have shallow covered areas, as the low wavelengths are adequately sampled by the regional data. Now, Geoscience Australia has made some great progress in incorporating airborne gravity, airborne derived gravity, into the latest national gravity grids, in which the ground gravity is upward continued to the airborne derived gravity. And so we expect the Kenobi survey to be merged into the next iteration, along with future AGG surveys that will be acquired by GSQ with money from this new funding package. All right, so that's all for the work in the acquisition space. Now, I'd just like to mention a few updates that have been made to the geophysics layer group in the GeoRes globe. Gone are the old airborne survey classifications of exploration, statewide, multi-client, etc. Surveys are now grouped by the observation type, so mag, rad, electromagnetic, magnetic, as you can see there. The system is also no longer just a static layer that needs survey extents and attributes from our new internal database, which also forms the back end to the GSQ Open Data Portal. The old apple green symbology has gone too, and we've also introduced a unique symbology for the MT, sorry, a consistent symbology, one symbology for MT and deep seismic transects. As we start to see more MT surveys becoming open file and plotting them, was no longer worth trying to fiddle with all the symbology to make them unique in the system. The data is also now presented in GDA 2020, which is also the datum you should be using when submitting geophysical data to the department. Finally, I think it's worth mentioning that thanks to our Geoscience Data Modernisation Program, which saw our internal and external facing systems overhauled, we're now capturing, cataloguing and providing ground-based geophysical surveys via the GSQ Open Data Portal. The quality of these data previously submitted for ground survey types, such as ground mag, ground EM, IP and resistivity, can be relatively poor, and there's still a lot of work yet to begin capturing these historical surveys and making them available, as we're going to be prioritizing the gravity data in the near future. As these collections become more mature, we will add functionality to the Open Data Portal to make these easy to find, as well as making them spatially visible with additional geophysical layers in the GeoRes globe. Thank you.
going to be.
All right. Any questions?
Does that include
Is the gap over the emerald area covered? I think that gap is.
sorry, you have line spacing there at 100-metre spacing, then
No,
not?
400
Okay,
metre.
right. Thank you.
There's a question online, which is when will the Kenobi results be available?
Sorry, the Kenobi results are already available. You can download them from the Open Data Portal right now. Just follow the link and a QR code on the program and you'll take you to a page where you can find that. It's been shared in the chat apparently. All right, if there are no further questions, I'll hand over now to Dr. Janelle Simpson.
You'll find better system for changing.
Let's just take 3 slides. Just forward it back.
Yeah.
So this one could work.
All right, thanks Roger for such a great introduction to what I will be talking about. So I'll be giving an update, a much more detailed dive into what we've been doing in the Magneto-Telluric space in Queensland. I thought it would be worthwhile going over the recent, I've taken a very broad definition of recent here. So the recent MT surveys that we've done in Queensland, I've got the first really big array MT survey in Queensland was done in about 2014, 2015. That's over 1,600 sites. It's still one of the larger ones that you can access in Australia. And then after we completed that, our focus really shifted up to Mount Isa into the Cloncurry region. And in 2016, we collected about 470 sites. And then we came back in 2020 and finished the rest of this 1,000 site array up in the Cloncurry area. You can see that it is a much higher resolution survey. So this guy's at 2 kilometre station spacing rather than the more broadly spaced one we did down south. And then as Roger mentioned, last year we went back and collected data along these 2 profiles down here in the south of Mount Isa. So they're 10K station spacing, so more broad again. But really looking to put some understanding about what's going on in the south of the Mount Isa inlier, where we're deeply covered along these 2 profiles, which are road traverses, also with deep coastal seismic data along them. So it's nice complementary data sets down here in the south of Mount Isa to try and give us some information what's going on. And then the forthcoming survey that we have is the CCA MT survey. That's all of these blue sites forming a backbone of data down the eastern succession of Mount Isa. And I will be going into a bit more detail about this survey at the end of the talk. And then complementary to this, we've got Geoscience Australia working on rolling out AusLAMP coverage across the state of Queensland. So this is long period Magneto-Telluric data looking down deeper into the crust at about 55 kilometre station spacing. If I start at the very biggest scale for understanding the context of all these high resolution surveys that we've got scattered across the Mount Isa province, this coloured swath of data here is an AusLAMP model produced by Geoscience Australia. It's a beautiful view down into the deep crust. And so this is the slice at about 33 kilometers depth. You can see there's really a fairly simple structure down at depth in Mount Isa. You've got this really strong conductor down the eastern side of Mount Isa, a big resistive block in the middle, and then a more moderate conductor in the western succession. This is unfortunately the extent of the current model, so we don't have this understanding in the south. There is data collected down here, but the models are still coming, so we don't actually have those available yet. This conductive structure on the eastern side of Mount Isa is called, it's got a name, the Carpentaria conductivity anomaly, if anyone's heard of that guy. And it's historically associated with the Gidja structure. Some people will call it the Gidja suture, depends on who you talk to. I'll be calling it the Gidja structure. It's this yellow feature down the eastern side of Mount Isa. So there's quite a lot of MT data, but it's really nice to have some sort of structural backbone to pin your interpretation to. So you've got some context for your anomalies in MT. So again, Roger mentioned this work. So this is a new crustal structure interpretation done with Karen Connors and Dominic Brown. So what we did is we used the deep crustal seismic, complemented it with some gravity modeling. We fed in some knowledge from the isotopic analysis across the area, and then leveraged the MT modeling in the area as well to try and put together a holistic view of what's going on at the crustal level across Mount Isa. And that report, all the details of that report are available in that link. But this was really the outcome. And I think I love this picture, it's so cool. So we're looking from this purple arrow in the south of Mount Isa up across this full set of deep crustal seismic lines. The seismic lines are in blue. So you can see you've got a nice interconnected set of seismic, a cohesive geological interpretation across all of those lines. And what it actually gives me for the MT space is a really well-defined location and expression of the Gidja structure, so that I can use that to try and understand what's going on with my MT models. So prior to finishing this work, there's actually some MT models that we can revisit with this new crustal structure interpretation. So there's obviously the Cloncurry model, which is quite well publicized now. There's probably a less well publicized model along the M6 seismic line here, right at the bottom end of outcropping Mount Isa. And so I'll revisit these in the context of the new interpretation. Not much has actually changed in the Cloncurry model. So I've zoomed up to Cloncurry. This is Cloncurry down here in the bottom corner. This is the IG1 seismic line. This is the big array of the full extent of the Cloncurry data, but the 2016 data was only really this triangular southeastern portion of the array. The modelling work sits in this location relative to the Gidja structure. So we're really in the crust above the Gidja structure. This is the MT modelling conducted along this seismic lines. This is only 2D modelling, but you can see there's a dipping conductive structure here associated with the Gidja structure. And then outboard to the east, you've got a conductive anomaly associated with the Soldiers Cap group. And then coming back off the Gidja structure, you've got these more isolated conductive anomalies. So this is the context for this model. So this is the model. There's a publication about this one if you wanted to have a bit more of a read about all the details. But what I've got here is a series of horizontal depth slices. You can see along the top, we're stepping down deep into the crust. And broadly, it's quite a simple story. We've got a big resistive block here in the west that merges into a mid-crustal conductor. Along the eastern margin of this survey, you've got a conductive feature that gradually dips out to the west. You can see it's coming further and further west as you go deeper into the earth. So you've got a big dipping, west dipping conductor. And then you've got these more isolated anomalies that come up into the shallow crust, merge with the mid-crustal conductor at depth. So that's not new information to anyone who's seen this before. That's pretty consistent. So if we step down now to the M6 model, which probably hasn't been considered in as much detail, the GIGIS structure here is highlighted in red. That's the map extent. These are the interpretations from the new work. And then if you overlay this existing MT model straight on top of the new crustal structures that we've interpreted, it actually changes the story a little bit for this MT model. So you've got underneath the GIGIS structure, you've got this big area of moderate to high mid-crustal conductivity, very similar to what we're seeing in Cloncurry. And then you've got these more isolated anomalies that come up off associated with strong areas of faulting that lead to mid to upper crustal conductive features. So that's what already existed. If I look at some new modelling work that I've been doing, so this has been my focus for the last little while, using the crustal seismic interpretation to provide the context, and then doing a 3D MT inversion of these two aqua boxes. So this one in the south, I'll talk about first and then revisit the Cloncurry story. So we're using ModEM 3D inversion code. This is actually hosted on the supercomputer down at ANU, and these two new surveys, well, this new survey and this extension of a previous survey both give us new information about what the crustal conductivity of this GIGIS structure might be. So if I pop down to CF3 first, so I'm well off the bottom end of the Mount Isa inlay here. It's quite deeply covered terrain. This again, we've got this slightly more deformed nature of the GIGIS structure here. We're about 100 k's south of the M6 model, so it is quite a fair way away. And remarkably, the structures here are very, very similar. So if I look underneath the GIGIS structure, I've got an area of mid-crustal to lower crustal elevated conductivity. I've got these east-dipping conductors that come up off that mid-crustal conductivity associated with faulting. So this one here is maybe associated with the overhang shear. This one's associated with this intense faulting through the central eyes of crustal block. And then out here to the east, very, very similar to what we're seeing in Cloncurry, there's an area of elevated conductivity associated with the Soldiers Cap group. So we are a very long way south. The crustal conductivity structures are very, very similar. So if then I step back into Cloncurry, same context again, I thought it would be worth revisiting because not everyone has spent like 2 years of their life staring at this. So this is the 1000 site array in around Cloncurry again, Cloncurry sitting down here. And again, we're just sitting up here in the space above the GIGIS suture in the prospective rocks around Ernest Henry. So Ernest Henry sits, ooh, can I do it? It sits in here, I think. It's probably wrong, but it's close. So this is an inversion that I have running at the moment. It's fitting reasonably well. So I've got an RMS of 2. Ideally, your RMS is 1, so not that far away, but there is a little bit of uncertainty still in this model. So what I've done is I've taken an 8-kilometre depth slice out of this model. You can see I've got a conductive feature down the eastern side of this array, similar to what we saw in 2016, but extending up to the north. There's actually quite a strong conductor here, particularly as you go deeper into the model, associated with the Quamby Fountain Range fault. And then you've got this very isolated conductive anomaly that sits in here. So if I put the approximate location of the GIGIS suture, GIGIS structure on here, you can see, and it's quite coarse, but there's a dipping conductive anomaly, a mid-crustal conductor that it merges down into, and then these pipe-like structures that come up off that mid-crustal conductor. And then there's an indication here. So this is off the edge of the data array, but up here, if you take a slice through this orientation, this crustal conductor here, and this one here actually merge down into a large mid-crustal conductor. So it's quite a similar story. Everywhere we go along the GIGIS structure, we get a similar answer, and it's a mid-crustal conductor with conductive fingers coming up off it. associated either with faults or, I don't know what this one's associated with. It's still running, so I'll work it out when it's done. But it's remarkable to me that you go from a high resolution survey in the north, you can image these things quite well. You go to 5K station spacing survey here along M6, they get a bit broader, but still associated with faults in this mid-crustal conductor. And then you go down to the south. And again, they're a bit more diffuse, but you do have lower data resolution. So there's an expectation that if you infill this one down here, you might get something more similar to what's going on in Cloncurry, despite the huge spatial distance that you've traveled. So that's really the motivation for the forthcoming survey. So what we're trying to do, as I said, it's 320 new sites. This time they're in red. So what we're trying to do is provide a backbone of data down the eastern succession of Mount Isa where it's most explorable, to really track where the conductive anomalies go from between the Cloncurry survey down south to CF3, where we managed to image it on the new profile of data. There's some sites down here in the south to try and give us an understanding of where that conductor might go off the southern end of the Mount Isa province, to see if it has any continuity down here or if it's indeed solely associated with the Mount Isa province. And then some higher resolution infill along the 94 deep crustal seismic line as part of this survey as well. So it's going to be collected over the next 12 months. I should say it is being jointly funded by ourselves and Geoscience Australia. So it's really great to have them help it out to cover the cost of this survey. So hopefully this time next year I'll have data to release, but hopefully and that's where the structure is in this array. So you can see we're really just trying to put some data around that structure and understand what it looks like down here. I will leave it there.
Any questions for Janelle?
Thanks, Janelle. That's great. It's really nice to see all that MT happening and the results. Now, so the Carpentaria conductivity structure, I'm sure this has been discussed before, but I must have missed it. What is sort of the latest thinking on that? It looks like from your sections that the Soldiers Cap group is a regional conductor. Also, where the Gidia structure or suture is interpreted is a large conductivity structure. Over the length of that Capricorn conductivity anomaly.
Yeah,
What's the latest thoughts on what actually the geology is there?
Yeah, so I think previously the Carpentaria conductivity anomaly has really been defined by quite wide space data, and I suspect that the previous understanding of it is kind of an amalgamation of several different anomalies. So you do have the Soldiers Cap anomaly, and then you've got the one directly associated with the Gidia structure. So as we get more and more fine resolution data, it's actually resolving into a number of different features. I don't understand what the Soldiers Cap conductor is. I wish I did. I've thought about it. I don't have an answer. I think that the primary part of the CCA is going to be that strong conductor directly associated with the Gidia structure. To my mind, that's what it is. What it actually is in terms of what rocks are down there causing it is a really tough one, and I hate giving this answer, and I don't know what it is. There's a number of things it could be. It could be that there's elevated salt content or graphite content or sulfide content associated with that structure. Maybe there's some sort of graphitic schist that's been entrained down into the structure as well during its formation, but yeah, I don't have a satisfactory answer, unfortunately.
Any more questions? Are there any questions online? No, okay, you've bamboozled them all, Janelle. All right, now I'm just going to stand here. I'm going to introduce Geoff Fraser, who's joining us from Geoscience Australia. and it's going to give us the latest from down south. So get his mic sorted out and take it away.
That's on. That's it. We set to go?
Yes.
Yep. Good. All right. Well, thanks, Helen, and particular thanks to Evan and GSQ for giving me the chance to come up and be part of the workshop. It's kind of nice to get out of the depths of Canberra winter for a couple of days and come to the tropics. So the aim of this presentation is to give a fairly brief, I guess, overview of quite a range of different data sets that and activities that Geoscience Australia has been doing across Australia in general, particularly in Northern Australia, and with this audience, I guess I tried to focus in a bit more on Queensland in particular. And in putting this talk together, I got to a point starting to think that this is starting to look like a bit of a hodgepodge of a bit of this sort of data here and that sort of data there, and things at different scales and quite different styles, different sorts of data. So it sort of had a risk of becoming a bit of a itty-bitty talk. But I just wanted to step back from that before I go into those data sets and reiterate that there is some sort of method to what might seem apparent madness. And that sort of overarching vision is that we're engaged in trying to piece together a whole range of different styles of geological, geophysical, geochemical data across the whole continent in ways that those data sets can be merged and inform each other about what the geological meaning of them is, but also collect sufficient data sets that can be used in a mineral systems context collectively to start making predictions about where undiscovered resources may be. And the image on the bottom right is an example of a predictive iron oxide copper gold prospectivity map. So there's work going on in the data space to collect the relevant data sets that become input into these predictive models. What I'm going to talk about today is on the data side, some of the data sets that we've been collecting. If you're interested in more of these predictive maps and models and that sort of work, my colleague Ariane Ford is in the audience somewhere. There she is up the back there. And she's now leading that type of work at GA. So if you're interested in that type of work, please try and catch up with Ariane over the next couple of days. As Helen pointed out in her introduction too, obviously at Geoscience Australia, we're not mineral explorers. We're in the kind of what's so-called pre-competitive geoscience space. But clearly we want the data, the things that we do to be useful to the minerals industry. And so occasions like this are a really good opportunity to get some feedback. So I've put a few sort of prompting questions up here to the audience, I guess, that would be really great to get some feedback during this workshop about how useful the sorts of work we're doing actually is to you, what is most useful, what is least useful, what else, other sorts of data you might like to see. Also things like how do you access the data, how easy is that for you, and how would you best like these data sets delivered. So please try and keep those things in mind as we go through, and I'd be very happy to talk one-on-one or in discussion sessions over the rest of the workshop. So a quick reminder that the vast majority of what I'm talking about today has been funded or is being funded through the Exploring for the Future program. Many of you will have heard about it, I'm sure. A federally funded program that was initially funded over 4 years from 2016 to 2020 with a strong focus in Northern Australia, as shown by the map on the left with all the activities in the north. That was then extended for another 4 years, and we're in the midst of that now between 2020 and 2024. And the idea with the extension was to try and roll that approach out nationally. So a bit more attention has started being focused in Southern Australia. but still with work going on in the north, as you'll see in the rest of the talk. And none of this work is possible for Geoscience Australia without close collaboration with our partners, particularly the state and territory geological surveys. So again, big acknowledgements to GSQ for their part in that, and also Northern Territory Geological Survey for our work in the north, and also our partners at MinEx CRC for some of the stratigraphic drilling work that I'll show. Okay, so I'm going to start with a couple of examples of compilation style work going on at the national scale. And the first one of those is working towards a seamless multi-layered solid geology map of the whole continent. This work started in the north, and the first collection of solid geology maps across Northern Australia were completed in the first phase of Exploring for the Future and have been delivered. And we're now working towards to rolling that out across the rest of the country. And you can see a kind of snapshot of progress in this map on the left here. And then, I guess, somewhat in parallel with that, there's been a compilation of metamorphic grade and style across the whole country as well, put together by Ben Goscombe. And that compilation is in QA/QC sort of phase at the moment. And it's been, I think, something like 30 years since there's been an updated metamorphic map of the country. So we look forward to that coming out. So these data sets, particularly the multi-layered solid geology maps, obviously take us from 2D to starting to get into the 3D space. The fourth dimension, which is close to my heart, I guess, as a geochronologist, is obviously time. And so we've also been putting a lot of effort into compiling all the publicly available geochronology across the country. The national coverage can be seen in this little image in the top left, coming out of the GA portal. There was a strong focus initially in Northern Australia, but we're now pushing that out across the rest of the country. There's an updated compilation from Tasmania about to come out, and additional work going on in New South Wales and South Australia. But given this audience, I've shown a snapshot of some of that coverage across, I guess, the north. So this is all available through the GA portal. Something else that we've added recent functionality is the ability to, I guess, select an area of interest like this shaded box and produce a kind of quick summary plot of what geochronology is available in there and the sort of the age distribution. And you can then hover over any of these points with your mouse in the portal and see a bit more detail about that data. So, what method it was, what rock it was on, the data source, etc. So that's all available for use via the GA portal. And so those were two examples of compilation work going on at the national scale, but obviously, including Northern Australia and Queensland. In parallel with that, we're also pushing along with national scale geophysical acquisition. And one of those flagship, I guess, programs is the Oz AEM program with the aim of covering most of the country with 20-kilometre line-spaced AEM. It's the world's largest survey of its type. This little snapshot shows the coverage as it was about a year ago. So obviously very much across Northern Australia. This is the coverage now, a year later. You can see almost complete coverage of Western Australia now, as well as this strip down the kind of border region between Queensland, New South Wales, South Australia, Victoria. And as we speak, there are planes flying to complete Southern Northern Territory and this remaining strip of Western Australia. So we're well on the way now to a national coverage of AEM. And similarly, as Janelle's been talking about, there's a national effort towards a conductivity, electrical conductivity view of the continent via the AusLAMP Magneto-Telluric program. Again, the aim is to cover the whole continent with about 55-kilometre spaced grid. Progress can be seen in this top left image, with the green areas having already been acquired. Clearly more to do in Western Australia and Queensland, but we're starting to address that. The main image here is I think, a beautiful model coming out of this AusLAMP work from basically Northern Australia, straddling the border of Queensland and Northern Territory. This came out late last calendar year, led by Jingming Duan and others. So that forms some of the backbone to the more high resolution stuff that Janelle's just spoken about. And there's work in place to extend this. There's been acquisition now in the southeastern part of this model, shown by the red dots on the map in the middle. They've been acquired and also push things out to the east, shown by these yellow circles, where instruments have been deployed just recently. And just last week, people were out there picking those instruments up. So we would expect this model to be extended sort of to the southeast and further east, hopefully a new model in early next calendar year. And that will be very interesting to see how some of these major conductivity features extend southwards and eastwards, as Janelle's emphasised. Also a nice segue from Janelle's talk and from Paul's question about what is the meaning of Magneto-Tellurics, and I think it's probably fair to say that it's fantastic to see all the new data. We've probably not yet fully explored what all that data means geologically, but there are a couple of papers recent papers I'll draw your attention to that I guess try and improve that understanding. The one on the left I'm talking about here is one by Wenping Zhang in the East Tennant region, where she and colleagues have used a kind of multi-scale MT approach, so AusLAMP broadband MT as well as, long period MT as well as closer space broadband MT in a sort of scale reduction way to I guess, zero in on fertile regions in the East Tennant region. And then the example on the right is a recent paper by Alison Kirkby and Coralie Siegel and others. It doesn't have data from Queensland specifically, but what they're doing here is exploring how different mineral systems express themselves in electrical conductivity data, with examples from North America, Southeast Australia, the Andes, etc. And not surprisingly, they find that different mineral systems have quite different electrical conductivity expressions, and that's obviously key to how to use MT data effectively in an exploration context. So that's one to look out for if you're interested in that type of work. Okay, so I've spoken about some national scale compilations and data acquisition activities, and now I want to zoom in a little bit to things that are going on more at the Queensland scale, I guess. And one of those things is a reanalysis of a whole bunch of stream sediment samples across Cape York and Georgetown region primarily. So stream sediments reanalysed for 64 elements here, something like 5,500 samples through this central belt, as well as nearly 1,000 over in this little patch in the west. And so that data is currently in final stages of preparation for release in August 2022. So in a month's time or so, there's already some interesting patterns showing up, particularly relevant to, I guess, anomalies in critical minerals. So that's one to look out for that's coming very soon. There's also been some compilation work through Alison Britt's team in our resources and advice team that has just looked to pull together historical mineral occurrences across this whole Barclay, Isa, Georgetown region and put them together in a consistent way. It pulls together things like discovery dates, the mineral system style, exploration methods, and also tries to compile, I guess, the reported presence of critical minerals in any of these discoveries. So hopefully that's a useful place to find, I guess, the collective historical archive of discoveries across the region in a consistent single place. But the other thing this map does is draw attention to how biased the coverage is to areas where there's outcropping rocks and how few discoveries there have been in the surrounding covered regions. So a big focus in the Exploring for the Future program has been to push data acquisition in those covered regions to see if we can improve the success rate of discovery undercover. One of those regions was the East Tennant region that I mentioned previously with the MT study. I don't want to spend a lot of time on this today because it's not in Queensland, and it's also been talked about in various places before. There was a program of 10 stratigraphic holes here east of Tennant Creek. Most recently, we talked about that at the AGES conference in Alice Springs a couple of months ago. The main point here is to say that the analytical program on rocks from those 10 holes is essentially complete, and most of the reports are now available via this website, with a couple more to come very shortly. So if you're interested in that data, that website is the place to go. And the other, another example of this undercover work that's been conducted is in this South Nicholson Basin region, shown in the blue outline here. It straddles the Queensland Northern Territory border. Again, similar to some of the maps that Janelle just showed, you can see this network of reflection seismic lines across the region, many of which have been collected during the EFTF program. Some in collaboration with GSQ out in the Queensland side, obviously. And one of the aims of some of these lines was to test the geological meaning of some of the distinct gravity lows that you see in this gravity image on the right. In particular, I'm pointing at these distinct gravity lows out here near the Queensland border. And seismic across that region has, I guess, revealed a previously essentially unknown package of stratigraphy in a depot centre that's now being called the Carrara Subbasin. So that was identified in seismic, but that stratigraphy was completely untested. There were no drill holes into it, so it was very difficult to confidently correlate that with anything else in Northern Australia. And to address that, a deep drill hole was put into the western flank of that Carrara Subbasin. So that's the NDI Carrara 1 hole that was completed with MinEx CRC. Drilling finished in late 2020. The hole went to 1,750 metres depth, went through about 600 metres of Cambrian Georgina Basin, and then another over 1,000 metres of essentially unknown Proterozoic stratigraphy beneath that region. So, as I said, the hole was finished late 2020. Through last year, there were sampling programs on that hole, and a whole range of different analytical work done on those rocks. And again, there's a website up here where you can go and find a lot of those reports. There are a couple of AGES abstracts on this work. There are reports on organic and inorganic geochemistry, XRD results, physical properties of the rocks, sedimentology, biostratigraphy in the Georgina Basin, et cetera, But the thing I want to talk about in a little more detail today is the geochronology that's come out of those rocks, because for the first time we now are able to pin where in the stratigraphy we are in that Carrara 1 hole. And the key to that geochronology constraint is the identification of these quite narrow and in some cases very subtle green glauconitic horizons that were interpreted or considered to possibly be volcanic tuffs, just from observation in the core. And then thin section work on those things, as shown on the right, has confirmed that yes, indeed, many of those are volcanic rocks. You can see beautiful glass shards and sort of bubble wall fragments and things like that in thin section. So for I guess geochronology in sedimentary basins, this is just gold to get actual volcanic rocks instead of having to use detrital zircons for correlation. So numerous horizons of these volcanic tuffs have been dated now by Natalie Kositsin and Chris Carson at GA. And this is the sort of headline, I guess, result out of those things. There's a whole swag of them down towards the bottom of the hole at about 1,600 metres depth, which tend to give ages around 16 and 11 million years, and then some slightly younger ones further up the hole. So now we know that that much of this Proterozoic stratigraphy correlates with the mid to upper Lawn Hill Formation, and that obviously there's been major episodes of volcanism through this period. So from an exploration perspective, I guess one of the key implications of that is that this western flank of the Carrara subbasin has stratigraphy that can be correlated in time to the stratigraphy that hosts the Century mine out in the far out to the east. And so if we're looking for similar sorts of base metal deposits, you know, maybe there's potential out here if we can find or track this stratigraphy to explorable depths near the surface. And that seems to be what's going on with what we've heard last week. An ASX release from Encounter in South 32, working on this western edge of the Carrara subbasin. So I guess there's more potential to look at, to use that sort of exploration model, I guess. And this was just to reiterate that same point, I suppose, that if you're looking for century style stratigraphy and mineralization, there's more potential across this Carrara subbasin. All right, I suspect I'm running out of time. So I'll wrap up. I know that was a whirlwind through lots of different sorts of data sets. If you're looking to get more information, there are various places you can go. There's a monthly Exploring for the Future online newsletter you can get from this web page here. There's lots of data in the GA portal, hopefully people are aware of. There's also a roughly monthly minerals alert that comes out via email, so you'll need to subscribe to an email list for that, and a whole bunch of extended abstracts with more about to come out. I've mentioned a few times along the way things that are imminent, just about to come out, new products and data, and this is just to promote that the program, the Exploring for the Future program, is planning a showcase event in about a month's time, or the 8th to 10th of August. This will be an online event over 3 days, but they're not full day sessions. They're about 2.5 hours per day. So there'll be obviously new data and reports promoted there, some of the new tools that are available to visualize and use that data, and plans for future activities over the next couple of years. So if you're interested in that, you can go to this website here to look at the showcase and register for that event. So thank you for the chance to come up and present that. And thanks to Helen again for the invitation. I look forward to the rest of the program.
Thanks so much, Geoff. We do have a question for you online. What is the time frame for releasing the solid geology map?
There won't be a single national map, I wouldn't think, until roughly the end of the, let's say 2 years from now, I would think. The effort, we're putting out a product from across the Delamerian, so the border regions of East and South Australia, Western Victoria, Western New South Wales. That'll be the next, I guess, tranche, and that's in review now. So I would think later this calendar year, you could get that. And then there's the West Australian data set is also pretty close. So yeah, later this calendar year, there'll be additional data sets to go with the North Australia data, and then hopefully the full national coverage in a couple of years' time.
Great, thanks. Are there any more questions in the room? Now, we did have our Minister for Resources here. Thanks, Geoff. Appreciate that. I think there's no more questions. You can find Geoff if you have any more at morning tea shortly. But we did have our Minister for Resources, Scott Stewart, in the room. He's run away. So he'll be back in about 2 minutes. All right. So he was going to say a couple of words. But we might get Dominic Brown from GSQ to come up and get ready. We'll get your microphone on. And just for those online, unfortunately, there's been some kind of a glitch with the online registrations, and everybody is showing up as Prue Osborne, but I can see that Richard Scott has managed to rename himself. So just Richard, if you can hear us online, can you tell everybody else how to change their names so that we can see who's asking questions and commenting? Oh, Prue is very inquisitive. Yes, Prue has registered about 60 times and has a lot of questions and comments for us. Okay. All right. I might just give our minister another minute if he's coming back. There he is. All right. So I would like to welcome up to the stage, he's walked back in, Minister Scott Stewart, who's the local member for Townsville and our Minister for Resources. So really pleased to have him here today, and please give him a very warm welcome.
Oh, good. Okay, thank you. Good morning, everyone. My apologies, I was just doing a quick Teams meeting technology, right? Which just explained why I didn't actually end up doing the Teams meeting. But can I firstly acknowledge the traditional owners of the land in which we meet today, the Walgarukabar and Bindal people, and pay my respects to elders past, present and emerging. And of course, acknowledge all the traditional owners of the lands in which you actually all work as well, because it's very important that we do acknowledge those. Great pleasure to be here with you today. Just dropped in, thought I'd drop in and have a bit of smoko with you during your conference today, and I know it's going again tomorrow. But thank you to the Department of Resources, and what an outstanding job they do. I'm very lucky to be the Minister for Resources because their work makes me look really good. So thank you, keep making me look good. They do an outstanding job. And I'm sure those of you that work with the team will certainly agree with me that, and look, this is going to be full of some really bad dad jokes. So here's the first one. These guys are the real rock stars. Oh, yeah, I know. Don't laugh. It just encourages me to do more. These guys are the real rock stars of, I think, of Queensland, because what we know is that when you look back over history of how Queensland has performed, particularly in the resources space, we had the gold boom, and that was sensational for Queensland. And then we've moved into coal, and now we've gone into the gas industry. But what's ahead of us now is the new economy minerals. And as we've heard from our presenters this morning, there is an absolute abundance of these new economy minerals, particularly in the northwest and the northeast of our great state. Just last Friday, I announced or released our QRIDIP, which is a Queensland Resource Industry Development Plan. And that's our 30-year vision of where we're heading and what that looks like, and the opportunities that will exist for us, but also those challenges out there as well. If you've had the opportunity to read a draft or to have looked through that, or to be able to give us that consultation back, you will see in there it's very heavily focused on the new economy minerals, because this is where we see the future for Queensland, because as the world decarbonises, and those economies will change, the world will be looking for those new economy minerals that we have an absolute abundance of here in Queensland. So we've got to put ourselves ahead of the curve, because we do have competitors out there in other parts of the world. Our biggest factor that we have working for us is our ESG credentialing. And this is where we're putting the money in the bank, so to speak, is to look at ways that we can to tell the rest of the world how good we are at doing what we do. Because, you know, typical Queenslanders, typical Australians, what we do is we just get on and do the job, and we're really good at doing the job, but we're really terrible at telling people how good we are. So our job now is to spin that. You guys continue to do the outstanding work that you do, but our job as a government is to tell the rest of the world how good you do your job, but also the great opportunities that exist, and attract those investors into here. Helen said you've got 3 minutes, and I think I'm pretty close to the end of my 3 minutes already. But can I thank you all for the work that you do each and every day, because we know that the easy minerals have been largely found. And so now it's getting harder and more difficult to find those new discoveries. And we can't have a great booming industry, particularly for our new economy minerals, if we can't find the stuff. So I encourage you to collaborate, to work with the resources team, my rock stars, but continue to do that work together. Because there's another saying that I have that my team is sick of hearing me say or hear, but it's the rising tide lifting all boats. That when we do work together, we do learn from one another. It just makes us all perform at a much higher level. So the opportunities are out there. Anything we can do to help, please catch up with us. I'll be hanging around for smoko for a cuppa, and then I've got to chuff off and do some other work. But thank you again for your outstanding work. We've got a great opportunity that lies ahead of us in the new economy minerals. Thank you.
All right, thanks, Minister. Now, without further ado, Dominic Brown from the Geological Survey of Queensland is going to talk to us about regional prospectivity undercover in Queensland. Rick's just going to get his presentation up. And for those online, we have resent a link so that you can actually be yourselves instead of Prue. First time in his life Rick's ever been shy.
Yeah. All right, g'day. I'm going to talk about GSQ's regional prospectivity project, which is designed to basically reduce geological uncertainty undercover and focusing on Mount Isa province. So the regional prospectivity program initially started off as a plan to re-assay a bunch of company material and do mineral chemistry on it, which is still part of the program. But as we started to get into the program, we realized that there was a big gap in our knowledge of where the material that we were looking to try and analyze was and what had already been done. So what we're trying to do is to capitalize on the existing geochemical and geological data and to collate this data, to bring it all together so that we can use it and then go back and try and fill in the gaps rather than starting the other way around. So this is where I see us. A lot of the things that Geoff talked about, that's really in the sausage end. We're in the grinder. So we've already got the meat from the companies and we need to get that data together so we can make something useful out of it. So there's lots of good things that can be made, like the depth of basement and the solid geology and these sort of prospectivity models. But before we can do that, we need to make sure that we have all our data in a form that's actually usable. So the current state of the data is up to 2011, we've got pretty much complete coverage of Mount Isa anyway, and most of the state up to 2006. But there's a gap that exists in our compiled company report data that's actually usable in sort of modeling and being able to use in different sort of software packages. And further to that, the data in the old data is generally focused on base metals. So you can see we've got good coverage over the Mount Isa inlier that's showing you different types of surface samples, but a lot of this data really doesn't have anything in the rare earth space. And to compound that, the modern data that has been collected by companies, we don't have compiled. So this is another look at our information gaps. So this is the broad view of the new economy minerals. And this is the current data, lacks most of those assays. So this is 75% of our data has this copper and zinc, but you can see it decreases significantly as you go throughout the periodic table. And we've got severe gaps in these spaces like the rare earth minerals and a lot of other things that have become quite important lately. So this is the data that exists in our open data portal, but has not currently been compiled into our drill hole database or geochemistry database. So we identified 400,000 soil samples in the Mount Isa province and up to 10,000 drill holes that are currently not in our database. They're sort of living in unstructured text files and in company reports. And so we've undertaken a program with Map to Mine to start getting all this data sorted out. So last night we received delivery of 3,800 of those 10,000 drill holes and 160,000 new bits of geochem data. And so that'll help us close the gap between the 2016 compilation and the current state of the data. And further to that, I've included some new high quality data that we've collected through CEI and Genova. And in the initial part of the program with our collaborators at South 32, we collected a bunch of new data in the southern part of the Eastern Succession. There's also a bunch of surface samples from the Crusader area that was collected through a CEI project as well. So we've got another 6,000 bits of high quality geochemistry data we can make sausages out of. And that's just the current state. So we've cut that 10,000 hole gap down to 6,000 and cut the soils down to 340,000, which is still a lot of data. But we're going to have a pretty good swing at it. I think we can take a pretty good bite out of it by just sort of using our data science tech skills and things to get into the GGIS-MT template data and reduce that number down quite significantly in quite a short period of time going forward. So one of the aspects of this, the initial aspects of this program is to look at the geochemistry of background. And we found that basically, once we started getting into it, the geochemistry of metamorphic rocks is quite complicated. And it wasn't as simple as we thought it was going to be. So we thought once we feed this program a whole lot more data, it'll be useful for the other programs going forward, particularly say the halo sort of work that's going on in the mineral system space, trying to expand out from mineralized rocks to unmineralized rocks. So by uplifting our data, we're going to be able to contribute in that space as well. The depth of basement is another space we're trying to contribute in. So we've got things like the sea-based model, which is fantastic, and the domain map that me and Joe made last year, which is pretty good, which is focused on the sort of top 125 meters of cover. But if we feed more data to it again, we'll be able to improve that, and we'll be able to step out into the sort of more explorable depths. So we've got a compilation of drill hole data that'll feed into that, but we're also doing these 1D inversions of the Magneto-Telluric data. So this is some work we're doing with CEI Round, and this is just a model from across the top of the MT array that Janelle showed us this morning. And these are the drill holes, they are not used to constrain the inversion. And you can see this is the resistive basement here, and it's doing an extremely good job of matching up with where the basement is, the resistive basement. So I think if we can feed that data into the depth of basement model, we can really expand our model outside of where there's drill holes and get good coverage. So there's the MT coverage, I think that's really good. And another thing that we want to do in this project is to reduce geological uncertainty by improving our solid geology mapping, both by uplifting our current data. So we've got compilations which have been completed in the Selwyn area and the Central Eastern Fold Belt, that they haven't been integrated into our seamless solid geology coverage yet. So that's underway at the moment and should be completed quite soon. And we plan to complete a new solid geology coverage up in this Northern Eastern Fold Belt where we can uplift the data to something more like a 100K mapping, because we've got the MT and the AEM and a whole bunch more drill hole data, and I think we can make a big difference to the quality of that. And that's it. So yeah, the overall thrust of this project is to try and reduce the uncertainty for exploration by reducing geological uncertainty in covered areas in Northwest Queensland. And we're undertaking uplift of a lot of our different types of data, and we're going to fill in some of those gaps once we understand where they are better and update the soil geology as well. Thank you.
So I learnt last night that Dom had a chat with the South Australian Geological Survey and almost went to them. And after seeing that picture, I'm thinking they can have him. Bloody hell.
It's a prospectivity sausage.
It's a prospectivity sausage. Jesus. Okay. Does anybody have any questions for Dominic? No, you've just done it. No, that's awesome. This is a project that's only just kicked off, so there's going to be a lot more to see, and we're doing a lot of it with the help of South 32 and other companies, so really appreciate that collaboration. All right, there aren't any, there's one question that's just appeared online. Richard would like to know, when do we think this will be finished?
Well, we'll release a few things pretty quickly. Like we just got that data from Map to Mine last night, so we should get that out once we QC'd it in the next month or so, and then with the CSIRO 1D inversion thing will be finished pretty soon as well. But there is still 2 years to run on the entire project.
I think it's sort of going to be the sort of project that will never end. There'll always be more to do on it.
You could easily send it out into different parts of the state.
Yeah. And I think there's a comment here that it's very good working on these problems. So good job. Anyone else in the room? Otherwise, thanks, Dom, again. And we will break for morning tea. There should be morning tea now out in the foyer here. And we will come back. We will come back at 10:30. 10:30. All right. Thanks, everybody.
That which has been seen cannot be unseen.
that on your belt or pants or something. Laser pointer, it's the green.
Yep, forward and back.
Slides, is there?
No worries. Should we start?
Are we on time? All right, everybody, if you can take your seats, we'll get started again. This is obviously the rowdy table in the corner over here. Stephen Mickleplate. Okay. All right. We're going to kick off again for the pre-lunch session, and we're going to start with GSQ's own David Purdy, who's going to talk to us about his project on Peralkaline rocks in North-East Queensland.
Thanks, Helen. Yeah, so today I'm going to talk about our project, which is focused on Peralkaline magmatic systems and their evaluation of those for critical element or critical metal or new economy mineral enrichment. And it's actually throughout Eastern Queensland, so it's from the southeast corner right up into central Queensland, really. So globally, igneous rocks are very important sources of critical metals. So the rare earth elements and some of the other high field strength elements like zirconium, niobium and tantalum. And of the igneous rocks, peralkaline rocks are considered prospective because of their relative enrichment in the heavy rare earth elements. The challenge and also the opportunity that we have in Queensland and globally is that these aren't traditional commodities. And they're not well-known mineral systems. So we're really at the starting point of understanding the distribution and potential for critical metal enrichment in these systems. When we think about critical metal enrichment in peralkaline magmatic systems, there's some quite elegant models in the literature to explain how this happens. And basically, it starts with very low degrees of partial melting of an enriched or metasomatized lithospheric mantle. And following this, as melts ascend through the crust, they evolve by very high degrees of fractionation so that the resulting liquids can become hyper-enriched in incompatible elements, potentially including critical metals. To form high levels of enrichment, this needs to be a fairly closed system, so you don't want too much assimilation of crustal materials or too much interaction with other magmas. And importantly, you need to retain volatiles, and this enhances alkali solubility and also high field strength element solubility. And that allows fractionation to progress well beyond where it normally would and lead to hyper-enrichment. So this is the basic model that we're using in Queensland, and we're interested to see where our peralkaline igneous rocks sit in this model, and do they have the potential to be highly fractionated. This scenario plays out in two main continental settings, so continental rifts and in mantle plumes in continental environments, so areas of bimodal magmatism. Secondary enrichment is very important as well for forming economic deposits. This might be hydrothermal alteration or simply weathering. The regolith developed on enriched igneous rocks are important sources of critical metals, and these are the ion adsorption deposits that people will know from China. In Queensland, we really haven't done much soil geochemistry at all, particularly in terms of rare earth elements. So this is something we can easily test in Queensland, but overall, primary enrichment in the igneous starting material is critical. So that's where the focus of our work is going to be. So our current understanding of peralkaline, or the distribution of peralkaline rocks in Queensland, is very basic. We know that igneous suites, some igneous suites include peralkaline components, but we don't have a good understanding of the internal variation. We also don't have a very good understanding of the degree of fractionation within individual units or individual suites. And a lot of rock units lack geochemical analyses altogether, or they only have a few XRF analyses. So you don't have the full suite of rare earth elements. So that's a big and easy gap we can fill. So the GSQ project aims to answer the question, do igneous rock suites in Queensland have the potential to host highly fractionated peralkaline magmas? And to get to this, we've outlined several objectives. The first of those is to compile an inventory of peralkaline or near peralkaline igneous rocks in Queensland. So this is a compilation of information about the distribution, lithology, mineralogy, geochemistry, basically all the known information from the existing literature. We then want to look at the petrogenesis of individual suites to evaluate how highly fractionated they are. Is there potential in those suites to host highly fractionated rocks? On a larger scale, we also want to look at the origin of peralkaline magmatism. So what are the largest scale crustal or mantle controls that favour peralkaline magmatism and highly fractionated magmatism in particular? We also want to look at the subsurface plumbing system associated with these suites. So can we use geophysics to model these systems at depth to see if there's, see how connected they are, or if there's magma reservoirs at depth that might be prospective. And then we also have that bonus objective of secondary enrichment through regolith geochemistry. So the inventory is already completed. This has been published and you can get it from the GSQ open data portal. For the inventory, we focused on rocks that were emplaced in rift or plume-related settings. So in Eastern Queensland, these are rocks that are late Triassic or younger in age. And they extend from sort of the Mackay area right down to the southeast corner. In compiling the inventory, we found that these rocks fell into 3 age categories fairly nicely: late Triassic, Cretaceous, and Cenozoic. And between those, there's differences in the settings that they were in place, the rock types, mineralogy, and things like that, which you can see outlined on this slide. But there's also significant differences in the geochemistry. So these plots show all of the data that we compiled for the inventory. So these are from existing literature and theses. And you can see I've made the peak range volcanics these yellow symbols. They're Cenozoic, but just because we use them as a bit of a benchmark for comparison. So you can see in terms of the peralkalinity, there's a lot of Cenozoic and some Cretaceous rocks that are plotting down in the peralkaline field. The Cretaceous rocks down there are ones that are fairly small volume and occur in sort of bimodal suites. But you can see the peak range volcanics really do stand out, particularly in terms of total rare earth elements. We do have some Cenozoic samples and Cretaceous samples getting up in that area. And hopefully we'll see some more as we collect more data in this project. So our current work is focused on this area that I mentioned before. And the larger map there just shows the distribution of some of the major units. And the symbols, the yellow symbols on that map are our samples so far. So we've spread our sampling quite widely at the moment. And we're now working on sort of some areas that we identified in compiling the inventory and doing some more detailed work in those areas. So I'll run through some examples of the sort of work we're doing at the moment. The Mount Cooper trachyte, for example, is a fairly small Cretaceous unit that crops out here down to the southwest of Rockhampton. And the original description of this unit is that it compiled a pile of intermediate to mafic volcanics and volcaniclastics, which are overlain by rhyolitic and tetrachitic flows and domes. So in the scoping phase of this project, we drove by there and collected a rock which had fairly high zirconium, a felsic rock. So we thought this is going to be a good area to get up higher in the sequence into those felsic units and see just how enriched they become. We did that over probably a day and a half or so in between a lot of storms that were occurring at the time. And these are all our observation points here. So we did a lot of traverses up creeks and ridges and so forth. What we actually found is that the unit is just a fairly thin pebble to boulder conglomerate with clasts of basement sediments, so clasts of the Bowen Basin, also intermediate volcanics and felsic volcanic clasts. And this conglomerate is treated by an extensive series of rhyolitic tetrachitic dikes. Mainly, there's also some small pods of granite and pegmatite in there as well. So quite different to the original description, and in some ways sort of lowers the prospectivity of the unit. This is an example from right up in the guts of the unit where we should be in felsic volcanics, but what we're actually seeing here is an outcrop of the Back Creek group. So the Bowen Basin there, which is intruded by a felsic dike you can see here. So if you go upslope from this, you are actually into the Cretaceous conglomerate, but it's only a very thin package. There's an example of a conglomerate. What we did find in this area is some veins that were quite rich in niobium and zirconium. They're probably associated with one of the pegmatite bodies, but that's something we might follow up in future. Here's the data from the samples we collected, extending across from trachyte into the rhyolite fields. We do see some high zirconium values up around 3,000 to 3,500 ppm, but we do lack high total rare earth elements for these rocks. Last week, Emma and I were up around Nebo looking at the felsic Cenozoic volcanics up there. And in this area, they're just mapped as unnamed units, unnamed TV, tertiary volcanic units. But what we find is they're actually quite complex. Some of these bodies are sills, some of them are rheomorphic ingobrites, some of them are lavas, some of them are domes. Just as an example, we did a traverse up this hill here. There's quite a lot of relief in this area, a couple of 100 meters. And this is what we found. The Bowen Basin actually extends a fair way up this hill. In this case, it's the Mount Benmore volcanics. Overlying that is Cenozoic vesicular basaltic lavas and scoriaceous breccias. There's a very extensive rhyolitic dike, extends for several kilometers. And then there's a very thick package of volcaniclastic sediments, which are scoriaceous in the base, at the base, grading up to more felsic to the top. That's about 80 meters thick in this area. And then overlying everything is a coherent trachyte, probably a lava, with a big autoclastic domain forming this knob on the edge of the cliff there. Similarly, we've been doing some work in the Minerva Hills volcanics, another Cenozoic unit near Springshaw in here. We're fortunate to have Sam Platt from QUT, who's doing a master's research project in the area. We'll just put up the overlay there. And what we're finding here is, again, is a lot of complexity in the geology and the volcanic facies in this area. So Sam's been crawling all over these hills. It's a very large area. And he's trying to understand the geology and volcanic architecture, and also collecting a lot of samples for geochemistry, because there hasn't been a lot of geochemistry done on the felsic rocks in this particular area. Another area that we're going to be working in the next few months is the Mount Hedlow trachyte, which is just up to the northeast of Rockhampton, out towards Yeppoon. This area is slightly different in that it's probably more of a true dome field. So you can see all the domes here in this panoramic photo. So all of the felsic volcanics here are actually forming individual domes. So again, not a lot of geochemistry from this area. So it'll be interesting to see what comes out of that. And in this area, we're working with Brendan Simpson, a PhD student at UQ, who's collecting geochemistry data from this area as a small part of his project. So moving on to the geochemistry that we've collected in our project so far, we've got about 150 samples that we've analysed. Again, I've separated out here Christmas Dome. So this is from the Southern Peaks Range, and they're the yellow triangle symbols, which again we use as a benchmark. So this is the area that NorthX has been exploring for critical metals recently. And these data are from the CEI drill hole that we reanalyzed some of the samples just to compare methods there. But overall, you can see a good spread from sort of low silica phonolites right through to high silica rhyolites. Quite a few samples pulling down the Peralkaline fields already. But what we really lack is those high total rare earth element values. So we don't really have any data at all up around what we see at Christmas Dome yet. But we do have a lot more sampling to do. So hopefully we'll see some of this trend pushing up further. A bit of a messy spider diagram, but I just wanted to show that the pattern for the Christmas Dome is quite consistent for all those samples. We do have similar patterns amongst other rocks that we've collected, but again, we don't have anything with the high heavy rare earth element values that you see in Christmas Dome yet. We also did a very simple soil geochemistry study on the Kubi trachyte member, which crops out around Crow's Nest in the Toowoomba area. We chose this area because there are some quite thick soil profiles developed there, and we're also able to access some quarries where we're able to sample fresh trachyte, weathered trachyte, and some soil profiles as well in the same area. And really here we're just trying to compare relative enrichment or depletion between fresh rocks and soils. And what we found is that there is enrichment in the soils. So on these plots, the solid symbols are fresh rock, the open symbols are soil samples. So for most of the sites, we do see enrichment in the soils. For this particular site here, we think that is related to clays, so an ion absorption type model. For other sites, it's probably more related to residual accessory phases in the soil profile. And we actually get the opposite for this sample, this site here, which we're still scratching our heads about a bit. But that little project is published as a GSQ record. I tried to upload it to the portal the other day and it didn't work, so it should be up there in the next week or so, hopefully, once that gets fixed. Moving on to future work, we're going to continue filling up that the knowledge gap for poorly studied units. We'll move on to petrogenetic modelling and looking at isotopes to consider those larger scale controls on peralkaline magmatism. We've done some high logging, so we've high logged the NorthX CEI drill core, and we've also high logged some of our samples, and that's some work we'll probably keep going with to see if we can identify rare earth element rich domains or rare earth element rich phases. And as I mentioned before, we also will be looking to do geophysics. As we progress, we'll choose an area where we will do some probably ground geophysics to try and understand the subsurface plumbing system and see if there's anything interesting at depth. Oops. A lot of people to thank that have been involved in the project. All of that existing geochemistry, a lot of that was compiled from theses. So thanks to all the students who compiled all that information. Ross Chandler and Carl Spanler for alerting us to this style of mineralisation in Queensland. Sam and Brennan, postgrad students working on these rocks. The landowners of Central Queensland have been very helpful with land access. They've also been very interested in the results of the project. And of course, everyone at GSQ has been involved so far. Bob, Dom, Joe, Emma, Janelle, and Dan. Thanks a lot.
Thanks, Dave. Any questions for Dave? Yelena?
Dave, I'm just curious, you have this incredible enrichment in the zirconium and rare earth elements. What about uranium and thorium? Do you see the same enrichment there? It's first question. And the second one, what is the mineral phase which is holding all these nice commodities?
To answer the second question, we don't have a good understanding of the mineral phases yet. So there has been that work done on the peak ranges, that Cyril did, that outlined some of the mineralogy of those. I won't try and pronounce the names of them, but that report's available on the portal. But for the rest of the project, we don't know yet. So what I'm thinking about doing is, once we have sort of a top 10 or top 20 sites or something, we might then investigate the mineral chemistry of those. And yes, for some of these, we do see enrichment in uranium and thorium as well.
Steve?
Thanks, Helen. Thanks for the talk, Dave. Now, I'm a structural geologist, which means I really wish I knew more about igneous geology. So you mentioned in a few sites that the sampling was showing that you weren't getting the kind of the high earth element values you were looking for. What I don't know, because I'm ignorant, is could that because your sampling is too sparse? Is it possible we've missed something in these complicated intrusive complexes, or is the sampling representative of a fingerprint for the whole intrusion?
Well, I mean, both. Both. We're trying to sample as much as we can. So when we turn up to, for example, the tertiary felsic fields, at the moment they're mapped as these blobs of tertiary volcanics. So we're trying to go to every single one of those and sample them. What we do is we take the handheld XRF around with us. And so we will analyze in a lot of places, but we might only collect 1 or 2 samples from each body. Christmas Dome, for example, if we're going to use that as a benchmark, I think you could walk over most of Christmas Dome and you're going to get pretty high values. But there's other places where the highest values will just be in dikes. I think that the Glasshouse Mountains is a good example of that. There's some really high values from dikes around the Glasshouse Mountains. So it's tough. Yeah, you can't sample everything, but yeah.
We've got 2 questions online, and then we'll quickly go to the next talk. So Alex McCoy West is asking, what type of isotopes are you planning to do to constrain the broader scale processes?
Probably samarium neodymium, because there's already a body of that data coming out already. I know Carl's doing more as well, so that'll create a good picture across Eastern Queensland.
Excellent. All right. And then the next question is from Valeria, but I think you've already answered it. So have you identified your dialite phase, Na15CO6 FEM N3 zirconium 3 SiO, blah, 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 blah. So I think you had already said that you hadn't identified the specific hosts to the mineralization yet.
Yeah.
Yep.
Well, it's interesting. One of the rocks that we have sampled is supposedly eudialyte bearing, and that was reported in the 70s. But we still haven't found eudialyte in those rocks that we collected from there yet. So it's tricky. It's a tricky business.
Yeah, great. Okay. Thanks, Dave. I will now move on to the next talk. Otherwise, Evan will get cranky and tell us we're all running late. Alex Edgar, we're going to welcome you to the stage from JCU to talk about collisional orogenesis in North Queensland, implications for critical metal mineralisation.
Probably just don't have my name on it. Yeah, it's not there.
Were there any more questions for Dave just while we're getting the next talk set up? Oh, Johan.
Where's Dave? Thanks, Dave, for the talk. It was really good. Just a question. Do you measure for fluorine? Usually in these systems, fluorine is quite high and you have fluoride. You do?
The answer for those online was yes, he does. Any more questions? All right, Alex, you ready to go?
Great.
Please
Thanks
take
very
it
much,
away.
Helen. And thanks for the survey for inviting me here today to talk. It's nice to get out and give a presentation to a crowd. So my name is Alex. I'm a PhD student at JCU. I'm in the third year of my PhD at the moment. I've been flying under the radar a little bit. Haven't really had a chance to talk about what I've been doing, even though I've been spending lots of money. So it's a good chance to share some of those results. Broadly, what I'll be talking about today is some indications of collisional orogenesis in North Queensland. So basically a flip in the tectonic model and how this may influence how we explore for critical metals, particularly in North-East Queensland. So yeah, a little bit of an overview of what I'll talk about today. I'll give a bit of a background on kind of the existing or accepted tectonic models for North-Eastern Queensland. And then I'll sort of talk about where my project fits into that. I'll talk about a regional geology, the local geology. Then I'll start talking about ultra-high pressure metamorphism, which is really the crux of what I've been doing, some of the indications, the evidence we have for that. I'll talk about the tectonic implications that we can sort of draw from ultra-high pressure metamorphism in North-East Queensland. And then I'll sort of start arm waving about possible collision and mineral potential. So first of all, I just wanted to talk about the Tasmanides broadly and kind of the tectonic model that people associate with it. This is time-wise from late to recent. So the idea is you have a long-lived subduction complex, which is westward dipping. As you have periods of extension associated with slab rollback, you open up back arc basins, magmatism, sedimentation deposit into those basins. Then you have periods of compressional orogenesis, which have traditionally been associated with just some sort of subduction jamming, whether it's accretionary sediment or whatever. And you close those basins up, invert the basin, deform it, etc. And then the process essentially repeats itself. And that's our cycles from extension to compression. And this has been termed in the last 10 or so years as accordion tectonics because of this sort of motion. So more specifically with North-Eastern Queensland, or I should say first, the models do become more complicated in that simple sort of accordion style when you have to explain the geology that you see. So in North-Eastern Queensland, for example, this model here by Henderson 2011 introduced the accretion of a small oceanic arc. into their model, which is related to the margin of the Broken River and the Greenbelt provinces, which I'll talk about a bit more later. But essentially, it's the same thing. It's subduction, accretion of a small arc, a lot of extension in the back arc, retreat of that subduction complex, and eventually closing of that basin. I just did that backwards, but if you could reinterpret it. And then another one here by Korsch, which is a geophysics-based study. This one does go from bottom to top. Again, subduction complex, arc, back arc basin, possible accretion or buildup of sediment, deformation of the back arc, retreat the subduction complex, new arc, new basin, etc. And the processes repeat itself. So just with a bit more sort of a time element to it, we have the Delamerian orogeny, which is best expressed in the southern Tasmanides. But in North Queensland, we do have a bit of evidence in some of the older rocks in the Charters Towers and Anarchy inliers. Following this compressional event, we go into, during the Cambrian Ordovician, we go into an extensional event where in the south, that's expressed by east-west extension with the eastward retreat of this subduction complex. And it's been interpreted that we've experienced that same sort of tectonic regime in North Queensland, again with the eastward retreat of a subduction complex. And then we have the Benambra orogeny deforming those basins that opened up during that earlier period. Just what I'd like to make sort of clear here is everything is apparently an extension during the Cambrian to Ordovician in North-East Queensland in the traditional models. So now for my project, how it sort of fits into all of this. Okay. Yep. Okay, good.
Yeah, so don't hit that one.
Okay, I won't hit that one again. So yeah, we were looking at the, I guess, the regional geology of North-East Queensland, and with this sort of back arc basin model, we were noticing that along many of the major structures in North-East Queensland, we had these lenses, pretty extensive lenses of ultramafic rocks. These are particularly in the Greenbelt province, which we know to be mineralized with the Greenbelt laterites. These were traditionally interpreted as altered ultramafic intrusions, but when you really start to look at their distribution, even though I don't have it on this map, they're really situated very closely with these structures that run along here, 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 up here, and along this margin. And their original interpretations from the 70s really hadn't taken into account the potential of ophiolite complexes at that time. Now that we have a better understanding of those, it looked to us like these were more likely to be ophiolites, which you wouldn't expect multiple suites of ophiolites sitting in a back arc basin, because if you were to open up a back arc basin so much that you were exhuming ultramafic rocks, when you close that basin, you would expect to be subducting that material first. So we decided upon sort of 3 to 4 key study areas for the project. And what I'm going to be talking about mostly today is our findings from this area here, which is the Running River Metamorphics, which is situated along this fault here, which is the Clark River Fault. So a little bit more in detail about this area. As I said, the Clark River Fault is a major structure that separates the Charters Towers province from the Broken River province. That's also the boundary between, well, a boundary between the Thompson origin and the southern Mossman origin. We also have Thompson origin material in the Greenbelt province. So in the early Paleozoic, we are supposedly in the northeastern margin of Gondwana, and we're part of this broader Terra Australis origin, which includes like the Tasmanides, the Ross origin, etc. So zooming into the Running River Metamorphics, what are they? They're basically a suite of complexly deformed amphibolite facies, metamorphic rocks. They comprise mostly of biotite gneiss as the basement, a suite of amphibolites which have been tectonically emplaced against the gneisses, That's them up there. That's actually a block of amphibolite that's been rafted by a tonalite here, and it's starting to release this felsic leucosome. There's also some ultramafics in the region. They're far more prevalent than what I have mapped here. We've only really looked at a small portion of the whole formation, and every time we go back to the field, we find more and more of these things. So they comprise things like antophyllite schists, hornblendites, chlorite schists, etc. And then we have a suite of these interesting quartzites here, which have also been rafted, like I said, by that Falls Creek tonalite. We did some petrography on these quartzites and we started to find some pretty interesting things. So the quartzites are located up here along the margin of the Falls Creek tonalite. So these are garnet-bearing quartzites. They basically comprise mostly of quartz, of course, these garnet crystals, some amphibole crystals, and these sheared biotite zones. We started to look in a little bit more detail of these garnets, and that's when we started to find evidence for ultra-high pressure metamorphism. So I'll stay on this slide for a little while and explain these features, but essentially the first thing we noticed was in these garnets, not a great picture, but there are these striations running through them, these sort of inclusion trails. And amongst those inclusion trails were exsolution needles of rutile and apatite. So the theory there is that under increasing pressure and temperature conditions, garnets can incorporate excess titanium and phosphorus. And during exhumation and depressurization, that titanium and phosphorus is no longer stable in the garnet, so we exsolve rutile and apatite. Those aren't necessarily diagnostic ultra-high pressure, they're more just a high pressure or high temperature feature. So we kept looking. And the next feature we found were these guys here. So this is a garnet grain, a bit of chlorite here. And these are quartz inclusions sitting inside those garnets with these radial fracture patterns around them. In the literature of ultra-high pressure metamorphism, that's basically indicative of the transformation of coesite, which is the ultra-high polymorph of quartz to coesite, to quartz, sorry. And during that transformation, there's a significant volume increase, which produces the radial fracturing around the grains. And that transformation, which at 700 degrees occurs at about 2.7 GPa, actually marks the boundary of high pressure to ultra-high pressure metamorphism. And that's that reaction line there. We kept looking and we kept finding new and interesting things. So in this grain here, this is a garnet, we have this suite of sort of cubic black inclusions. Most of that is now cubic graphite and carbonate, but if you look in detail, you can actually find diamond in there. So we have this reaction line again, the transition from graphite to diamond, which occurs at even higher pressures and temperatures. We kept looking, well, at that point we were pretty excited, but we still had these features here. We don't know exactly what they are. These are quartz rods or laths oriented sitting in the cores of some of these garnets. To us, and compared to the literature, they look like quartz exsolutions, which is indicative of like mega pressures of 6 GPa and above. So that would correlate with rocks, which have seen depths of like 200 kilometers. We weren't too sure about these though, so we've sort of had a conservative estimate of the PT conditions at Running River, or that this quartzite experienced, at about 4 GPa at 800 degrees Celsius. So we're like, oh, that's pretty cool. And we started to try and bring some conclusions out of this finding and how it could influence the tectonic model. So we had a combination of things at Running River. We had pelagic quartzites, which were hosting these garnets, an OIB geochemical characteristic to the amphibolites, which are basically interbedded with the quartzite. And we had ultra-high pressure metamorphism. So we think that it's pretty clear that the Clark River Fault, which runs along the Running River metamorphics, is an ancient suture zone, or at least a subduction complex. Now the question is, which way does that subduction complex dip? With the traditional model, everything basically dips to the west. With our model, we've had things dipping to the east. So how can we justify that? On the southern or southeastern side of Clark River Fault, we have that Falls Creek tonalite, which intrudes the entire sequence. That has a pretty strong continental arc signature, and time-wise would match up with basically SYN or just post-collision, or yeah, I guess an active subduction complex along that margin. Additionally, we've also been looking at the McCross and Igneous Association, which is a little bit older, and the 70-mile range group. And we think there's potential there for that to be sort of like an arc, back arc pair, possibly related to this southeastward dipping subduction complex. So critical metal wise, what does this mean? Well, it means that the Clark River Fault, there's potential for an arc sitting on the southeastern side of the Clark River Fault, which wouldn't have been described before. And this would be prospective for porphyries, potentially IRG, orogenic gold, tectonic ultramafics, so slices of ultramafic material which have been thrust on the continent, BMS styles like Cypress style BMS, and of course laterite mineralization. So yeah, in our model here, we've kept it quite simple, of course. You'll notice that we haven't included the Greenbelt province or the Broken River province in there because we really don't know how they sit. And at the moment, we have it as a subduction complex dipping to the southeast and an eventual suturing event between the Thompson origin and potentially the North Australian Craton. Could be the Broken River province, could be the Greenbelt province. We're not 100% sure. Don't do this again. Okay. So it's a little bit more about the ultramafics we've been looking at in the running river metamorphics and their critical metal potential. Every time we go out there, we collect new samples and they're lighting up with certain elements, particularly scandium and vanadium. So, and those are sitting mostly within this hornblendite. We differentiate a hornblendite from an amphibolite based on the fact that the hornblendite is extremely coarse grain and basically 95 to 99% hornblende, whereas the traditional amphibolites have a plagioclase content of 15 to 20%. This is what it looks like in thin section. That's probably a field of view of about a centimetre because it's quite a coarse grain rock. And within this hornblendite, we have enrichments of vanadium, which is sitting mostly in ilmenite, and scandium, which is actually sitting probably in the hornblende itself. That sounds terrible because you've got it in a silicate, which you'd never be able to recover. But what's interesting is that any potential laterite which may develop on top of these hornblendites has the potential to be up to 10 times enriched during that weathering process. So a laterite developed on top of these could have, thousands of ppm scandium. And then, yeah, we've had some chromite-rich rocks as well. So in the entophyllite schist I mentioned before, that's quite enriched in chromite. You also have this interesting rock here, which we're not 100% sure. So all this bright material is chromite grains. You can kind of make out some relict grain boundaries. This is basically a chlorite schist now. And we think that maybe it was actually a chrome-rich pyroxene prior to retrogression. And it's essentially exolved all the chrome as chromite. So yeah, I just wanted to make that point again. The amphibolites I had on one of the earlier maps that trend in the northeastward direction, all of these extend under this cover and are likely continuous along the entire Clark River Fault. So there's really potential for these things to be concealed under, I guess, relatively thin cover. And there is potential there for some high-grade laterite mineralization. Another point I'd like to make is the similarity in the geology between all of these basement metamorphic terrains. So whether it's the running river metamorphics, the Clark River metamorphics, the Hall to Rord metamorphics, they all have very similar geology, and I wouldn't be surprised at all if the amphibolites in all of these regions have anomalous scandium and vanadium. So I just want to put this slide up here again, took it out of the Bible by Groves. So basically it models the potential for gold mineralization in various tectonic settings. And when I was going to input this into the slide, I sort of thought that it actually fits quite well with potentially what we're seeing in North-East Queensland. So we have this sort of collisional event in here. The theory, of course, with mineralization is thicken the crust, promotes melting. You're inputting thrusts as well. Later on during orogenic collapse, those thrusts are reactivating to extension faults, which tap into those melts, hopefully mineral-rich melts and magmas, which are placed in the upper crust, and you can form orogenic gold and IRGs, etc. Potentially, this is highly speculative, but potentially the Greenbelt province is a an island arc. We're not 100% sure, but it'd be a nice story if it was. But that's basically what we think is going on. So a little bit of future work and a bit of shameless self-publication. We put out a paper recently on the metamorphic diamonds, which you can look into. It'll be available in about a week or two with a lot more detail into that. We've also been looking at some of the north-south trending structures further in North Queensland, where we think we're seeing similar styles of tectonics with potential arc collisions running along the Russell-Mulgrave fault and also potentially along the Palmville fault. Some of the things we want to work on a little more in the future is investigating this enrichment of scandium and vanadium and why it's so high in these amphibolites and hornblendites. We want to chase up some island arc geochemical affinities, as I mentioned, associated with the Russell-Mulgrave and Palmville faults. Ultramafic lenses along the Palmville fault, potentially also sitting on the western side of that fault. Maybe they represent clips or ophiolites. And also an interesting section of the Ainslie metamorphics, which has been mapped within the Hall's-Reward metamorphics. So the Ainslie metamorphics belongs to the Georgetown province. It's Meso or Paleoproterozoic in age, and it's sitting in conjunction with the Greenvale province Hall's-Reward metamorphics, which are Cambrian to Ordovician. And it's potential, if we are dealing with some collisional events and thrusting or nape style tectonics, there's potential for that to actually represent a window within the younger geology. So a couple of acknowledgements. Of course, I'd like to thank the GSQ for the generous funding of the project and the opportunity to present today. And also my supervisors, Johan Stanislav, Paul Dirks, and Carl Spandler for their input and support. But other than that, I'd like to take some questions if you have any. I was dreading a question by Greg. So, yep. Yeah, I sort of skimmed over that.
Hold on.
Oh, sorry.
For those online, we need to have the microphone. So hold on.
Have you dated the UHP metamorphism?
To an extent, yes. So I skimmed over that a little bit. The amphibolites or the felsic gneiss, in which the quartzites are basically in place within as an age of 472 MA. And all of that material, the fibrilites, the quartzites, which host the ultra pressure metamorphism, the felsic gneiss have been intruded by the Falls Creek tonalite and rafted along those margins, and that intrudes at 456 MA. So we're sitting between 456 and 472 as the date of ultra pressure metamorphism.
That's similar to the ages out of Charters Towers on the pegmatites and stuff that that intrude the high-grade metamorphics.
Any more questions? Are there any online? No. Oh. Okay, thank you so much, Alex. And now I would like to welcome Coralie Siegel from CEI Round to the stage. She's going to talk about some of the work that she's been doing with us. Let me just get the title here. Alteration footprints of tungsten, moly, bismuth, mineralization, insights from the Wolfram Camp deposit. We will do the microphone shuffle. Thanks, Coralie.
you know that the of smartphone, the vibrator board is done by a motor, and is a tungsten panel. And that tungsten alloys can be everywhere.
No, there's something.
I can't hear you online.
Sorry about this. I'm not exactly sure what's wrong there, but.
Is it better now? Just click online. Can they hear me? Oh, wait.
They can hear you a little bit.
A little bit. Okay, I'll try to speak louder.
Have to use your outside voice.
Yeah, speak louder. Okay, I'll try not to scream. Is that better now? Yes. Okay, good. So I was saying in your mobile phone, there is a little vibrator mode that is made of a motor, and associated with it is a tungsten alloy, and that tungsten alloy is very dense, making that motor turning around. That's what makes your phone vibrate. So one of the properties of tungsten is that it is dense. Tungsten, when it is alloyed with other metals, is also very hard and is used as cutting tools, such as that drilling bit here. Tungsten is also heat resistant, it's got a very strong resistance to temperature, and as such it was used as filament in the now phased out light bulbs, but are also used in X-ray tubes. Tungsten is on the critical mineral lists of US, Europe, Japan, but also Australia. The potential in Australia is quite high, with demonstrated resources of about 577 kiloton as of 2020. Yet the production of tungsten is quite little, it's less than 1 kiloton. When we look a little bit at the resources, we can see that Australia has about 11% of the percentage, the world percentage. But the production is dominated by China, with 82% being produced by China. As of 2018, one mine was operated, was a Kara mine in Tasmania, and I think that's changing with more carbide going into production. So how do we explore for tungsten? There's a little tip in this photo here. If you see at the front of it, there's some granitic rocks, granite boulders. Tungsten is commonly associated with granitic rocks. And so the question is, what sort of proxy we might use to help exploring? And that's one of the aspects I'm looking at here today, looking at the Wolfram Camp deposit. So first, I'll look at a little bit of the schematic diagram. Tungsten is generally associated with the late stage evolution of the granitic body when it goes from the magmatic to the hydrothermal transition. Tungsten then gets enriched in the quartz pipe, as shown here in black, and that's sometimes occurring within the country rock. So Australia's tungsten resources are quite diverse. Today I'll be focusing in North Queensland, mostly on the Hodgkinson province. You see on the map on the right-hand side. What's interesting in this map is you will notice purple dots, which are the tungsten occurrences, seems to be essentially associated with granitic intrusion, shown on the geological map as pink, while the tin resources are essentially located on the Hodgkinson sediments. So there's the green dots on the purple, pale purple formation. So that formation here. So green dots. So there is proximal tungsten and distal tin. And I won't go into the details because that's not the scope of this study, but I'll be focusing on the Wolfram Camp in that black circle, which is essentially tungsten with no tin occurrences. So the Wolfram Camp deposit is hosted in the James Creek granite, Carboniferous granite. at the top of the rooftop, the intrusion, and at the contact with the Hodgkinson sedimentation here in blue. And when we look at the cross section from the top of the granite to the country rock, we see some layering at the top, and the layering are composed of mica-rich granite, quartz granite, and quartz pipes. Some of those quartz pipes are barren, some are mineralized. Today, I'll focus on DRD05, a drill hole at the top, which is cross-cutting here you see in red from the top of the intrusion into the country rock. So we've done bulk rock geochemistry on a selected set of samples shown here as red triangles. And you see they're quite highly oxidized and have elevated rubidium-strontium ratio, suggesting they're highly fractionated. They compare quite well with the host James Creek granites and with the overall ore and supersuite that the James Creek granites belong to. But you can see the samples we analyze are very perluminous. I think that perluminous character is probably secondary due to alteration of those rocks. The log shown, so it's been logged as 8 different lithology. On the bottom in brown, we have the sediments of the Hodgkinson province. In purple, there's a strongly weathered altered granites. At the top in blue is a fresher portion of the granites, and then of interest we have in red the quartz granite, in orange the micaceous granite, and in pink the quartz pipe. And it's quite difficult to see the quartz pipe at this scale, so I've shown them as arrows, so they're quite regular along the hole. We've done data mosaic to identify boundaries, and those boundaries, so they're lithogeochemical boundaries. So we've used mineralizer data. So here we used aluminum, silica, potassium, calcium, and iron, and done some clustering to identify the different boundaries. Overall, matches quite well with, at the top of it, we have the fresher granite in pink. It's more the quartz pipe, the bit of quartz granite. In orange, we have more the quartz granite. It's not reflecting quite well with the log, but I'll show you in a second a little bit more the data. In green, we have, again, a zone that is not really well presented in the logs, that is enriched in calcium. So you see that wiggly line in red at about 150 to 170 meters depth is that calcium-rich zone. And then in brown seems to be lumped together the sediment of the Hodgkinson province, but also the micaceous granite. And when we look at those cluster of data, we see in pink the quartz pipe, so high in silica, low in aluminum, low in potassium. In orange is that quartz granite that is again high in silica, but a bit more potassium this time. And when we look at the fresher granites and the blue here, and at the top it's a bit hard to see, high in iron are some of the formations that were at the top of the hole, but also those bone clusters that correspond to sediments and the micaceous granite. Now, when we compare that to the high-logger data, we see quite well in the tail that we have high quartz representing that quartz type. We have also that green zone that wasn't shown in the log, that calcium-rich zone is reflected by a high proportion of kaolin. High-logger data also is quite good at distinguishing the composition of the chlorides, and we can clearly see the distinction with these sediments that are much more magnesium-rich compared to those from the granites that are more iron-rich, amazite, except at the top where we have some clinochlore. And interestingly, when we look at 1480D, which is usually used to distinguish the sulfates, we found some of the sulfates shown here in brown. We also see the quartz pipe being very highly distinguished, as shown with the arrows. And the reason for that is because spectral signature of those quartz pipe basically represents water. It's a water signature. And what we found is that they correspond to trails of fluid inclusions. That's basically what we're seeing. So it's very easy to actually identify those quartz pipe with the hydrograph data. So here I'm showing the mineralizer data for selected elements. The cross has a bulk geochemical data, and you can see there's some areas a little bit of a mismatch. But I want to identify a few zones, few quartz pipes. So we'll start with the top one at about 40 meters depth, which is a barren quartz pipe, but it does have high arsenic content reflected by the presence of arsenopyrite phenocrysts. Take a bit of time to load. And in that quartz pipe is surrounded by first a quartz quasant. So we have the quartz pipe on the right-hand side, and then just at the edge of that quartz pipe, more distal, we have the quartz quasant, and then the micaceous quasant. So you see that transition as you go towards the quartz pipe. The second quartz pipe is a mineralized quartz pipe at about 70 meters depth. It has high proportion of molybdenum and bismuth. The tungsten, however, is quite low. It hasn't been detected with mineralizer. But there is tungsten occurrences at the edge of it, about 5-6 meters away from that quartz pipe. Within the quartz pipe, we see some wolframite crystals, or larger wolframite crystals shown here in black. And we have also molybdenite on the left, and on the top right, we have the bismuth and bismuthinites shown here in reflected light. So that large quartz pipe has very high proportion of molybdenite, and when we look at it in micro-XRF, we see that molybdenite in blue are quite intimately associated with bismuthinites along the edge of the crystals. And then we have the quartz pipe. When we look at the quartz pipe and the cathodoluminescence, we see that there are several episodes of quartz generation. So it's not as simple as it seems. We look at the backscatter, it's blank. We look at the cathodoluminescence, we see some phenocrysts to the bottom left, and we see also some very bright CL fractures that are going up to the molybdenite crystal. Further away from that quartz pipe, that molybdenum-rich quartz pipe, we see a transition from micaceous quasant to more of a strongly weathered granite. But interestingly, we start seeing that disseminated wolframite, so the iron-rich tungstate within the granite. Again, same rock, this time identifying more the mica in that middle section, and more Keffelster-rich towards the right-hand side. And we also have a bit more iron-rich minerals in the iron side on the within the micaceous granites. And again, when we go about 150 meters depth, we see a similar pattern. We have elevated moly and bismuth at 150, and about 5-6 meters away, we have tungsten peak in the mineralizer data. And you can see the moly within a very, very tiny quartz pipe. And at the edge of it, we have wolframite disseminated within the granite. Again, the micro-XRF, but this time we see in the granite there's also occurrences of molybdenite and bismuth, all of them being associated together, like the micaceous quasant. In this part, we're getting more of that strongly altered granite. Just a picture of wolframite, and you'll notice here wolframite and the cathodoluminescence is quite black, but surrounding it is scheelite that is replacing the original wolframite at the later stage of the evolution crystal of wolframite. So my take-home messages today is at the camp scale, it's good to look at tungsten versus tin geographically to help proxy towards tungsten mineralization. At the deposit scale, looking at just this drill hole, it looks like the tungsten enrichment is mostly within the granite, 5-6 meters away from the quartz pipe. The moly and bismuth are correlated together, and the highest tungsten grades are designated. So thank you, and I'd like you to think about tungsten next time you look at your phone.
Thanks so much, Coralie. Don't run away too much. We've got questions. There are questions. Trevor Ellis is asking, I'm just going to sit down to read it. Have you done any work or come across scheelite or scheelite cobalt gold association or deposits associated with ultramafic intrusions?
So there's a bit of scheelite in this hole, but I haven't looked at the regional scale, and I guess that would be maybe a question for Courteney.
So Courteney will cover that in her talk. Trevor? Okay, are there any more questions in the room for Coralie before we let her go? All right, great, thank you. And next up, we will have Courteney Dhnaram, who is going to talk about intrusion-related tin, tungsten and gold mineral systems in North-East Queensland and their critical mineral potential. Sorry. Yep.
I mean, I'll try not to run a marathon, we'll see. Thanks, everyone. I hope you can hear me online. This is quite precariously positioned. So I'm very excited to be here today to speak to you on intrusion-related tin, tungsten and gold mineral systems in North-East Queensland. It's been a number of years since GSQ, thanks, I'm short. Since GSQ have really been working in North-East Queensland. I think the last work was in 2015 when we did a joint project with a bunch of people in the room here. So I'm really excited to be back here to talk to you about what we're doing. So it's a real simple talk today. It's about the project rationale, about the characterization work we're doing in North-East Queensland. For those who are unfamiliar, so probably only a few of you, about the reference collection project and what we're trying to do across Queensland to build up a physical and virtual sample selection. And also I'm going to talk about some of the work we've just started doing on tin tungsten mineral systems in Herberton. So really the rationale for this project was driven out of the New Economy Minerals Initiative, which was trying to characterise what deposit types in North-East Queensland have a high potential for critical minerals. So there were some no-brainers, which were obviously the tin and tungsten moly bismuth systems, which also have indium. Copper, lead, zinc and silver systems, which are almost part of the same tin system, which also have indium and germanium. And then I chucked in gold because it's my favourite thing, and silver potential. So some of the focus is on intrusion-related systems in the area, but really the aim is for us to get to all of the distinct mineral systems within North-East Queensland, because there's a lot of non-intrusion related deposits that have potential for critical minerals. So GSQ reference collection, I've been going on about this for a number of years, but really it's one of the fundamental projects that GSQ is running. We're really trying to build up a collection of geological information from our major deposits. It's simple. We really don't have the samples and materials across Queensland from the previously mined deposits and even some of the currently explored deposits for us to be able to say anything, with modern data about what these deposits are doing and what the broader systems are saying. So it's for publicly accessible samples and data sets for industry and researchers. And we're really trying to get representative samples from major deposits. Now, this really means ore from the deposits, but where we can, we'd like to get stepping out into the proximal and distal alteration halos. This is an example from Northwest Queensland, but really it shows what we're going to try to do in North-East Queensland. We're going to try and hit it hard and cover the whole region. In Northwest Queensland, we were able to get in 4 years over 30 kilometres of new drill core. This was complemented by 1,500 additional samples complementary to this drill core. We used pulps, crushings, lone drill core, ROM samples, pit samples, anything we could get our hands on to collect this new data. And really, this allowed us and all our collaborators in research then
to undertake more detailed studies across the region. The power of this is the virtual collection and the data sets that we're building from this drill core. Yes, it's great to have all of this drill core and these samples sitting in the core shed, but we want to be able to make all the information that we're learning accessible for everybody. In North-West Queensland, we're able to do almost 40 kilometres of non-destructive core scanning. This was a combination of mineralogical scanning from HiLogger, from core scan as well, and then we tried our hand at both TrueScan and Mineralizer to try and get some continuous XRF geochemistry, where we couldn't do geochemical sampling or just to have complementary data sets. We also did a fair bit of destructive data acquisition, so hopefully you guys don't have to do it as well. So we sampled in the IOCG, in the copper, over 1,000 samples for consistent multi-element geochemistry. So in GSQ, we put together a standard set of geochemical methods that we are trying to apply to all of the deposits, irrespective of what commodity and what part of Queensland, so we can do big comparisons on a Queensland-wide scale. And really the data collection is looking at tens to hundreds of meters of scale. So we're not going to do super detailed work on every little deposit, but we're trying to understand what deposits are like each other and what the bigger mineral system are doing. So what have we been doing for the last couple of years in North-East Queensland? Well, really the first year was building up our physical sample collection, the hardest part. We're trying to target main deposits in North-East Queensland, specifically in the tin and tungsten area, but also across the whole area. We've scanned over 7 kilometres of drill core via the HiLogger. And when you think about a lot of the historical drill holes and the depths, so some of them are 30, 50, 80 metres, that's a lot of drill holes scanned. One of the data sets I'm quite proud of is the mineralised data that we've been doing on a lot of the drill holes across the region. And we've scanned over 5 kilometres of this. And I'll talk about that more in the next slide. And we've done about 250 multi-element geochemical samples. So these have been on the major deposits, because as you start stepping into the smaller prospects and specifically into the Herberton region, which I'll talk about soon, it's quite hard to get the material needed to do this geochemical analysis. And these are the areas. Blue is tungsten molybismuth, green is tin, and yellow is gold. So these are just some examples of where we have this data set so far. So just talking about the mineralized data sets, we tried to focus on getting a spatial coverage. We didn't want to do any one deposit in too much detail, try to do 1 to 2 drill holes per deposit. The data that comes out of this is 1 centimetre or 10 centimetre bin data. And it provides really good key complementary data to these older drill holes where we may only have a few elements assayed. So anybody who's worked in North-East Queensland understands that a lot of the gold data sets, you're looking for gold, you just assayed for gold, maybe arsenic. If you're looking for copper, lead, zinc, well, that's what you're assayed for. So this is just providing a little bit of the whole rock geochemistry and some of the other elements. Now we are also following up with geochemistry, but not all samples, we have the material to do this. So why did we start at tin tungsten mineral systems? Well, it was almost serendipitous, and I'll talk about that in the next few slides. But we thought really this area is a nice way to sort of target a mineral systems approach. We're looking at the whole Herberton region, as you can see up there in green, essentially as one project. We're looking at the variations between the tin to the copper to the lead, zinc and silver parts of the system, trying to understand the spatial extents of the different mineral systems and their timing. Really, we're trying to drive new exploration in this region. There's a lot of untapped potential, and as I go through my slides, you'll realise that, and I didn't realise, that it's not just a tin province. A lot of these deposits have a lot of anecdotal data saying, oh, there's 7,000 ppm indium, and we know there's all this tungsten here, but they're comments in handwritten logs with not a lot of modern data to back it up. So we're trying to do systematic collection of all samples, to do TEMA and SEM work to identify the mineral phase that these elements are in and complementing this with geochemistry. And also many of these deposits within the tin fields have waste dumps and tailings with unknown potential. So you'll hear a bit about that tomorrow with the secondary prospectivity talks. But by looking at the work and reanalyzing samples from these old drill holes, it's also informing what's probably sitting there and wasn't mined in the waste dumps. So we're really lucky in Herberton. There's been some really, really good work. So this is an overlay of the work from the 1970s from Blake, and the purple is just the permocarb intrusive rocks that I have put in purple. A lot of the work's been done for us. A lot of these systems, we know where the tin-rich areas are. We know where things step out into the lead, into the zinc areas. And also some of the work, and this is a bit hard to see, but essentially it's a similar updated map from JCU that was put out in 2015. And what it did was it's highlighted the main areas of the main commodities. So in here, let's see, here you're saying it's tin, here you're saying it's tin, down here you're saying it's base metal. So it's a very good place to start, but it's quite simplistic because what I've learned is that it's not just tin or just copper or just tungsten. So we started with detailed deposit studies. We tried to get more recent drilling from these deposits where we could get a sizable amount of drill core, HQ drill core, and complementary geochemistry. So we started at polymetallic deposits and we started at tungsten, moly, bismuth. But you're saying, well, where's the tin? Well, unfortunately, there hasn't been a lot of modern exploration in the Herberton region. But luckily enough, we stumbled across a rescue mission to get over 170 drill holes from the Herberton region. We managed to get a lot of the old historical drill core, AQ and BQ, that's was kept safe for 50 years from all of these places and all of the data and records to go with it. So this provided us with samples from all of the major camps and the whole region. Of course, when you look at it, it's small and it's tiny and it's old. So you have to really question what sort of work can I do on this that's complementary and can help explorers. And one of the really interesting things was, as we were pulling this data together, I was pulling out all these tin holes, we were doing a big retraying program, is that there was so much copper in them. And then I started to dig a little bit deeper. And as I alluded to before, nearly all of the tin holes were not tin, they were tin and copper at least. And you can see by the grades down there, there was a ton of silver floating around as well. So some of the work we've been doing from that drill hole is that we can actually high log it. So yes, it's quite narrow drill core, but we've been able to scan everything. So this is a key data set that we'll have from all of the region. One of the really neat things that you can see is that up in here, and it's kind of really pale, these are base metal holes. So these are holes that are copper and copper zinc predominantly with a little bit of lead floating around. But when you high log them, you can actually see here, you've got some topaz floating around. And in here, you've got a little bit of topaz here, and it's pulling out all that tin. So it's not necessarily visible cassiterite, but in these areas, they've actually have early tin mineralization. One of the really fun things that I've been doing also is going through the old GSQ historical sample collection. So actually, these are samples from 1910 to 1960 that we've had sitting in our collection. And a lot of these were taken in situ and from underground. So I've been able to complement some of these drill holes with ravaging the collection and taking small pieces. Now, obviously you can't do multi-element geochemistry without destroying all of it. So one of our approaches is to do some SEM and TEMA work and then possibly do some electron microprobe to better identify what these sulfide phases are and then fit that into the bigger story. Oh, this was a nice segue. So one of the things that we've been doing, and you'll hear a little bit more of this in Avish's presentation tomorrow from JCU, is we've been starting to do TEMA work and microprobe studies. Because one of the questions we had from a lot of the literature was like, there's indium everywhere. It's a massive indium province. And you see these numbers with no analytical methods associated of like thousands of ppm, and you're like, well, that's pretty good. So we went, had a look at all the deposits that had all the sphalerite in them, and actually they weren't always high indium. And what we found from here is that it seems to be the indium is in sphalerite, yes, predominantly in stannite. So in these tin systems, you have early tin and then you have copper either coming in near or just after, and you're forming stannite, which is a copper tin sulfide or a zinc tin sulfide. And this is actually where the indium is sitting. Now, that's not what everybody wants to hear because it's not always so easy to get it out, but this is also possibly where it's sitting in the waste dumps and in the tailings. And it's been really nice because the historical indium assays we've had actually have matched directly where we've had sphalerite, but mostly where we've had stannite. And one thing we've noticed in some of the deposits is when you get high copper, so you're talking about 5%, 10%, which is actually more common than one would think, you're getting 800 ppm, 900 ppm indium, which is really, really nice grades. And just to finish up, some of the work we're starting to do is isotopic fingerprinting. So I wanted to say geochronology, but Elena, my colleague, is telling me that there's much more that we can do with this. Because we can't do lots of geochemistry because we don't have all the material, we're trying to be smarter about what we can do from these smaller samples. So we're looking to do a multi-mineral
and multi-method approach to try and constrain these mineralizing events. It's really important to understand when the copper came in, the tin came in, the copper came in, the lead zinc came in, because this will affect where and what critical minerals you have. So we're looking at dating alteration minerals. So with our collaborators at UQ, we're looking to get into garnet and calcite and fluorite dating. This is really keen because there's fluorite often associated with tin, but often, 2 to 3 more events that happen between the copper and the lead zinc. Directly dating all minerals, and you'll hear some more work about this tomorrow with Avish from JCU, and something we're looking to get more into. Isotope signatures of all minerals, trying to see what this data can tell us. We haven't started doing this, but I think it's quite important to see, chuck everything out these samples and see if we can start to work out how to vector. And a complementary data set we're collecting as well is looking at mineral chemistry on these same garnets and these sphalerite as well, to see if also we can find a way to vector. And this is really important, like I said, to understand the timing of the copper and base metal mineralization, which is really important for what indium's doing in the system. So in conclusion, really, I'm just here to sell the idea of trying to get rocks and drill core from everybody. It's so important for us to get physical samples from all of these deposits. Yes, most of our work so far has been in tin tungsten, but we're moving into base metals and gold. And it really doesn't happen without the support of you guys. So happy to have I'll chase you, you can chase me, it's easy. But really this allows us to then facilitate more research with our collaborators to go and try and answer some of the questions you guys might have in exploration. And really the focus is to collect modern data sets over this historically mined region. Everybody knows about Kidston, everybody knows about Maitland, everybody knows what they look like here, but we don't actually have modern, consistent geochemistry over these gold deposits. Same with Herberton. We'll be lucky to have another element that's just not tin assayed at the same time. So it's built up from these older samples and older data, and we don't think much will change, but hopefully we can find out a little bit more about the critical mineral potential that can help companies explore for it. Thank you so much.
Thanks, Courtney. All right, do we have any questions? I know we've got one online. I'm just going to check in the room first. Andrew.
Hi there, Andrew Summers, SciAps. I'm just interested in the process for accessing the samples. I mean, are they being stored in Brisbane is the main?
So predominantly most of our samples and mineral drill holes are in Mount Isa. We bring them down to Brisbane as we do our high logging, that's where our machine is and that sort of stuff, but they're predominantly based up in Mount Isa. And then our physical samples, so we might have specimens and everything else that sits at in Brisbane. So just you can have a chat. All the drill holes and everything are on our online data portal, so you can see what we have. And we're working on getting our sample sets up there as well.
And to physically access them, what's the process?
Contact the Exploration Data Centre, and then they can put you in contact with the right people to depending what you're chasing. So
thank you.
Yep. I just make a comment. Some of them have been flagged for obviously non-destructive work as well, because we're just trying to preserve what we can.
Thanks, Andrew. Okay, we've got a couple of questions online and comments. John Menzies would like to know who was responsible for saving all of that important core across the whole Herberton camp.
It was us, myself, and Frederick, actually, Frederick von Klinski. Yeah, went up there, lots of trucks, lots of pallets, and about 18 months of retraining all of these drill holes one by one, remarking them up from feed and putting them together and matching them up. So it's actually, I was really grateful for all of the companies who knew how important this was to preserve somewhere. But when we heard they were going to get thrown out, we jumped because no one has drilled since those holes were drilled. So it's so important. And they'll all be publicly accessible. They're all getting put in the system now. So.
Okay. Yeah, I'm just moving to the chat. Trevor Ellis says we need to get some core from Chinova. Is he still at Chinova?
I just got some from you guys, but I'll take more if
New
you'd like
Hope,
to offer it.
near Mount Cobalt, and he wants to talk later. Gold, cobalt, tungsten.
Oh, so yeah, so just on his question that he mentioned before to Coralie, we have looked at the tungsten moly bismuth. And one thing we noticed that there wasn't gold previously assayed. So there definitely is gold associated with this system. It's not a ton of it, obviously, because it's not what they're mining. But that's been really interesting for us to see sort of like gold and a little bit of bismuth in these systems. but we wonder not just necessarily with the tungsten and moly. So
fantastic. Okay, and then we've got another question at the back.
I was really hoping for no questions, to be honest, but this is, I was trying to keep the time. So that's fine.
I know, it's good. Hold
Also,
on.
find me in the breaks. I'd love to talk. Hey, Greg.
Hi, Courtney. Historically, the government would pay for the shipping of core from railheads to the storage areas, and that was a great incentive for people with core to actually give it to the government rather than leave it in a pile in the bush. Is there any idea of having some kind of scheme like that that would make it easier for people to give you the core they have?
Yeah, that's a really good question. So currently with the work we've done in Northwest, that was an agreement with all the companies. So actually everything that we got recently, we have paid, we've facilitated transport. Often we've gone up there ourselves and like pallets and got them on trucks. So yeah, definitely that is cool. And paying is, you know, it's a no-brainer because we really want it. And we understand that sometimes, you know, not all companies can, or it's not a priority. So we're happy to step in and organize the transport and pay for it as well. So.
Okay. I can't see online now, so I'm not sure if
run.
there's more, but I think we'll leave it there. Thanks, Courtney. And move on to Heather Sparks, who, for those of you who don't know her, she's our new manager for the Collaborative Exploration Initiative grants and also manager of the engagement team. So she's been with us about 6 months now, and she's going to give us an update on CEI.
Okay, which one don't I push?
Alrighty, good morning, everyone. I'm Heather Sparks. I'm the Grants and Engagement Manager at the Geological Survey of Queensland. And today I'm going to give you an update on our Collaborative Exploration Initiative. Alrighty, so just a little bit of a background on what the department's grant program has been over time. So in 2007, we started with the Collaborative Drilling Program. And this program was really just for drilling only. And we realized that that was somewhat limiting. So in 2017, we shifted to include other forms of exploration techniques. So things like geophysics, geochem analysis, the reanalysis of historical samples, and machine learning. And we coined it the Collaborative Exploration Initiative, or CEI. So far, we've had 17 rounds collectively with more than 900 applications submitted. And to date, 252 successful applications across the state have received funding. So rounds now run from February through to December, with round 6 currently underway. What makes Queensland different from many of the other states' grants program is that ours is not required for co-funding. So this means companies do not have to match funds that they receive from the CEI program. And we think this really makes us sort of different, and we're quite proud of that. Grants have been up to a maximum of $200,000 each. And with data becoming publicly available on the department's open data portal within 6 months of the program's completion date. So just to give you a rundown on round 5, this program ran from July 2021 to June 2022, so it has just been completed. We had 98 applications submitted, and of those, we have funded 18. The activities covered in round 5 range from 7 drilling programs, 6 geophysical programs, 4 geochemical programs, and 1 machine learning project, which I'm really excited to say you'll be hearing from later this afternoon. So please make sure you stick around to hear their wonderful success story. Round 6 is active now. It started in February and will run through until December of this year. We had 58 applications submitted, and we're supporting 16 projects. The activities in this round range from 7 geophysical projects, 6 drilling projects, and 3 geochemical projects. So what's happening in Queensland and who is doing the exploration? Here is a really great image. I just love this image, and thanks to Roger in the audience for putting this together for me. I really appreciate it. This is a really neat snapshot. We just updated it last year, and it captures what's happening, and that is that the junior companies are doing the majority of the exploration in Queensland. So we have just over 80% of the EPMs are held by junior companies, with less than 10% of the EPMs held by either mid-tier or major companies. I mean, this distribution of tenure by market capital is just awash with purple. I mean, a lot of the ground that is being explored is being done by companies that don't have a lot of money. And this is why I just love the CEI program. It's because it's a way for the government to help these companies financially. And I mean, Queensland is a state that is rich in resources wealth and has a fair spread of known critical minerals. The Northwest, if we've been hearing today, is well known for its copper, lead, zinc, and silver. And the East, which we've been talking about as well, is well endowed in gold and tin and tungsten. Queensland leads Australia for bauxite production, while the Julia Creek region is home to a world-class vanadium field. Mineral discoveries is a high-risk activity in financial terms and is being exacerbated by the global challenges of needing to look deeper and in more difficult terrains than in time past. This is a really cool snapshot of some activity in Queensland from 2016 to present. The blue indicates the granted EPMs and the orange are EPMs in application. So as you can see, sort of previously, it's quite flatlined. The number has remained pretty much constant. We see this really neat dip here, and this is a direct reflection of the effects of COVID and people either having the inability to get staff or get boots on ground. But the impact of COVID is short-term only, and spending and activities are recovering, and the outlook is very positive for Queensland. And you can see this really steep upward jump. This is in the last quarter from 2021, and it's massive. It's just an absolutely massive spike. I mean, exploration is at an all-time high. And this is where the Queensland government wants to help. Currently, Queensland has 1,842 issued exploration permits, with 675 companies holding these permits and 614 companies having submitted applications, with the largest holder being Rio Tinto. This is another really cool plot. It shows the historical demand for copper and the forecast demand through until 2050. The demand for copper for the 25 years between 2017 and 2042 is predicted to exceed all the copper that has ever been mined throughout the entire human history. And these are trends also we see for other commodities, in particular those metals that are essential for the electrification and the energy transition. And one of the many ways we're helping explorers look for these critical minerals is through our CEI program. And I am thrilled to announce, as you heard earlier, the minister last week has given us an additional $17.5 million to our CEI program over the next 4 years. This means that from round 7 through to round 10, we will be supporting each round with $5 million. So typically the last few rounds, we only had $2.5 million. Now we're up to $5 million. I mean, this is just great. The global demand of the population growth and energy transition means that exploration into these higher risk, higher cost frontiers is being supported to help meet the demands for these essential critical minerals. So how do you get your hands on one of these CEIs? Well, first of all, you need to be eligible to apply. And this means you must meet a number of criteria. You have to have granted tenure. You have to be in compliance with all of your tenure held by the company or related entities and under all relevant or applicable legislations. You need to remain in compliance for the duration of your CEI. You need to have landholders' approval and be able to provide evidence of this, if applicable, with your application. And you'll need to supply the core and or rock chips to the department that were part of your CEI. And priority is given to programs focused on critical minerals. Now, this is only a select few of the mandatory requirements, so please refer to the guideline for the complete list. But building the critical mineral potential for Queensland and our understanding of what we can make for our future needs to decarbonize is key to the CEI program. Want to stay up to date? What's the best way? Join our mailing list. Just email GSQ at resources, ask to join our mailing list. I mean, this is a really exciting time to be exploring in Queensland, and the government is really thrilled to be supporting it. Thank you.
Okay, any questions for Sparky on CEI, how to apply, when the next round opens, whatever's going on, current round? You'll get all those questions in a few months' time.
We will.
I think. All right, I'll just double check online. No questions there.
I'll be here the rest of today and tomorrow, so come and find me, ask me anything you want. Happy to chat.
There's a comment in the chat. Hold on. So Trevor has commented, I think, and that was in relation to the slide you put up about the distribution of juniors, mid-tiers and majors.
Yep.
In terms of EPMs, saying we've got that dominance of juniors in terms of EPM holders,
Yep.
but not, he says it's not dominance in terms of this one, those spending the money. So I think we don't actually have those figures in a presentation, but yeah, that would be an interesting comparison as well.
Heather, just wanted to ask, this is kind of a Dorothy Dixer a little bit, but for companies that want to apply, what's your advice to them? What sort of project is the one what sort of projects are the ones that the government really wants to support?
Yep, absolutely. Really great question. So like I said before, priority is being given to those explorers looking for those critical minerals. So that's a big tick. Make sure that you meet all of the mandatory requirements to be eligible to apply, because if you're missing one of those, you get knocked out right away. So they're clearly identified in the guidelines. So for example, you must already be holding tenure to apply. If you don't, hurry up. As you can see, the Minerals Hub is just getting in all these applications now. So if you don't have tenure, get your applications in now. Time is of the essence. And I think that we have a panel that assess all of the applications when they come in. It's a long, lengthy process, but we're looking for well thought out projects. We're looking for things where the results, whether they be a success or not a success, still the results will benefit the state and all of Queensland. And again, yeah, we're really looking for those who are interested in exploring for those critical minerals as we move towards a future of decarbonization.
All right. Thanks, Heather.
Thank you.
Now, I think we are breaking for lunch right on time. We're even 2 minutes early. Evan's happy, so that means I'm happy. Lunch will be out in the foyer, and we will reconvene at 1:10 to hear from some industry legends. All right. Thanks, everybody. All right. Thanks everyone for coming back. And now we're moving into our afternoon session where Rick Valenta and a cast of thousands, including Paul Gow, Katerina Savanova, Karen Connors, Nathan Fox, and Jenna McGovern are going to take us through the astounding amount of work that they've done over the last couple of years on the New Economy Minerals compilation, which is a pretty fabulous prospectivity tool that they've developed. So I'm going to hand over to you, Rick. Thanks.
All right. Thanks very much, Helen. And don't worry, Karen and Jenna. Just because I'm only expecting you to do 3/4 of the presentation. Oh, didn't I mention that? No, sorry. Yeah, so I've just listed everybody here who's been involved in these compilations. And I know it's the first. It's a workshop, so it's a workshop that's going to involve a mixture of talking and some feedback. There are a whole pile of different data sets that are available on the GSQ Open Data Portal, but I'm not going to expect everybody to load up those data sets and play with them today because it's not really practical. But what I'm going to do is sort of try to do a live exercise with the audience where we re-rank some of the criteria that I used for rare earths and redo the prospectivity for an area of North-East Queensland on the basis of your perception of the importance, applicability, and confidence of data sets rather than mine. Yeah, and so certainly want to acknowledge right at the start the support and funding of the Queensland Government New Economy Minerals Initiative, and there's been a lot of scientific input from a lot of people in this room actually for this, not only Geological Survey of Queensland, but Coralie, if you're here, we used your data set as well, though we didn't actually release it because it wasn't ours to release. And yeah, a whole range of different data sets and input went into this compilation. But before we get into that, and before you can settle in for a nice postprandial nap, I wanted to go to Mentimeter and just, I'm going to get that out of the way. So if you've got a smartphone handy and the tungsten isn't wobbling, if you can either follow that QR code, if you just, hopefully it'll work from the back, or go to menti.com and put in the code that you can see there, 46357977, and that will hopefully, if I can find it and start the presentation. Oh, look, we've already got people putting things in. So we're just going to take a couple of minutes and get people to put in their things that interest them about new economy minerals. Not well understood yet, defining them. I think I saw a talk from David Houston where he said, new economy minerals don't actually have very many minerals. It's mostly metals, but also some things like rubber and various other strange things. Advancements, energy transition, that's shown up a few times. Exploration is the big one. Future, sustainability, discovery, all good. What is critical? Yep, there's a lot of good definitions of that. Supporting new technology. The answers are coming fast and furious. So I'm probably not going to spend a whole lot of time. Well, actually, I can see that I've gone 30 seconds here. I'll go, oh, I've got 31 answers. It's got nothing to do with seconds. That's great. Thank you very much. I'm going to move on to the next one now. So stay on your phones. But exploration is the number one, which is great, because one of the things that I've noticed about new economy minerals is that there's, yes, there's a lot of exploration for copper, but there isn't a huge amount of exploration for some of the other ones. And I think that's a trend that's going to change in the future as the focus on critical minerals, new economy minerals increases. So now I want you to look at all these different metal groups and rate them as to which ones, I'm interested to know which ones people are interested in. So you should be able to drag a slider across to, I'm a bit worried that, oh yeah, there we go, we're getting some. I was a bit worried that maybe it wasn't working because we weren't getting any feedback, but I'm just interested to know what metals people are interested in. They just happen to be the ones that we worked on in the compilation, coincidentally. What's that?
Just the first two, because no one's got that.
Yeah, the comment there for the people online was only the first two because nobody's gotten further down yet. So I'll wait, give you another 30 seconds on that. So quite a lot of interest in rare earth elements, which is very interesting because my perception is there aren't a lot of explorers for rare earth elements out there. Who's exploring for rare earth elements in the audience? I'll take indirectly. Not you, Stuart. Okay. Good. Now, I'm going to change tack a little bit and move on to think about something else, which is, given that we're exploring for all these new economy minerals, how do we do it? So how do you, imagine that you're exploring for one of those things. How do you approach ground selection for any of these commodities? Is it process-based targeting, which is what I'm going to talk about today? Acknowledging very much that as you get down to property scale, you very much have to rely on exploration data sets rather than process models. But I'm talking about regional exploration ground selection. I'm going to give people another minute on this one because I think this is a really important one. Yeah. And isn't it, oh, great, that's good. I was going to say, isn't it great that the theme of the next hour and a half is the one that people are the least interested in? But yeah, we'll hear about data mining and clearances for tomorrow it'll be the North-East Queensland Deposit Atlas, and we'll hear from Michael later about some machine learning. So we're covering all the bases today. But good. All right. Well, are those results a surprise to anyone? I don't find them too surprising. I think we still are in a situation where people don't tend to use process models with a few exceptions, obviously, for area selection. They'll do some sort of combination of looking at what's been done, what's been found, existing occurrences, and also using knowledge about deposits. What I'm thinking of there is such and such a deposit has these characteristics, and I'm going to therefore come up with a shopping list for exactly the same characteristics somewhere else. And I think the distinction between the one on the far right and the one on the far left is that with the one on the far right, you're always fighting the last war. You're choosing a set of characteristics and focused on those characteristics. But the one on the left, process-based targeting, allows you to divorce yourself from the last set of characteristics, which may be related to a particular set of circumstances, and going back to processes where part of that process may be different and therefore produce a different expression. And the classic example of that is the fantastically strong pyrite halo around Mount Isa and the almost absent pyrite halo around Century. I could be wrong about that. I haven't worked as much on Century, but my understanding is that it didn't have as great a pyrite halo. Okay, so I'm going to go back to, we'll leave that and we'll come back to Mentimeter again later. And I'll come back to the presentation if I can find it. Right. So, in fact, I don't even think I have to talk about this. People have already mentioned that I think it's becoming common knowledge that there's a whole pile of commodities out there that really are our only hope to achieve the decarbonization we need to enter into in the next 30 years. There's no plan C. It's either hydrocarbons or what we're all about in this room. And I guess the other, the other part of the rationale for this project was there's a whole range of non-competitive data sets out there focused on the things that we've spent a lot of time looking for, like gold, copper, lead, zinc, coal, so on. But we don't have the same sort of information for some new economy minerals. So the aim was to produce and analyze a set of products to focus on those minerals. And I'm going to go through all these. There's a whole pile of outputs that I'm going to go through in the presentation, ending in an industry workshop, which I'm going to call this. And so I'm not going to list them now. You'll see them as I talk. Queensland does have. I'm going to start by talking about rare earths, but then we're going to have a series of cameos from other people in the group talking about the range of different commodities that we worked on as part of this compilation. So what we're looking at here is a log plot of mineral resource and total rare earth plus yttrium for Queensland. And what we can see is that there's some very, there's some very big deposits where that's this line here. See my, yeah, this line here is 1 million tons of total rare earth oxides, a Bio-Nobo sitting out here somewhere. But there are some high grade and large deposits like Mary Kathleen Tailings, Milo, even though it's relatively low grade, Peak Range. And this is a total estimate of what it, and could be a great underestimate of what its size is, and a number of other deposits. So Queensland does have a rare earth endowment, despite the fact we spent very little effort looking for them. And the approach I'm going to talk about today has been completely lifted from Geoscience Australia. And I guess other groups, and I know you won't be able to read any of this here. I think we'll be making PDFs of these presentations available later, so you'll be able to have a look at some of these papers. But it's basically the mineral systems concept that in its modern form started with a paper by Leslie Wyborn and co-authors in the mid 90s, where they basically developed this approach where you have a series of spatial criteria that are linked to the source for metal-bearing fluids and metals, the drivers for I guess creating the circulation systems of those fluids, the pathways through which they travel, and the gradients that cause those metals to drop back out of the fluids. And of course, this diagram is taken from Chris Lawley's paper on nickel in Canada. The fourth dimension of that, which Geoff mentioned before, of course, is time as well, because none of these things are a steady state. Things go along and then something bangs into something else and the metals drop out. So there's a third dimension, or there's a fourth dimension as well. And anybody who ever wondered whether expenditure on this sort of thing was justified need only look at, and I saw a great talk by Dave Houston showing GA's analysis of this, need only look at Julimar as an example of the sort of deposit that was originally highlighted, as far as I understand, by a continent scale nickel copper platinoid analysis of prospectivity that has paid for all of the mineral systems, all the mineral systems prospectivity analyses till the end of time, basically. It'll always be a good proposition from an expenditure point of view, just based on that single episode alone. But there are a number of other examples of greenfields discoveries driven by this sort of system thinking. So basically, and luckily for you, I'm not going to actually expect you to read all of these all these different things, but for rare earth elements, there are a whole range of different deposit types that we considered. And again, for each one of those deposit types, we defined what a source for the metals and fluids might be, what what the driver might be, what the architecture might be that's allowing the flow of those fluids, and what the trap or gradient might be to focus those. So a series of the whole part of this approach is to identify and define mappable criteria that you can use to try to prioritize areas that have high potential for this style of mineralization. And once you define those mappable criteria, then the next step, and the one that I'm going to try to get us to go through as a group later on, is to decide whether these criteria are any good. Because you can come up with a wild, whatever sort of wild criteria you want to. And for any given data set, you've got to then say, okay, well, how important is this data set? How important is this criterion? So if you've got, for example, if you're looking for an Ernest Henry type IOCG deposit, and you look at a spatial correlation and say, well, it's spatially and temporally associated with the Williams suite of intrusives in the Mount Isa region. What's the importance of that to the whole system? Is it absolutely essential? Is it a nice to have? Or is it a don't bother looking if it's not there? So could we get by without it? So that's kind of the importance. It's not thinking about the data set, it's thinking about the criterion that you've developed from a theoretical point of view. And then the next step in that is to say, well, I've chosen a data set. How applicable is it? So for example, I've got a data set of GSQ mapping for a given area, and it shows the distribution of the Williams granite. How good is that? How good is that data set? Is there a good connection between the mappable data and the actual process I'm trying to map, or is it only okay? Is it really obvious and clear, and you could explain it to a 5-year-old, or do you need to sit down? Do you need to sit down over a few cups of coffee or several beers in order to get the concept across to someone? And then finally, are you confident in that data? So is it data that is definitive? Like, is it very good, modern, low detection limit geochemistry that you would say, well, if there's no expression in this geochemical data set, I think it's probably pretty definitive? Or is it a data set from 40 years ago or something where they've only analyzed for a couple of elements with a high detection limit and so therefore could easily be giving false negative? Another classic example is from geophysics. It's an IP anomaly. Well, how much confidence do I have that the IP anomaly is directly related to mineralization? It's a good start, but there's a lot of false negatives associated with it. So each data set that we analyze by this method, we basically rate its importance and then say, okay, how applicable is, how important is this data set? And we give it a rating from 0 to 1. And then we say, how applicable is this data set to the concept? Sorry, I'll go back. How important is this criterion? How important is this process? And then how applicable is the data set to map this process? And then how much confidence do we have in that data set? Multiply those three together, and then you get a modifier to that particular data set that you can then apply to your analysis. And obviously a data set that you're very confident in is going to rank more highly than one that's a little bit dodgy. So here's an example of that process for IOCG deposits, where for rare earth bearing IOCG deposits. And again, I'm not going to go through all the details behind this, where we've identified a series of, I guess, lithological and geochemical indications of drivers. And in this case, one of the key ones was the presence of Williams H granites, of sources, which would obviously be rare earth bearing intrusives, and rare earth bearing post rocks is something, units from which rare earth elements could potentially be stripped. Pathways which are shallower and deeper structures and depositional gradients, which in this case, there's a little bit of argument about, because the ones I'm showing here are a mixture of geochemical indicators of the presence of those gradients and lithological indicators of the presence of those gradients. So like a redox front is more of a process related one, whereas these little maps here that you can see are actually showing anomalous geochemistry. So, and you know, some people actually separate those. And they're all related back to this, to a process model. And again, I won't go through all this. If you go to the if you go to the actual download on the GSQ Open Data Portal, there's quite a detailed description of the model that's gone into I guess the background of this. And in this case, it's really adapted from you know, a couple of sources. I didn't invent this out of thin air. Roger Skiro's work and co-authors has been important, and also Travis Murphy and Mark Hinman and company working on in more detail. And you know, so what we ended up with was, in the case of IOCGs, an overall prospectivity model, and you know, not surprisingly, the outcropping area of the Mount Isa region had some pretty high values. One thing I would say is that we did a separate analysis for covered and exposed areas, because of course the data sets you can use are very different in that area, and then a series of areas of interest coming out of that, modified on the basis of areas that you know, we didn't obviously highlight areas where there was already a lot of known mineralization. So that gives you a bit of an introduction to the sort of analysis that we've done. But what I wanted to do now was just go through, or actually with others, go through some of the other commodities that we covered as part of this process, starting with cobalt. So Paul, if you, where's the mic gone? Yeah. Rather than switching mics back and forth, what I thought I would do is just I'll run the presentation and let the various people just use the handheld mic. So.
Okay, thanks very much, Rick. So cobalt was one of the, I guess, critical metals that we looked at, and it's potentially one of the, I guess the best known in terms of, if we questioned this room, I think cobalt is probably one element that people would know a lot about, the deposit styles, where it occurs, etc., as opposed to, for example, gallium, germanium, or indium. So next slide, thanks, Rick. So just a couple of slides. The thing about cobalt is that when you look at production and resources, it's very heavily skewed towards being a byproduct of copper and nickel. So you'll see up on the right-hand side there, that's a pie chart showing that essentially the sediment-hosted copper cobalt deposits comprise about, I think it's about 60% of 2011 production. And then in black is nickel cobalt laterites, and then in red is the magmatic nickel copper deposits. And you'll see on that plot also the grades. See that bar chart on the right? So the magmatic nickel copper PGE is typically a lower grade in cobalt, and then you move up to the nickel cobalt laterites, and then the African copper belt is where you're getting your high grade cobalt in your deposits. Now, one really interesting thing to note is that that top pie chart is about mineral deposits that are found in a terrestrial environment. Down the bottom here, you'll see that those two yellowy colors, which comprise about 75 to 80% of the global resources interpreted of cobalt, are actually seafloor deposits. So that what we're seeing on the terrestrial setting is only about 20% of what's interpreted as global cobalt. Up on the left, this is just to show, it's a plot from the EU's list of critical minerals, and across the bottom is economic importance, and then the vertical is supply risk, the vertical axis. And so that's where cobalt plots. And I've just plotted a couple of yellow circles there as well that are some of the other elements that we've been talking about today. And as noted earlier, I think this also does include coking coal and rubber are actually classified by the EU as critical minerals. So they're the three big deposit styles, and there's a list down there on the bottom left that where cobalt is found in a bunch of other deposits. So cobalt deposits are not really well defined. And there's a bunch of different schemes for how you might classify them in terms of deposit model. Yes, thanks, Rick. So what we did is, this is a similar plot, I guess, to what you saw that Rick was showing for the rare earths. So that in this, we've put together, we looked at a bunch of different deposit types, but what we've done is put together all of the mappable criteria. So this is just a very generic cobalt prospectivity plot. And what's interesting, Rick was talking about the process models and how they might take you forward rather than be backward looking. And that's the sort of thing we see down on the left is metasedimentary copper, cobalt, gold deposits. And whilst we might all look around North-West Queensland and North-East Queensland, there's actually down in the southeast or the central Queensland, there's a whole bunch of areas that maybe we haven't considered for cobalt prospectivity, but maybe they're the sorts of places we should be looking for different types of deposits. I think that might be it for cobalt, Rick.
Okay.
Next one.
Scandium, and that's going to be Katerina Sabanova, who's on the line. Can you hear us, Katerina?
I can, yes. I cannot turn on my video, so you just get my voice.
Just turning you down a bit. You're really, really loud.
All right. I will talk quieter.
No, that's fine. No, I can turn you down. It's good.
So, appropriate volume now?
Yep.
Oh, thanks. Yeah, so I guess you will progress through the slides. So thanks for hosting me. And in the interest of time, I guess I'll just jump right into it. Next slide, please. So the main one, yeah. So scandium is used as a doping agent to increase the integrity, lightness, and tensile strengths of aluminum and scandium alloys that are common in the automotive and aerospace industries. And it is also an important component for extending the life cycle of solid oxide fuel cells. It is not commonly found in large concentrations, and it does not often form ore deposits. So as such, it is typically recovered as a byproduct, and in fact, as part of rare earth and uranium mining. So clinopyroxene is the main scandium ore mineral. However, to date, scandium has been very difficult to extract efficiently from intrusive igneous complexes that are particularly rich in these ferromagnesian rock form minerals such as clinopyroxene and amphibole. So this proportion of the scandium resource is shown in the pie chart in blue. So as such, approximately 90% of the global scandium supply, which adds up to about 15 to 20 tons a year, is seen here in orange, and it is currently recovered as a byproduct from the azurine and badellite rich tailings from Bayan Obo in China. Next slide, please, Rick. So as I've indirectly alluded, globally, there are 3 key mineral deposit types that have been documented to host scandium mineralization. Scandium can be concentrated to form magmatic supergene ore deposits on top of the mafic, ultramafic intrusive complexes and hydrothermal carbonatite related deposits. In general, scandium is a secondary metal, and it's typically hosted in clinopyroxene and amphibole dominated layered and zoned mafic to ultramafic intrusions related to subduction tectonic environment. Like I've mentioned, azurine and badellite rich carbonatite and alkaline intrusion related complexes. And lastly, weathering of the mafic to ultramafic complexes and carbonatites as well. So laterites is an important source of supergene scandium. And using a common process model approach that Rick and Paul have already outlined, as a result of our study, we identified several prospective target areas for each of the 3 deposit types. So in particular, Queensland with subtropical to tropical climate is considered a favorable location for supergene regolith hosted scandium-rich laterite deposits, and particularly when they're related with weathering of the mafic, ultramafic intrusions. That is it for me.
Thanks, Katerina. Okay, now on to tin tungsten.
That's me. So tin tungsten is probably 90% of the people in this room are probably tin tungsten experts up here in North-East Queensland. And really, I guess when you look at tin tungsten, one of the key criteria that I've chosen to highlight here is the fractionated felsic rocks, which with its associated. So one of the things that we did, and it really struck me when Dave Purdy was talking this morning, is that throughout the Tasmanides, there's been so much work done on the intrusive systems of the Tasmanides, but you look at what Dave was showing us this morning. There's still so much to be done, and so many places that still haven't been sampled, for example. So it's quite phenomenal. But there is quite a good record of felsic rocks that having been classified from Champion and Heinemann, from Ford, from Budd et al, and of course Siegel. Coralie, thanks for letting us use some of your data. So one of the key data sets in this was the fractionated felsic rock. So we put all of those data sets together and tried to then map out where those fractionated systems sit in North-East, or all of Queensland actually. And one of the other key data sets we used was on the left here are the stream sediment data sets, both from Geoscience NGSA data set and also the Cape York catchment data set from GSQ. And we basically went and looked at those element associations and built a tin index to try and use those stream sediment data sets for mapping out what might be areas or drainages prospective for tin and tungsten. Next one, thanks, Rick. So basically, this is just an example of some of the outcomes, and as you would imagine, the areas considered prospective are very much focused up in North-East Queensland, but also some down to the south on the border with New South Wales and along the eastern margin, and some in areas that sort of popped up out around Mount Isa, I guess, on the basis of the characteristics through that Proterozoic belt. So this is the sort of outputs we had from the tin tungsten with a lot of target areas up there in North-East Queensland. So that's it, I think, for tin.
Okay, back to Katerina.
Back to me, thank you. Let me just set up as well on my side. All right, so the main slide, please, Rick. All right, so the steadily growing demand in the development and use of renewable energy technologies, particularly solar power, is the driving force for the increase in exploration for silicon. And so, of course, silicon is used in solar panels, optical fibers, mobile phones, computer screens, flat screen monitors, and so on. It's also used as a semiconductor and can be used in transistors. So high transparency glass may comprise up to 97% of solar panels' weight. So that's how important silicon is. Interestingly, Australia is not currently considered to be a significant producer of silicon. And so in this pie chart, it is lumped with the rest of the world. And it's kind of peculiar because the largest silica sands mine in the world is located right here in Queensland at Cape Flattery. So another important point is that Australia is actually actively adopting renewable energy technologies, and so contributes about 2.5% to the global market share of solar panel installations, such as rooftops and solar farms. All of this means that we largely rely on the import of the already refined silicon and the import of the solar panels themselves. So all of that has implications, like the cost of the silicon metal production is currently quite high, and there is a degree of variation in the produced quality of the silicon metal. So working towards decreasing the cost of silicon metal production and increasing the quality of the product is ultimately important. Next slide, Rick, please. So most of the documented quartz resources in Queensland are of the silica sands type and are in the far north Queensland region, particularly Cape York Peninsula, and typically in association with quaternary sand dunes. And these will be sort of a dry mining and excavation type of deal operations, 10 to 50 meters below surface. And it is considered economically viable to mine silica sands and then add an additional step of agglomerating the grains during the purification process so that the final product is sort of large enough for use in solar panels. So something like 1 centimeter in diameter crystal or a wafer. So as part of our study, we highlighted 5 coastal areas prospective for silica sands, and that's on the left. And also in general, alaskites, pegmatites, and quartz veins are a great and important source of high purity quartz. However, these deposits have to be like physically big enough to be cost effective. So in these types of quartz deposit, quartz is extracted by chemical leaching, but you first have to beneficiate and isolate quartz from feldspar. So for that reason, alaskites that may contain up to like 75% quartz by composition and quartz-rich pegmatites are attractive. However, there's very little record of these type of quartz deposits. And in Queensland, there is a site called the Sugarbag Hill and the Lighthouse that I believe currently mining for quartz. And in terms of the mappable criteria, we ended up focusing on tin tungsten deposits that Paul just mentioned and pegmatite hosted lithium deposits as a guide. But here we want to make sure that these wouldn't come any metal enrichment. So we also used values from whole rock geochemical analysis, and particularly those that return greater than 80% silicon dioxide values. So to identify areas of silicic, sort of leucocratic and pegmatitic rocks outcropping at surface. And as a result, using these main criteria, we highlighted 6 target areas for the hydrothermal quartz deposits. Thank you.
Okay, thanks, Katerina. Polyrhenium, that's you, Nathan.
Okay, can you hear me okay? Yeah. So just a very brief overview of the molybdenum study. You can go to the next slide, Rick. Just in terms of the uses of molybdenum and rhenium, similar to some of the other critical metals, they're used in high strength and high temperature steels. So they're commonly used together. So in the aerospace industries. We've shown some of the resources that we do have in Queensland as a guide, and also the location. You can see we've kind of split these out into the North-West Mineral Province around Mount Isa. So they're kind of some of the most well-known high rhenium systems like Helen. But probably the largest resource in Queensland is the Julia Creek Vanadium District. So they're in the oil shale region. So you can see on the grey tonnage plot, looking up there, about 100,000 tonnes of molybdenum or more. But mainly the main hosts are porphyry systems, and also a few unusual types such as Grism-related systems, which Paul's already talked about, and uranium, moly, bismuth, unconformity deposits. So we do already have a range of known deposits, and the criteria that we've been working on have mainly focused on the North-West Mineral Province type, Merlin and Kalman type, porphyry copper, and the Julia Creek systems. So yeah, the next slide, please, Rick. So just as a kind of a guide, you can see some of the numbers there. You don't have to focus on them. I guess what I kind of wanted to highlight is that there are some gaps now. Our knowledge about rhenium in molybdenum largely comes from the geochronologists who use this as a geochronological indicator. We do have some gaps in our knowledge on rhenium in molybdenite. So actually, I think there's something there that we could actually fill in. If maybe people in the room already know that there's some gaps we can fill in there, then we could probably do that. But it's really interesting to have a look at some of the resources. You can see that we actually do have quite a lot of contained molybdenum already in Queensland, and we're actually going to build our exploration models around these typical models, so particularly porphyry copper and the polymetallic systems up in Northwest. So the next slide, please, Rick. Thank you. Just as a very quick summary, so these are the prospectivity maps based on the criteria that Rick's already sort of outlined, and obviously the details are in the report, so you can look at that. But you can see that obviously there's quite a lot of overlap between the Proterozoic regions between Mount Isa and the Georgetown area. There's potential that they're picking out some of the unconformity uranium type systems up in the Northwest, in the Northeast, and the Georgetown inlier. Oil shale vanadium is showing a lot more prospectivity than just around Julia Creek. So we're actually seeing quite a lot of prospectivity for those systems. There are unusual deposits from molybdenum, probably don't have any rhenium, but certainly worth following up on. And of course, we all know the porphyry systems on the eastern margin complex and often quite small, but potential to have quite high grade molybdenite as well. So yep, just a very brief summary there. Thanks.
Thanks, Nathan.
Thank you.
Actually, I'm going to see what this question is. There's a question from, you can probably see, well, you can't read that. What's the uranium content of the vanadium moly shale deposits? I know that 10 years ago they were uranium targets. Now they're vanadium targets. So there's a fair amount of. Oh, I'm not supposed to say that. I'm like, no. We can edit that out of the video later.
Indium, okay, and we'll hear a lot more about indium tomorrow in the talk. I think from Avish and Olivia are going to talk tomorrow about Belgammon, which is a very high Indian system, and we're also going to have a look at that in the North-East Queensland Mineral Deposit Atlas session. Next slide, thanks, Rick. Now, indium is really interesting because it's one of these things that's there, but nobody quite knows where or why. But the interesting fact is that 95% of the global indium basically comes out of smelters where they're processing zinc concentrates. Okay, so that whilst a lot of that production, so you'll see that down the bottom there, that the largest producing countries of refined indium are China, South Korea, Japan, Canada, and Belgium. But more than 95% of the global indium comes from the electrolytic zinc refining, but actually a lot of that material is probably being mined in Australia as well, and places like Peru where you're getting a lot of zinc production. So in terms of deposit styles, the common deposit styles are those that have zinc in them. So for example, zinc skarns, VMS, base metal epithermals, obviously your sediment hosted lead zinc deposits, also porphyries, granite related deposits, and to a very tiny extent, sediment hosted copper deposits. So that plot on the left there was some great work done by Werner et al. About 5 years ago, and you'll see that the top bar chart on the left is the sort of reported mineral resources, and you'll see most of them are from skarns and VMS, and there's a couple of enormous skarns in China that dominate that first bar. But then when you go and look, Werner actually then went and said, well, let's go and look at the places that don't have indium reported, but we know they're big zinc deposits and probably have indium. Then the next bar chart along, you see the sedimentary hosted lead zinc deposits really pop up then in terms of I'll use the word, well, Werner uses the word inferred resources, but it's not actually the JORC inferred, it's just interpreted, I guess, would be the word. Next one, thanks, Rick. So that's the indium deposit types, and this is to have a bit of a look at where they, I guess, have been reported in Queensland. And typically there are about two types of deposit styles for indium reported in Queensland: the VMS deposits, and you'll see those marked there. And then a couple further up north, which are the vein systems like Belgammon and Nightflower, etc. And there's the typical grades of indium from Werner's work, and you'll see that that really, I guess, porphyry and granite related have the highest grades. Average grades about 67 and 44 ppm. If you ignore the tailings and slag, but those other deposits like skarn and epithermal at about 36 ppm are not far behind. So it's so that's the sort of types of grade that you get for indium deposits. So that's probably about it. We'll hear more about indium tomorrow.
Okay, thanks, Paul. Now what I wanted to do was just give you a quick look at the sort of data that, and I like I said, I haven't sort of set up an exercise where everybody downloads the data and loads it up on their computer and has a play with it, because it's probably something where there's not enough time to do that and do it justice. So I really just wanted to show you the sort of thing that we put together, and I guess the just some of the basics of the data is that we've and this applies for all the different commodities, but again, I'm focusing on rare earths just because it's the one that I was most involved in working on. We're looking at a QGIS version of it here, but we essentially produced an ArcGIS, a map info, and a QGIS version of the data. And it basically runs the whole gamut from if we run down the list, I should have turned some of these things off, but I'll turn these off yeah, so if we, there's Queensland. So, we've got a series of occurrences of different types that are taken from the Queensland data set. We've done a compilation of soils, or taken data from whatever geochemical data sets we could find, essentially. And because when you're dealing with rare earths, of course, you're dealing with multiple commodities. We've ended up taking a percentile approach. So if you're greater than 90th percentile in something, then a value gets highlighted. So there's a whole lot of information there, but as I said, there's not the actual background data isn't in there because those data sets belong to other people, but we were given them to sort of process them and produce products from them. And one of the key outputs of that I used in other analyses was rock units, to take those point geochemical data sets and turn them into rock units that have greater than 90th percentile rare earths in them, of one or the other of the rare earths. And then also a 500-meter buffer around that unit. And that's been used in a few different things mainly for looking at potential source regions or source areas. And then, of course, we have the stream sediment geochemistry. Again, in that case, there's an example of that. So what we're looking at here is the, actually, I should put the whole data set up. Well, anyway, I'll just leave it like that. So this is what this is basically looking at is the drainage basins for Queensland, and this is from the national database. The drainage basins for Queensland have a whole range of different rare earth elements associated with them. So I took two approaches. One was to say, okay, what's the minimum of all the different rare earths? What's the minimum anomalous value? As basically, then what you're saying is that everything is above this minimum anomalous value in terms of standard deviations above the mean, because obviously the different levels of rare earths have different levels. So in this case, what we're looking at here is the reds are 2 standard deviations above the mean for at least 2 standard deviations above the mean for everything. And the greens are at least 1 standard deviation above the mean for everything. So I guess it's something that shows broad anomalism in rare earths in those drainage basins. And one thing that comes out, and Joe has spoken about this before, is that far north Queensland, the Cape York Peninsula always comes out of, you can look at these data any way you like it, it always comes out as being anomalous, which is really interesting. So we've used this, and there are various interpretations as to why that is, but I think it's something that is unfinished business in terms of exploration, in my opinion. So that's coarse fraction, but there's also fine fraction. I won't go through all those. There are a whole range of different geophysics data sets, the standard magnetics, but also gravity and radiometric data sets. So for example, you can't see this very well, but these are all pixels in the state radiometric data set that are above 10 parts per million. And I've also got some for about 5 parts per million. The significance of that is that is that for almost all the deposits out there, uranium and rare earths correlate. So it's a really important, it's an important geophysical indicator, obviously only in exposed areas, not in covered areas, that you can use as a proxy for rare earths. And there's a whole bunch of geology layers as well. So I'll turn off the geophysics layers, put on the geology layers. Geoff already mentioned the Northern Australian solid geology compilation. That's a brilliant compilation. It's really useful, and I've made a lot of use of it in this analysis. So I think, is that going to come up there? Or, no, I've turned everything off, so it's not going to come up. So I'll turn the. Oh, it's big. Anyway, oops, that's the wrong one. Anyway, yes, so there's all these data sets are put in there. Also, the down here you can see the Queensland portion of the solid geology for the Thompson origin. You know, there's not really anywhere near reliable geological guess as to the geology in that area. So, you know, again, I'm not going to go through all these, but just to show that we've sort of pulled all this data together to try to map different structures and rock units. And then all these various different lines are fault data sets that are available over the state as representatives of potential pathways for fluid flow. So, you know, so what this, I guess, what this compilation contains is just a whole range of these, you know, a range of the different data sets that we use to carry out the analysis. And then when you look at the, just going to go to the components here. So if we look at, you know, so that's those are the IOCG, the final prospectivity estimate for the IOCG, which is carried out using in two different slices, a covered area and a non-covered area. But inside that, there's a series of I'm just trying to find it now. The individual components have been separated out. Yeah, so for example, all the different inputs are put on there. So that's one of the source inputs. That's another one of the source inputs. So when you're going through the data set, all of the source inputs that went into the prospectivity analysis are included in there. And then the outputs are for the different components. So that's the source output, which is based on, you know, as I described before, the different individual data sets that went in, that were used as proxies for that source, modified by their importance, applicability, and confidence. And the same thing goes for drivers. So you can see that I placed a lot of importance on the Williams suite as a driver for IOCG mineralization, because it's such a strong, there's such a strong, I guess, spatial correlation with that style of mineralization. But it wasn't the unique one, because maybe there's something else that does the same thing for rocks of a different age elsewhere. And what you can also see is that I've extended that interpretation undercover using the deep mining Queensland project and other projects that have mapped Williams suite granites under, or Williams suite intrusives undercover. And then pathways are from a mixture of surface mapping and the structures from sea base and GA's crustal scale data set of crustal structures and some geophysical criteria as well. So, and then for traps, there was an exposed version, and this is the exposed version. So we're actually using geochemistry, and then the one that neglected geochemistry is an indicator of these sorts of things occurring, because obviously you're not going to see a geochemical expression of a trap if it's undercover. So I guess that gives you a feel for what's in the data. How many of you, by the way, have actually downloaded and had a play with any of the compilation? Whoa, 1, 2, 3. Well, it's good. At least you might find this boring, but at least it's new. So, even if you don't want to use this approach at all, there's a lot of data that's been pulled together relevant to rare earths, relevant to cobalt, relevant to scandium or whatever, that you can use in your own way. It's just one of the main aims here wasn't to impose an interpretation on someone. It was to say, well, here's all the data that we could find relevant to this, relevant to this particular kind of challenge. Okay, so does anybody want to? Might be we've gone through nearly an hour of talking now. Does anybody want to ask any questions, or are we dealing with? We have a couple online. That one's done already. Leslie, what did you mean by mineral systems was always meant to be about processes? Are you complaining about our approach, Leslie? Oh, yeah, we can't hear you. You're gonna. Okay.
Are you still trying to track Leslie down, Rick? Or
no, that's okay.
Yeah, this is great to see, Rick. You showed the different component plots, I guess, like source, driver, depositional gradient, and so on. Somewhere embedded in here, can people see the way things were weighted, the way the different input data sets were weighted to get to those component plots?
So if you look at the report, well, actually, yes, they can. So if we go, I'll go to the, I'm just going to quit from this presentation for a second and go to the online tool, if I can. So this is the actual online version of this. I'll go to a different one to start with now. So this is actually, looks pretty empty so far, doesn't it? But so this is for alkaline rare earth systems. So this is, and it's a little bit of a low resolution one. So you can do a higher resolution one on here. But if you look on here, and this is for source, you may not be able to read that, but you can choose source over here, and then it shows the importance value, the applicability value, and confidence value. And if you click on that S1, and again, it's pretty small when you're looking at, I could barely read it from here. We'll see a bigger version of that in a second, but it actually shows what the criteria was. So in this case, S1 is non-magmatic sources of iron, copper, gold, potassium, rare earth, uranium, etc. And the specific mappable criteria is rock units with greater than 90th percentile in total rare earths, heavy rare earths, or light rare earths. And so I've rated the importance, applicability, and confidence value for that, and the other ones as well. And then if you go choose up here, you go to driver, and it's done the same thing for driver. If you go to path, it's done the same thing. So you can see all those, and obviously they're all in the report. So again, I stole my approach from the GA papers on nickel and on IOCGs in the TISA region and that sort of thing. I used almost exactly the same table, but modified for my purposes, so that there's an importance, applicability, and confidence estimate put up there. And arguably, there's probably more you could say about why I chose those numbers, but actually, part of the exercise today, if I don't run over time, is to get some of you to actually second guess me and think about what sort of value you would put on those, and then we'll modify this, because with the online tool, what you can do is basically say, well, for the driver, let's just say for the driver, well, I don't know, let's say for the source, you could say, well, actually, I don't think that's important at all. And so you just drag that slider down to 0 and then recalculate it. And you say, actually, I don't think this one's important as well. And you may or may not be able to see, but it's changing the prospectivity estimate on the fly. So the same thing you can say for the trap. You can go, well, actually, I don't think including geochemistry is really something we should be doing in all this. So I can turn all the geochemistry off, and I'll go back and put go back to source, put these ones back up, and it's gotten rid of the geochemistry and changed the prospectivity estimate.
Yeah, and presumably this depends what sort of geochemistry we're talking about too, right? Whether, yeah, and I'm just thinking out loud really here now. So, but one thing this makes me think about is the prediction part of this is one side of the equation, I guess. But some of these data sets you're talking about are perhaps more in the detection side of the story. And maybe one way in this data set, you could use it in both ways. I guess you could select your data sets that you think are part of the prediction story and produce the predictive map. And then because you've got all your other data sets there, like surface geochemistry, for example, it's maybe more a predictive thing to see how well the hotspots in prediction turn out in detection. So
yeah, that's this was like the prototype of this tool, and we've had that feedback from other people. I mean, I think that's really good. It's a really good observation. I think it's something where we probably should do that, because I mean, yes, you can say a geochemical expression is evidence that sort of thing has worked, but it's not actually. It's not telling you about the process. It's telling you that the process has worked. Yeah. So yeah. Any others while we're okay? I think I'm just going to come back to.
Rick, I'm looking forward to putting some of this stuff in Digital Earth. Because it'd be really good to put in there. But I guess my question is similar to an issue we face is the updating of the baseline data. So, you know, you showed us the fault map. Is this linked to the web services so that will change over time?
No.
Any plans for that?
No. Well, it's something that probably we should do, but no. This was a painful snapshot compilation of everything we could find at the time, and actually this morning as I was listening to talks, I was thinking, oh, I wish we'd had this data. Like, Dave, where are you? all of the data that got collected for for Peralkaline intrusives in Eastern Australia would have been really good to put into that compilation. So.
Oh, yeah, thanks, Rick. I just wanted to comment. I saw a question there about mines gaining value from indium through the smelters, for example. And we've had some long discussions about, I think Nathan and I, about this over the last month, is that, for example, indium, and I guess it goes back to IOCG deposits and cobalt as well, for example. But if you look at indium production, and most of it is essentially coming out the back end of the smelter that's processing sediment-hosted base metal ores or concentrates. But what we've been looking at is to say, well, are there other more niche styles of deposits that you might be able to find that, for example, you know, Belgammon is an obvious example whereby you know that it's very indium rich, and in that case you may be able to sell your concentrate with indium or baked into your or a price for indium put in your contracts with your concentrate, etc. So it's not just getting it as you're losing it to the smelter, but it's actually a deposit style that you know you can actually gain value from those byproducts. So that's just, I guess, try to add some context around that.
Great, thanks, Paul. Actually, what I might do now, so is you know, as I said, introduce you to the I sort of thought, well, which example am I going to go through? And there's the one that I thought could be relevant because we've got a couple of unconformity related or arguably unconformity related uranium, mainly uranium, but possibly rare earth bearing deposits in this part of the world, in Maureen, Ben Lomond, and that sort of thing, is to go through the process model for unconformity / metasomatic uranium rare earth deposits. And the reason I grouped those together is that there are a lot of elements that are very similar between those different data sets. And again, this relied quite heavily on a very good analysis that GA did about 10 years or so ago, looking at uranium potential across Queensland. But this sort of cartoon, I guess, and I'll focus on the upper one, is the sort of context to talk about the process model for this style of mineralization, which is essentially that you have oxidized and acid, probably basinal fluids, relatively low temperature, that are stripping uranium, rare earths, platinoids, and a whole range of different things from fertile host rocks. And those fertile host rocks could be a whole range of different things. Anything that is enriched in those elements, but it usually ends up being either felsic or felsic derived igneous rocks, and traveling through basins, but also through the fault architecture in a region, I guess driven by deformation, but also potentially driven by the heat source of intrusives, and precipitating in redox zones. So in those redox zones could be a skarn in the case of Mount Isa. In the case of unconformity deposits, it's often a redox contrast between the basement and the cover rocks, where the cover's more oxidized and the basement's more reduced. In the case of North-East Queensland, actually what you see is mineralization associated with metasediments, and even more commonly, I guess, carbonaceous metasediments that are spatially associated with these thermocarboniferous volcanic intrusive complexes. And that's really what you see at Maureen. And so I guess without going into a huge amount of detail, that's the kind of process model that we were pursuing in this case. And in this case, what we ended up with was really focusing on Northwest and Northeast Queensland, coming up with a range of different areas that were, and again, what I'm focusing here are not the obvious ones that we knew about already, but the ones that are potentially areas that haven't been as explored, that contain, that have the right sort of confluence of those process ingredients as I've judged them. So what I was going to do now is go back to that Mentimeter and actually go through a little bit of an exercise, and I'll have to get back to the right. Back to the right. Sorry, just wait a second. Yeah. Oh, before I do that, if you want to have a play with these data sets, so this is not the Mentimeter. This is the actual link to the unconformity rare earth, unconformity / metasomatic rare earth deposit. Or if you go down here, it's a little bit hard to read, but smi.uq.edu.au/project/Queensland New Economy Minerals compilation. That will link you to all the different data sets we've done like this. But this one will just take you straight to the online tool. Now this tool is written in JavaScript. So if you want to put your own data sets into something similar, it's all there in JavaScript for you to download and play with. And there's actually, I'll give you the link to the GitHub to it later. So again, this is just a delivery system, and there's a lot of improvement in this system that we should probably go through, but it's all there for anyone to play with. So I already mentioned these, so I'm not going to mention them again. I only just put them on here because what I wanted to do now was for a few different data sets, think about the importance of the process, the applicability of the data set, and the confidence in the data set. So, but I'm going to start with some open-ended questions, and that is that, you know, assuming for a second that we're looking for a style of mineralization where the rare earth elements are actually leached from source rocks that are already there, what are the data sets you would use to map those source rocks? You've got a blank slate. Somebody says to you, I want to, you know, tell me where the source rocks are for rare earths in Queensland. So any ideas? Type away. Anyone typing, or are they just saying, good God, free us? Regional AEM. Now I've got to know how would you use regional AEM to tell you about source rocks for rare earths? Fractionated felsic rocks, yep. Geology maps. I'm thinking about what particularly you would look for. Not I would look in the geology maps, but what would you look for in those geology maps? What would you look for in the geophysics or we've got here, so rare earth patterns, potential to look for rare earth depletion. I have an interesting story there. How am I doing for time? Let's got 20 minutes. So I went to an Amira exploration managers meeting, and there was a guy from Inco. I could say this because Inco doesn't exist anymore. And he said, we decided to do a global exploration program on the premise that nickel deposits would be associated with extremely nickel depleted mafic and ultramafic rocks because the nickel had been stripped out of them to make nickel deposits. And he said, we succeeded in finding some of the most nickel depleted deposits on the planet. Which I thought was a really good story. Whole rock, felsic rocks, yep. Alkaline rocks, yep. Radiometrics. Yeah, I mean, I already mentioned there's a really strong correlation between, you know, you look at when you start doing this sort of compilation and you start looking at the geophysical expressions of all these deposits, they're always a uranium anomaly. There's, you know, it's really, really common. Okay, so now what I'm going to do is get you to and that's probably too small for you to see. So I'll describe what we're looking at here. This map, which is obviously very tiny, but all these different green areas are rock units. So I've taken the whatever data that we have. So GSQ had a data set, Coralie had a data set. There were a range of other data sets that had rare earth analyses, and I can't remember how many rare earth analyses I found in total, but it wasn't a very large amount. We need a lot more, and just cross-reference them with mappable rock units. If there was a rock unit that had total rare earths, heavy rare earths, or light rare earths that were greater than 90th percentile in the whole data set, and obviously there's some problems there because you're thinking about percentiles in the data set rather than an absolute number. But you know, and you'd say, how important is that? How important would you say that is to so we've got a couple of people who've ranked it. And how applicable is that as a data set? So what's the linkage between a rare earth enriched source rock and that data set? And then how much confidence would you have in that data set? So I'm going to give people another couple of minutes to think about it. It's not a test. There's not actually a right answer, but 30 seconds more. We've only got 13 answers. No, you can answer anything in between. Oh, right. Oh, bugger. Oh. Is it? Oh. Gee, I better change these other ones. Just wait a second. I better change them so that you don't, I've got a whole pile of these and I don't want it. No. It should be, how was it presenting today? I don't care, go away. It's getting worse. Sales and slide type. Oh, I'm really sorry about this. I thought you could sort of drag that slider to anywhere. Let me see if I can fix this. Yeah. Set range from the scale and all. Sorry about this. Customize. Show. Oh no.
Change the high value to 10.
What's that?
Can you change the high value to 10 maybe?
Oh, maybe that's it. Yeah. I'm gonna, yeah, I'll do that.
You just have to.
Okay, I'm gonna reset and start again, and then actually let's take this one as a dry run. And I'll go on to the next one and set the values to and we'll see if we can go 0 to 10 and see if that allows you to. So you know, we got some sort of indication anyway. So now I'm gonna change that one. See if you can. Is that all right now? You can choose numbers in between. All right. So in this one, I'm actually using the radiometrics. I'm saying, okay, there's two different ones here. The S2A is very close to uranium source. So in other words, you've got to be within 10 kilometers, you know, within 10 kilometers of a radiometric anomaly of greater than 10 parts per million, a number which I pulled out of, you know, where, but it was one that showed a number of, I guess, you know, an acceptable number of anomalous areas, taking into account the characteristics of the radiometric survey. So, okay. All right. Now what I'm going to do is go change all those other ones before we get to them. Because what I'm then going to do is take these numbers and plug them back into the online tool. So got 25 people. So just give me a second, and very sorry about this. I'm going to now do the other ones. There's about 1 million of them, so I won't subject you. I won't subject you to all of these. We'll just go through the source ones. Give them the time. That's it. Okay, right. So we've done that one. Go back to present. Okay, so now we're going to go on to the next one. Oh. I forgot. So this one is actually, I haven't changed the, oops, there's a little mistake. So that one's actually, it's not rock units greater than 90th percentile. It's a 30-kilometer buffer for uranium anomalies, so moderately close to the uranium source. Greater than 10 parts per million in the data. The question was, how are you defining the anomaly? And really, it was one where it's greater than 10 parts per million in the radiometrics. And obviously, I think the ground values would be very different. But if you changed it to the number you might expect if you're on the ground, you wouldn't get anything in the whole data set. So that's why I chose that value in the state grid. It's obviously not telling you really what the actual value is on the ground. It's just the conversion in the radiometric data. Okay, so this one now is stepping back and leaving aside the rare earth content of these units and just saying felsic rocks, on the premise that rare earth enriched felsic rocks are commonly invoked as a source for these hydrothermal deposits. But it's also there on the premise that the amount of data for which we actually have rare earth analyses is relatively small. So if you only focused on units that you'd identified as being rare earth bearing, you may miss out on units that are perfectly good. They just don't have any analyses because there's so few analyses. But you might have less confidence in that sort of data. Okay. And then this one is really based on, it's based more specifically on North-East Queensland. And that is that there's a really strong correlation with and good potential source associated with the, or it seems to be a good potential source associated with the permocarboniferous intrusive volcanic complexes. So where those complexes occur is another data set we use to say, okay, where's the potential source? So it's just permocarboniferous intrusive complexes. Okay, now what I'm gonna do is write all these down. Sorry. Yeah, okay. I'm just going to go back through these now. Okay, so I've got now what I'm going to do is just go back into this. Oh, actually, it's where quit out of this and just very quickly back to this one. Choose the uranium earth. And then show North-East Queensland because I've divided them up into different areas. And then for the and then change these. So that's 0.7. Anyway, look, I'm probably not going to go. So you can then go through and change all these to the numbers that people came up with, and rerun it. Not sure why it's not running here. I'm just going to change it to arbitrary numbers here. And then I think I must have lost the internet or something. There we go. This is the low res version. I'm just doing that. Okay, so how much time have I got left? Oh, 4 minutes. I thought there's no way I'm going to use up all this time. I'm only, yes, that's right. Well, that's important though. Okay. I'm just going to go straight to the end for the last couple of questions, which are very simple. And again, a free form thing. What do you think of the potential benefits of using this sort of approach? None is a perfectly good answer, by the way. It has been successful in other exercises, but So definitely thinking data objectivity, new areas highlighted, honing regional prospectivity, ability to test different hypotheses, maximizing exploration dollars, collates relevant data, spatial relationships, good first pass, gaps in data sets, testing models, thought experiments, those are all good. And challenge bias. And then I think there may even be more answers for this one. What are the potential limitations of this approach? Thanks. Yep, so good. Yeah, source data, quality input data, heavily biased towards outcrop. We would try to address that. But, you know, the reality is a lot of our data is based on information you get, you know, that you get in outcropping areas that you don't have in areas that don't outcrop. It's very good bias through data availability, bias to well-explored areas. Yeah, that's where you've got the data, regional scale, averages, over small thumb. Yeah. Oh yeah. What? Yeah. When you have a whole group full of people, it averages out to 5 out of 10. Yeah, that's right. Yeah. Biased to, yeah, limited by lack of solid geology maps in covered regions. Very good point. Narrow opinions on what should go into the model. Data scarcity. Yeah. Experiments limited by data inclusion in data set. Overestimation versus under. Granularity, inappropriate sterilization of land based on current groupthink. I mean, that's partly we're trying to get around this by linking it back to processes rather than deposit-based models. These are all good observations. So we've really only got a couple of minutes left. I hope that gave you a little bit of a feel for what's in the compilation. Most of you haven't looked at it, so all of the data sets that we've talked about today are there and available on the GSQ Open Data Portal. I'm just going to go back to my presentation and shoot ahead to the end. Lucky for you that you missed all those. There's more there as well, but if you go to if you go to the GSQ Open Data Portal and type in New Economy Minerals compilation, all of those data sets will come up and are there and downloadable. I've also got copies of them all here if you want to you know, get me to copy them all onto a dongle rather than using 50 gigabytes or so of your bandwidth. Yeah, the atlases, which we'll talk about tomorrow, are in there as well. So that's about it. I think I've used up my time. Thank you very much, everyone. And please come ask me more about it later, or if you have any follow-ups, just let me know.
Do we have questions? Stunned silence.
Is there any more? Katerina mentioned one about a lithium one. Is that something that you worked on?
No, we're not doing lithium. There's a couple of more. There's a gallium germanium one that hasn't quite seen the light of day yet, and the Indian's just being finished. But there's not a lithium one. Yeah,
because there's no lithium.
But you know, we'd be happy to do one. And gold and.
Paul?
Yeah, just a comment rather than a question. You know, in terms of thinking about undercover versus explored, you know, you hear so many people say, you know, all the deposits close to surface have been found. And this is often when people are talking about copper or lead or zinc or gold, etc. But I think getting into new economy minerals is a whole new ballgame in that we haven't understood those systems. So I think to a certain extent, we're going back to scratch now, whereby I think a lot of those deposits that are going to be found in those mineral commodities are actually going to be at surface and haven't been found because we just didn't understand the systems before. So I think it's a really nice case that we can go back to exploring at the surface and still be expecting to find world-class deposits. Here in Queensland, of course.
Good news, Paul, good news.
Olivia had one minute ago.
Where?
Rick, can you hear me? Yes. My question is about the future, if you will consider repeat the same workflow in other state, because one of the challenge sometimes in geology is merged in the age, exactly the same geology that one state already done. So I don't know if part of the project in the future.
Yeah, we're not currently doing this anywhere else really, but Geoscience Australia is certainly doing similar kind of analyses. In fact, you know, an approach that we've more or less, you know, borrowed from. For example, going from Tennant Creek across to the Mount Isa region, that certainly crosses state borders. But you're absolutely right. Yeah, this sort of analysis, you know, should really be based on a geological province rather than state borders. But
and I'll just make the comment. Thanks for the question, because I think it's a good one. There is a tool in the GA portal that does something very similar to this. It's called the Mineral Potential Mapper, and it gives you the same sort of functionality where you can go and decide on the criteria that you think are important and play with the weightings and merge data sets together and produce a similar sort of thing. Yeah.
Is that still working? Because I went trying to find it and wasn't able to find it last time I looked.
As far as I know, but I haven't tried recently myself, but
yeah,
it should be still working. So we should have a look, and if it's not, work out why not.
Are there any questions online, Rick?
I don't. Nope.
Any more in the room? I'm sure there's lots of discussion to come out of this, and I would encourage everyone to have a play with the tool, whether it's through the MapInfo, ArcGIS or QGIS data sets, or the online tool, and very open to, you know, suggested improvements and anything else that we can add to it as well. All right. Well, thanks, Rick and Nathan and Paul and Katerina. Really appreciate the team effort there. And I think we might now break for afternoon tea, and I'm going to lean over Andy so I can see what time we come back. We will come back at 3:10 to hear from Dan Johnson, Fetch Metals, the new kid on the block. Hope he comes back.
Just testing. Yep. Just testing. Testing the other mic. Seems to be working. Okay.
Since the host has removed him from the meeting.
Yeah, because he
couldn't.
He asked me to and then couldn't log back in again. So. What's that? Well, yeah, he's still there as a. Let me just check and make sure. I mean, he's still there as a panelist. You want to be added as a panelist? Yeah, we'll add you as a panelist. You just brought your Cant. Yeah. Yeah. Okay. Okay, so. Again. Geological Queensland. Okay, Okay, you're at it now. Yeah. So you should get an email just about. Yeah.
In the table you showed, the stack of the different types of iron deposits. There's a thing you said that's
It's the. I mean, there's a lot of argument about that, whether it's actually skarn related or whether it's an overprint of the skarn. But I would call that like a medicine deposit. There's definitely a pre-existing skarn there, but it's not made for it. It's a hydrothermal deposit.
sorry, what was the I'm doing my PhD engineering.
Right.
The biggest part is trying to put it in the mineral systems context and figure out what it is.
Yeah.
And so far, most of the the job that I have found is that it's contact with scan deposits, and I'm not new. And I found one or two obscure as a little reference papers in the way somewhere.
Yeah.
I think that might be more.
Yeah, so Ken Fuller's records that there's that he's seen evidence of alkaline intrusives that are associated with mineralization. Nick Oliver did his PhD in the region and worked on Mary Kay's and Nick's interpretation was that the skarn was and look, I haven't done I guess the and then this had a student who worked on who had also interpreted it to be hydrothermal overprint of the skarn, but the mineralogy associated with that overprint is still skarn. So that's where I would put it. I put it in. I had this broad class. There's a whole range of different uranium, copper, uranium, rare earth deposits in the Mount Isa region. They're very variable. They include Helen, and they include, I think, things like that that are arguably ICGs, but they're all a product of, in my opinion, anyway. Hydrothermal fluids probably enriched in high-purity elements that are oxidized, that are depositing as in response to a competency and freedom from hydrothermal fluids. It's not, you're not getting rare earths transported. I mean, I know that Ken has found 3 samples of something that plots in an alkaline field, but there's not, anyway. I'm repeating a bunch of stuff that's based on my reading rather than a huge amount of work.
So interesting that you put in the classic sky. That's like 90% of the.
Yeah, I think it's because when you look in the Mount Isa region, there's all these different deposits that are roughly the same age, that have roughly the same mixture of elements, that have great variation in characteristics. In my opinion, they're all just the varying products of a series of processes.
Yeah. Just very gold. Very cake.
Oh yeah, okay. Yeah.
Mary Kay is like the biggest one because that's a lot of the turquoise and you put in mind, but I just did a company in Mount Isa in May, and I took that company there to use Natalie and Anthony were up there in 2020 when they could travel from Canberra, right?
Yeah.
And they took us to samples as from Elliot Swan and a couple of other places.
Yeah.
But there was also room for IOCG studies.
Yeah.
Whereas
But
I'm looking at everything like IOCG, but It's such a weird thing that I was actually quite happy not to see scars in this specification just now.
You know, if you apply the sort of the little boxes approach to classification of uranium deposits in the Mount Isa region, you have albitite uranium with copper and rare earths associated with that's the gold albitite. Then you would have skarns that very quickly. Then you would have some sort of variant of IOCG. You'd have other things as well, you know. So then you'd have really something that somebody would call some other sort of exolite. And I think there are products of a hydrothermal fluid that's interacting with, you know, that's producing different sets of characteristics in response to, you know, in response to variable conditions of the process. Yeah. I think
proof that it's really scarred.
Yeah.
Would I'm just looking at so much from that it's like I'm never going to finish.
Yeah, and I wouldn't bother. I think it's more important to think about what processes went on and look at.
Yeah, that's going to be the focus.
Yeah,
so,
that's great. That should be a great project.
At the moment, there's already we say scar. Yeah. I just need it more peroxide. I mean, it's a different way from human. I mean, I have a unit American injured for that is up to 99% peroxide.
Yeah.
That's up to 99% pure garnet.
Yeah.
That's sitting in there. So what am I supposed to call it if I don't say kind of peroxide?
Yeah. I would call it exactly what it is. Yeah. It's amazing that it, yeah. I mean, well, the same thing happens. I just think it's much better to describe what you're seeing and then, you know, work out what it means in terms of process rather than trying to fit it into a box. And you know, again, there's a classic, there's an area way out to the north of Natalie. North is the name of the project. New press drilled it before that. And you know, there was a big bunch of Williams granites in the mag. This is under 4 meters of cover, and then big magnetite bodies around the edge with, you know, actinolite and epidota and areas that have, you know, got lots of biotite and people say, oh, well, that's not an IOCG, it's a skarn. Going, really? Well, it's just a big magnetite body around the, you know, a big dense body of magnetite around the edge of Williams edge granite that's got some skarn associated minerals associated with it. But why is it different to, you know, to an IOCG system? Oh,
north of Mary Catherine there.
Oh yeah, I've probably been there.
Bodies and the cabinet, and we went up there and we were doing field work. The cabinet was perfect.
Yeah.
Up to this side is perfect.
Yeah.
Even if this was like this, but just a bunch of like little ones.
Yeah.
And all those massive anthropos.
Yeah. I've got some of those at home, big actinolites, but it's big. Yeah.
And then those little trucks of wood and superflights and those ones that edge super tourmaline and adenite as well. And then you've got snake because the neighbor the other time before it, it's just a bit east of the big like
Yeah.
basically Lead, limestone, something.
Nick did his PhD, Nick Olden did his PhD in that region, as you probably know. His interpretation of that was that they were, they were essentially big veins. They were just veins associated with big gabbro bodies.
One of the undergraduates is doing a special project on that right now. Just presented a talk today.
Right, okay. Yeah, good. You're gonna grab a coffee before.
Exciting. I'm going to smash it. Say it. You're gonna smash this with cement.
No. Well, I will.
You got some good questions. Who's gonna win the next origin game?
Who's gonna win first? That would be a bad.
Is someone filling in for sun?
Yes. All right.
Going.
The invite. I couldn't accept the host had removed me though, so we'll run it off Helen's computer instead.
Oh, okay.
Helen can share as well.
What if I get inappropriate emails?
Close your emails.
You're going to get hooked up. Yeah. There's a pointer. Evan is the man. He's going to get everything sorted. Everybody, if you could make your way back into the room and take your seats, please. We're early, that's why they're still out there. And Evan's doing these really quiet.
I got it, Rick. Thanks. Well, you know, you still got it.
Everybody, please take your seats and be quiet. There was some cheeky laughter up back there. All right, we're going to kick off for the super session of the afternoon, which is where we go, oh my God, what's it all about? It's about mineral exploration. Dan Johnson is going to lead us off from the newly formed Fetch Metals, currently putting out an IPO. I'm sure he'll talk about that. So please take it away.
Thanks, Helen. Hear me? Yeah, look, Helen and your team, as always, wonderful gathering of people here, lots of familiar faces, so great to see everyone. This is a presentation which probably not going to hit as much on the geological side as I'd like, but I'll explain why that's the case. We're a new company, private company at this stage, but it's an exciting project area. So I'll, without further ado, I will move on to the snippet. There we go. So,
start now.
Yeah.
We've got mic issues as well. According to the online view.
Might have to just switch mics here, sorry. Yeah, just take that one. Yep. Working, it doesn't seem to be. Just gonna put that in there.
hello.
I'll listen. Could you just talk a bit and I'll just check?
Yeah, how's that? That's working. This one?
Yeah.
Well, I could talk without slides, but you'd miss out on the pictures.
No, it's all right. Keep going.
The slides are.
No, but they're not up there.
Oh, the slides aren't.
No, they're not moving through.
We have to.
Well, I've tried the arrow. Arrow, none of those.
So what you have to do is.
Oh.
Does anyone have any questions for Dan? There we go. He's away. Okay.
What was that, Helen? I didn't hear that. Usual display. Well, no one will be able to read that. So anyhow, we're not listed, but anyhow, take everything with a pinch of salt. Right. I hope this work. Oh, good. Okay. Right. Quick one on who we are. Some of you will have heard of Hamish Collins. Hamish and I have worked together for over 12 years. We were both working on the Wolfram Creek project. So Hamish is the MD. He's down in Sydney. I think he might even be listening in. Tim Gunning is our chairman, as myself. Two investors that came in, or representing the investors, Anna and Richard. and Matt, who's over here, who's only been on board for just over 2 weeks. So that's the team, and there's a lot of experience in that, and in the right areas. Obviously, the technical aspects of what we do, but also the ability to hopefully bring capital to this project so that we can progress it and also actively explore. I've combined some of these slides from stuff we presented to investors previously. So there's the usual kind of statements here about the obvious investment kind of interest in this thing, where we are. Obviously, oops, there's the press the wrong button. There we go. So obviously some of these names people will be familiar with. Glencore, where I know a lot of you have worked, and then the others, the guys at Genova. I don't think anyone's here today. South 32, thanks for putting this on. So in a great part of the world, as has been made very abundantly clear today, it's got pretty much all the strategic metals, that you could wish for. We've got a project here which we think we can produce 15,000 tonnes of LME copper, year on, year out for at least 10 years. That's our aim. We're in a good part of the world in terms of the infrastructure. We've got a railway line nearby, and the possibilities of other infrastructure being put in the near future. That's the tenement holding we've got. There's a small interest in that bottom, that purple, in 20% or slightly less than 20% actually at the moment, or sorry, 11% at the moment, in that Tombola ground around Gilded Rose, etc. The rest of the brownie colours are other tenements. Little bit on corporate structure here. I suppose the main point down here is the mineral resources, just a bit under 30 million tonnes, less than 1% copper, 0.9. There is gold in this thing. It doesn't mention some other things. I'll touch on that a little bit later. As you can appreciate, this is an area where there's a great deal of interest. So people will be probably following in the news the work that Peter Bowler and his crew at Carnaby, Russell Davis and co at Hammer. Lots of you in the room will have other interests in this. We've got the Rio guys, the Genova guys. This is already about a month old, this slide, but it's a tightly held area, and there's a lot of there's a lot of money being spent in this area right now. Quick corporate structure here. We're Fetch Metals, as I said, private. We completed a deal with ActiveX to take 100% of the Florence Bore stuff just before Christmas. We've been dealing with the White Range stuff since almost July last year, and that was only completed, well, 5.5, 6 weeks ago now. We now hold 55% of that, and that's composed of those bits you see there. The White Range. When we talk about the White Range project, essentially that's the QMC assets. Florence Bore sits out of that. I think we'll be talking about that as one package. Obviously, Florence Bore going forward. Strategy, obviously, I mean, we want to develop this project. It's an exciting project which is sat in a degree of limbo, you could say, for the last 12 to 15 years, for varying reasons, but we won't go into that. But we want to obviously move this thing forward. It's been too long sitting there, kind of not moving. So develop. We are, well, I say I have been, but Matt certainly has got his head into the data now, only in the last few weeks. There's a huge amount of data. This has got a long history, a very, very interesting history of exploration in this area. I mean, people know about Cloncurry as an old mining district, and certainly this is very much part of it. We're growing. We obviously keep an eye, as we did with these two transactions, on other opportunities in the area to consolidate and make things, make this a real mineral hub in future. Obviously the facts of integrating renewables and reducing operating costs, all those abilities now of changing the cost structure of this development. That's what we're looking into at the moment. And the going deep thing is we haven't, obviously our first aim is to make money out of the oxide material, but these systems, as I'll kind of touch on quickly later on, these, as all of you here, mostly being geologists, will understand these things have good depth potential. We're only talking about the oxide in these things. So, another snapshot. Look, that's just generally the northern region. Oops, I've done it again. There we go. So we've got the different deposits down here. You've got Young Australia, obviously the Coorabella mine. These two, which were part of the ActiveX deal, the Florence Bore stuff. And then these ones around Green Mountain, two small deposits there, Vulcan and Desolation, and a Mountain Cave. So this is the kind of central hub of what we're looking at. As I said, we think the economics are robust. We are currently redoing the scoping study. We think that was necessary in order to take it from the mid-2000 to 2004-5 time to current, because there's a lot of things that changed, and there's a requirement to meet higher standards of how you operate these things. So that's what we're doing in the scoping study, and then obviously we intend to move that forward to a feasibility study after that. I'm just going to quickly touch on some of these deposits. As I say, the thing about this whole project is that there's all sorts of different deposits to actually talk about. And as I said to I think Helen earlier in the day, you could give a talk on any one of these deposits and have lots of slides of the rocks, the mineralisation, and the complexities of each of these systems, because they're all slightly different. There are, however, lots of similarities also. And one of them, I mean, you'll keep seeing, as I typed out these bits and pieces just for these few next slides, there's a strong structural component to all these. And veins, breccias, stockworks, all that mention of geology comes into play. They're largely in slates, or siltstone shale sequences. The mineralization styles, in part, the breakup is due to the fact that a lot of them are going from oxide into fresh rock. So you have all the different exciting oxide minerals of copper and other things, and then you're into the fresh rock. So these are broken out. We're assessing all that, because that's all important in terms of how you're going to process this, all these different mineral deposits. Also, how you potentially blend them as well to get the best out of them. So anyway, I'm not going to read all these things out. People can see that. That's the area around Green Mountain. There was a shaft there, which seems to date to about 1910. I didn't actually spot it when I was there, so that's pretty ordinary. Unless it was filled in. I'm still trying to work that one out. But that's the type of terrain it is. Those of you that perhaps also know the Copper Canyon area, which is to the north of this, it used to be Homestake. And I remember when I first turned up in Townsville in 1994, that was one of the most talked about exploration areas at the time in 94 that Homestake were working on. Coorabella, a long history here. This place is fascinating as well. Lots of tourists still go there to look at the stack and various things. Slightly high grade mineral system here. Currently we've got the top 100 meters. Genova have below the 100 meter mark. Yeah, as I say, long history. Again, as I said, structurally controlled veins, breccias, stockworks, black shales, siltstones. More different ore types here, part because of the aspect of having fresh sulfides in the system, but strong alteration systems in these things. And again, the depth potential on Coorabella certainly looks interesting. It's quite a long strike length. I'd say it's probably a bit more than 900 meters, but anyhow, yeah, a lot of work to do there. This is a shot I took just of Young Australia. This is looking up to the northeast at the kind of, well, I suppose you call the northeastern pit faces, well, walls. There's two lenses here. The lens to the right was the high grade stuff, slightly lower on the other side. That seems to carry to depth. There is a resource on the one to the left. It seems to be a bit skinny and it's got less drilling into it, but this is MIM mined this and trucked the ore out of this back to the Morgan Road. It's got some fascinating geology in the pit here. We were, myself and Dr. Gojan Zhu, who I work with at MIM and Xstrata. We had fun for a couple of hours wandering around here, looking at all sorts of interesting stratigraphy, mineralization, etc. So there's a lot to be got out of this thing. There's just on that. There's another thing called Tang Hill, which is out to the northeast of this, which they did some drilling on, exploration drilling, and got some very interesting results. And that'll be in the mix for getting more attention from the exploration side of things in the near future. In terms of growing, or for want of a better expression, these are, as I say, used for some of the people we've been talking to of late. This is a map just showing copper. There are a lot of very interesting copper trends that extend well beyond the extent of the currently understood mineralization. This will form, I think, many years of further work as we investigate what these mineral trends mean. Some have small, quite a few have small workings on them, but there's certainly some very interesting. Apologies. But up in that Copper Canyon area there, some very significant hits. And as I said, Homestay at the time back, whatever that was, 28 years ago, they were pretty excited about that Copper Canyon area, but there isn't a resource up there. These aren't very clear, unfortunately. There's some shots. I didn't manage to extract any others out of it. There's a lot of cool photographs, but I've kind of nicked those out of the YAML presentation that they had. But different types of mineral systems here that are shown in those two photos. So lots of work to do there, but lots of exciting copper trends. This is the deal we did completed just before Christmas, Florence Ball with the ActiveX ground. There's two small resources here. This is a subaudiomatic magnetic image. It has a tendency to pull out all the conductive stuff, both conductive interesting and potentially conductive uninteresting. But it's surprising how well it aligns with the two resources and a number of other good hits in the area. And so I put this up because it's part of our, part of the exploration mix. The other thing pertinent to this talk today was the total rare earths, including yttrium oxide. There's some quite decent numbers. That was mostly only the Florence Ball South was actually had assays for some of the rare earths. Not so much Florence Ball North, or very little, not so much that they could do anything with that, but there were some numbers put around the Florence Ball South, in the kind of region of kind of 0.13, 0.14 from what I can remember. So again, emphasizes the potential for some of these mineral systems where very little of that type of analysis took place. And I can understand that at the time, going back 15 years ago, you didn't willy-nilly assay everything because it would cost you a damn fortune. Whereas nowadays, with ICP, you can get out there and assay a big suite of elements, which is incredible. So it's been a massive change in the period that I've been exploring since 1984 when I first arrived in Australia. So today, so you shouldn't certainly look at old data sets and go, why the hell didn't they do that? Because I mean, quite frankly, almost no one did. So, but it is a big, people touched on it today, big opportunity to go back, get pulps out and re-assay to see what's associated with these systems. And I think Rick, you said about the uranium, that association. So there are link ups with these things, the focusing of fluids, mineral fluids generally into these systems is very interesting. So there's lots of excitement here with this project. The go deep thing, well, look, I've touched on it. This was just one slide. I didn't change it. It's not brilliant, I'm afraid, and I don't think, well, you probably can read a few of those. There's some reasonable numbers in there, but the point is that, as I touched on earlier, these things have great depth extent. They don't generally just miraculously stop at 100 meters or something. So anyone that's worked on any of the ISA systems, whether they be IACG systems as they're referred to, or like the ISA style, or any of the others, they usually have good depth potential. And certainly we see a lot of open space, for want of a better expression, below these all these mineral systems. And I think, you know, some will prove to be, you know, pretty exciting to, you know, chase up in future, and a lot of work there to do. But it's not an immediate priority, but it's certainly something that we see as being a way of also having a project out there that has longevity. If you're going to put a lot of effort into the capital costs of putting these projects into areas, doing it in an environmentally friendly way so that everyone's happy, you really want these things to have a decent lifespan. I think that's pretty boring, actually. I mean, we're doing all that. We're onto it. Should cut that one out there. Yeah, look, in terms of the flow sheet, this is I don't think there's too many minors here, but you know, this is how we will, you know, view you know, crushing this stuff up, putting it on heaps and chucking some acid on it in the first place. So that's that. I think that's pretty much it. Hamish, there, myself, yeah, we're certainly excited. Next time I come back, maybe I can dive a bit more into more rocks, or maybe I'll let Matt.
Thanks, Dan. That was great. Hang around for questions. So anybody got anything for Dan or Matt?
Yeah, Matt.
Matt, you can delegate now. Paul has a question.
Thanks, Dan. That's great. That's really interesting. Obviously the focus is the SXEW for immediate production.
Yeah.
That looks pretty nice. 200. Was I reading that right? 200 meters of down to the oxide, basically. Is that sort of
it varies
common?
Yeah. It varies for deposit. Greenmount. The core I looked at Greenmount with Gojam was, you know, I think the hole I was looking at, which was one they did 2 or 3 years ago, it was all oxide down to 130 odd meters. Lots of chalcocite, little, certainly malachite, etc. But yeah, well, it struck me that there was quite a lot of leaching in that, and that's quite interesting. One that knows about the Black Fall area, that's well renowned for having a deep leached kind of profile. But yeah, look, yes, lots of copper.
Yep, that's
currently
great.
in the current resources.
Thanks.
No, that's fine.
Any more questions for Dan? When are you listing?
Well, the market's interesting at the moment. So copper prices come off a lot if anyone's watching copper, but I mean, we think it's got a very strong future. I mean, it's very hard to see how people are going to meet the demand side going forward easily. And as I've probably alluded to, the fact is that people have to go back to some of these older mineral systems. They'll be accepting lower grades, and they're also having to be going deeper. So none of that's easy, particularly with a kind of environment where, environment's probably the wrong word, but in a climate of where people's expectations are that you've got to do these things very well and make them, you know, environmentally sound, etc. That puts pressure on the costs. And I think we'll see that copper price probably continue to kind of stay stable or again move forward. But yeah, we'll see. But as for IPO time, well, we're still aiming. We'd like to do it this year, but I think we've just got, you know, more than one eye on the market.
Good news. Excellent. Are there any questions online? No. You've got one red dot in the chat there. All right.
Just lots of talk about sand.
Oh, really? Okay.
Too much
Excellent. Thank you very much, Dan. Really appreciate it. Okay, next up, we've got Michael Rodder from Caldera Technology, or is it Caldera Analytics? Caldera Analytics, who's going to talk about some of the deep learning basement interpretation of the Mount Isa region, which is outcomes from one of our CEI projects under round 5. So we'll get it all set up and away we'll go.
No, it should be good. So, yep. Second, yeah. Okay, everyone. So thanks for coming to my talk. My name is Michael Rodder from my company Caldera Analytics. And so I'll be going over the recently completed basement interpretation project that I did. Spoilers. Yeah. So this was part of the recent round 5 for the Collaborative Exploration Initiative. And it was done for Strategic Energy Resources, who have 2 projects in the ISA region. So just a quick background on Strategic Energy Resources, or SER. So 2 projects, both in the Western and Eastern Succession, Canobi and ISA North. And both of them pretty similar characteristics in there's very limited drilling, so limited understanding, and a lot of cover. So a lot of the drill holes have been hitting about 400 to 500 meters of cover. So pretty tough terrain to explore in, and of course, because it's undercover, there is limited tools to make decisions with. So that brings us into the motivation for bringing in a machine learning or data-driven way of interpreting the basement. Firstly, of course, machine learning is a data-driven approach. So it's really complementary to the existing expert-driven approach, where you're hoping with your data-driven methods that there is less bias in its outputs. Secondly, by structuring what we actually produce as outputs from the deep learning model, we can come up with a way to help IOCG exploration in the area. Thirdly, with model outputs, we can quantify the uncertainty of our interpretations with our probabilistic outputs. So traditionally, if you're interpreting an area, you might be like, there's this lithology or stratigraphy in the region, but with a probabilistic output, our model can say 70% chance of lithology A, but there is a risk that there's a lithology B in the area. And of course, probably one of the biggest strengths of machine learning is you get fast updates with new data. So there is a lot of drilling and exploration going on in this area. New geophysical data being collected. Is that all right? Sorry. Yeah. Yeah, lots of new data being collected. So what you can do once you get new results or geophysical data, you just plug it back into the model, regenerate your interpretations, and then hit the ground running with your new interps. So the general framework with how you use deep learning to come up with model predictions. Firstly, we're just using gravity and magnetics as inputs into our interp. So this is obviously because the projects are undercover, so it is the most applicable inputs that work out there. And what we do, if we want to generate a prediction in an area, we pick that area, we take the surrounding 4.8 kilometers of geophysics, of gravity and magnetics to inform the prediction. So we put those inputs into the model, and where the output is the lithology or lithologies at the center of the input image responsible for the geophysical signature. So that's, it's really important to highlight that if we're trying to predict lithologies, they must show up in gravity or magnetics. So that needs to be factored in, which we'll touch on later. So I said the word deep learning, and I like to manage a bit of the expectations. A lot of media and fancy reports, these pictures of robots show up, and it's my pet hate when deep learning is talked about. Creates a lot of hype and creates this expectation that deep learning is going to come in and replace us all and solve everything. And then people, it burns a lot of bridges when it doesn't do that. Deep learning in this case, it's nothing special. It's just a form of machine learning model that can handle two-dimensional inputs and figure out automatically what's important. They're really annoying to use. You need a lot of training data and they're quite clunky. So there's nothing special about them. So if you have any pictures of robots in your head when you see deep learning, don't. So this slide I could probably talk about now on it. And hopefully by the end of this slide, you're nodding in agreement, or you might be burning me at the stake after. So to come up with a data-driven approach or a machine learning model, you need to actually have a bunch of historical training data or your known outcomes. And so when you train the model, you load up all your known outcomes, and then you train the model to learn the relationship between your inputs and your known outcome. And so this collection is called your training data set. In this case, that image on the right, in the Mount Isa region, each dot point corresponds to a point where I've gone and annotated, this lithology is, there's a lithology that is responsible for the geophysical signature of that region. It's sourced mainly from two categories. Firstly, once you're in the area where there's basement exposed, you can use map-solid geology if it is corresponding to the geophysics. But once you go out and cover, you can only use drilling that has intersected enough of the basement so that you can reliably say, yes, this lithology is responsible. So in terms of what you can actually predict, you can't go out and predict 300 different subcategories of lithologies. Firstly, we're only using gravity and magnetics. And secondly, we are optimizing the model to work under a lot of cover. So there is a real realistic constraint in what you can predict. So we roll them up into 6 high-level lithological groups. The ones in the blue are there. Generally, our focus was on things that matter towards the magnetite IOCG exploration process. So we had felsic tematic intrusers. We took out tematic dikes just because they're so distinct. And then we had significant amounts of metamorphic magnetite, hydrothermal magnetite, which obviously that's the real business value for a lot of explorers. And then we had this big catch-all group, remaining/other. So this is a big group that had volcanics and metasediments, and most of you will now think, okay, that's insane. You're basically lumping in most rocks into that one group, and that's true. But there was a real reason why. Firstly, we talked about we're building the model to work in areas undercover. And so our training data set comes from 50 years of open file data with different logging standards, different assay methods, different understanding at the time of drilling. So you have to apply resources to clean up your data into an appropriate machine learning friendly format. So our idea is if we got a fixed resource, we're going to have to go through all this open file historical data and convert it into categories that matter for explorers. So we're not going to be spending resources splitting hairs over different grades of metasediments. Ideally, in the future, that should be broken out. Hematite is in orange because it's technically possible, but obviously this was an R&D project, and we're focusing on Mount Isa. And red, any lithologies related to IFCG style mineralization, because we're only using gravity and magnetics, we can't really use that. So we ignore any hematite and IFCG style lithologies when we calcium, so the model never learns from them. So that's just showing the training data set from the perspective of the felsic intrusives, where any red dot, the machine learning model learns, don't predict felsics there. Any green dots predict felsics there. So a big part of the R&D project was actually testing what's called self-supervised learning. So I was just talking about how we need the inputs and we need a known outcome for the model to learn. But self-supervised learning, or SSL, involves training these machine learning models where you don't actually know the outcome. So if you have a big stack of inputs and you haven't gone and annotated what is occurring there, you can use them to warm up a machine learning model. And then you use that warmed up model downstream when you are actually using training data sets. It's kind of kicked off in the past 3-4 years, and it's making a lot of gains where traditionally you can get just as good results with 5% of the training data size. And like a lot of great things in deep learning, the intuition just comes from how we learn as humans. So in this case, think back to when we're toddlers, you get given a picture book and it's like match the animals or match similar animals, but we don't explicitly get told what animals they are. We just learn to group up the animals with different or like similar ears or tails. So, you know, when I read about self-supervised learning, I'm like, what domain has an enormous amount of unlinked data? And mineral exploration in Australia is the perfect application of this self-supervised learning. So the idea is traditionally deep learning models need a lot of training data, far more than what's available, because we can't spend $10 billion pattern drilling to get hundreds of thousands of training points. So can we use these techniques to get just as good performance with much smaller training data sets? So how the model was trained is you start a deep learning model, you warm it up on the gravity and magnetics of Australia so it gets familiar with what is geophysics. Then you take it and you apply it to you fine tune it on a highly curated training data set where it's much smaller, but the data quality is tip top. So just to quickly touch upon that, I dug through a lot of reports. I went through each training data point to make sure it's correct, and we employed a contract geo, Richardson, formerly of Minotaur, to go through and make sure a lot of the categorizations were really correct. And there's talk about uplifting the ground gravity database, and there's about 70 to 100,000 points, but as a latest check, I've found 110,000 and I haven't even finished. So there's a lot of data went into making sure this is correct. So we take that fine-tuned model and then we apply it to the ICE North and Kenobi projects. So I won't bore you with how I validated these results, because I'll put you all to sleep, but went through a pretty comprehensive testing framework, and these self-supervised learning, deep learning models were the superior choice when compared to deep learning models without self-supervised learning and traditional machine learning models like random forest. So results. So we got 4 images here. First one on the left is your mag input, your grav input, and I'll just say this is, we don't have time to go through the Kenobi, so we'll just touch upon ISO North. Third image is the model probability for hydrothermal magnetite, where dark areas correspond to low predictions, warmer yellow areas is high probability of hydrothermal magnetite. Uncertainty on the right is measuring the model confidence. So, or in this case, I've said uncertainty, where dark areas, the model is very confident or more certain in its prediction. And then yellow areas, the model is a bit more shakier, it has less certainty in its prediction. So just to superficially go over these, firstly, each kind of predicted area does correspond to, you know, traditionally more bullseye shaped magnetic anomalies. It hasn't just simply gone anytime there's a higher magnetic response, there's hydrothermal magnetite. So metamorphic magnetite, there's no real strong lithology area predicted for this lithological group. But you see running through the ICE North project, there's like a faint 20%, 30% chance. And when you look at what that corresponds to, there is a linear magnetic trend running through the project. And so this is making sense that you drill there, the model thinks there is a low risk that you might be hitting maybe a magnetite vanadine formation instead. So now that we're not talking about the money maker stuff, we can expand it out. So felsic intrusives, there's a really strong felsic intrusive predictor there that's never been drilled. And when you look at what it corresponds to, classic, circular, gravity and mag lobe. And then there, although the model uncertainty does light up a bit for that. And then there's a few other less probable, but still strongly predicted felsic intrusives, one of which was confirmed by recent drilling. Mafic intrusives. So firstly, it's corresponding to high gravity anomalies, which makes sense. So this one here, that's actually was, I think, drilled, and under what we categorize as mafic intrusive, the model does get that right, even though it wasn't used as training data, but it does fail down here when we get to the Peralkaline-Leichhardt belt, where the model's never been trained. And as far as I know, there's no interpreted mafic intrusives there, so it does fall down there. And no surprises when we check out that other / remaining group, which has most rocks, it is predicting a lot of it. So the best way to validate how your machine learning models go is actually on new data that's generated after you've finished modeling. So we were lucky in that a company that had the neighboring tenements to Ice and North released 2 drill hole results to the ASX. So, let's plug that into the model. Does the model get it right? So the model has never seen this, and it was finalized before we even knew these drilling results. So disclaimer, I'm only operating on the ASX announcement. The company would have had more data, done more studies. So this is really not commentary on, those drilling positions, but more just how does the model go? So 2 drill holes, this one down here intersected 45 meters of hydrothermal ironstone breccia within a felsic volcanic. So we assume that, the label under our framework come up as, it's a bit hard to see, apologies, but it comes up as hydrothermal magnetite. And our model says 60% chance of hydrothermal magnetite with very high confidence. And it's also getting the background felsic volcanics at 55% chance of high confidence. Drill hole number 2 is far more interesting. The model says, firstly, it intersected a felsic to intermediate intrusive rock. And the model, it's a bit hard to say what the label would be based on just that blurb, but felsic intrusive, maybe mafic intrusive, depending on the intersection. And so the model says 34% chance of hydrothermal mag with very low confidence, so it's very uncertain. 40% chance of other, which they got that wrong technically, and then 36% chance of felsic intrusive with very low confidence too. So to me, that's a really powerful result in that the model is actually saying, I don't know. It's a very strange area, and it's basically the uncertainty of the prediction is really high. So, if I got the result, maybe I'd be like, collect more data or focus more. So top-down 2-dimensional perspective of the hydrothermal magnetite predictions. That's drill hole number 1, that's drill hole number 2, showing the uncertainty with the red line, the drill hole trace. Drill hole 1, the models say where it drilled, very high confidence in its prediction. Drill hole number 2 is just the entire region is very uncertain. The model just doesn't know. So you can use these model outputs to come up with an independent data-driven way of ranking targets. So this is pretty simple. You're just using the hydromag probability and uncertainty, and then some traditional false positives that have been hit, like mafic intrusives, to come up with a quantitative way. And then this can be plugged in complementary to existing rankings. And then Kenobi, we haven't really talked about it. Apologies, once again, it's a bit hard to see, but the model is lighting up a lot of hydrothermal magnetite targets to the southern end of the project that there's never been any drilling in this area. So it'll be interesting to see what happens with those. Okay, summarize. A lot of this project was about self-supervised learning, and it's a great result that it works and allows you to use deep learning models, which traditionally you need way too much data than what is available in geoscience. So it allows, with these techniques, you can use these powerful models, but you can focus on smaller scale data quality or smaller size training data sets. Powerful complementary tool for magnetite-based IFCG targeting in its current form. Of course, I've only applied it to Ice North and Kenobi, but the speed and scaling, you could generate for all those areas on that Northern Australian Craton IOCG mineral systems model and see how the expert-driven and data-driven approaches line up. And of course, I'd like to thank SER, so Dave's in the audience, so thanks for trying these new methods. And of course, GSQ Queensland Government, this wouldn't have been possible without the CEI grant. So thanks a lot for that. And lastly, any questions, if you want me to bore you with a much longer version, feel free to reach out to me. And if you're interested in applying these models to your own project, I think machine learning, when you actually focus on the fundamentals, make sure data quality is right, make sure it's grounding in actual scientific theory, it can add a lot of value. So reach out to me via email or catch me afterwards, and thanks for listening.
Thanks, Michael. Have we got any questions? Yes, Karen.
Thanks, Michael. That was great. One of your final comments was that you could do this on a much larger scale. Is it really feasible time-wise, rock type-wise? How broad can we throw it out there?
So, in the model's current form, it's quite province agnostic. So it doesn't really focus on certain stratigraphies, especially because of that big catch-all group. So it is definitely, you can apply it elsewhere. Right now, the training data set, most of it does come from Mount Isa. So let's say if you saw that mineral systems model and you see Georgetown area coming up, or Tennant Creek, you would want to go through the drilling in that area and add it into the training data set. But yeah, time-wise, 1 day, 2 days max to generate for half of Australia, so very feasible.
Thanks, Michael. We've got a question online. Have you tried comparing the hydrothermal magnetite prediction results with the GA inversion results for magnetite and hematite?
Not yet.
The person who's asking is not sure if the GA layer covers the area, but I thought it was pretty extensive. Yeah.
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 Yeah, very different scale. Any more questions? Rick's got a question.
Thanks, Michael. That was really interesting. I'm going to have to go away and look. What do you the new form of supervised learning? Because we've got a few people who've been doing a lot of training, and it's a pain in the proverbial. But my question is, and again, I don't know if there's an answer to this, but the one thing about using gravity and magnetics is that things that are deeper, an identical thing that's deeper and shallower looks completely different in the data. And yeah, I guess it's one of many things that make it harder to do this sort of approach. But do you think there's any way to deal with that? I've sort of tried some things, but the fact that if you know what if you've got a hydrothermal magnetite in a drill hole that's at 50 meters, it's very different to hydrothermal magnetite in a drill hole with identical magnetic susceptibility at 600 meters. Is going to be different in the data.
Yeah, so with how we validate the model, what the model is validated on is quite a broad selection of lots of different, let's say if we're just focusing on hydrothermal magnetite intersections, it's quite a broad selection, so it's not biased in one area. It takes a lot of the hydrothermal stuff that's intersected in the inlier and out at depth. And secondly, there's methods for, obviously, I think I said this last time I presented this to you, but as you train the model, you're always altering it a little bit. So you're kind of rotating like your input training data. So the model learns, you know, the Ernest Henry hydrothermal magnetite, this is what it looks like, rotated a bit. But then you start applying like upper continuations. So the model, when it's trained, sees each training point hundreds up to thousands of times. And each time you randomly change your geophysics a bit. So you can take training data from near surface and, you know, apply geophysical transformations to help it learn what those lithological groups look quite deeper. You can't really do it in reverse, obviously. But there's also, you know, that's kind of getting closer to the fact that you would expect your uncertainty of what you can actually predict once you get really deep to just, you can't get around that. So that the metamorphic prediction running through ice and north, that was a faint 20–30% probability. And I think that's when I look at the predictions, when I compared it to, I think I had it go at like Star and near there. The model is far more confident in its predictions out near the surface, and it gets more lower, less certain as you go deep. And that's just, I feel that's reality. Like at 500 meters depth, is it actually possible to separate out a lot of morphological groups, or is the answer, the best numerical answer, saying it's quite an even split? Collect different data maybe to help split that out, or you just have to drill?
Thanks, Michael. That was good. All right. Next up, we've got Matt Price from Sunshine Gold, who's going to talk about exploration of critical minerals in the Ravenswood batholith.
All right, thank you very much for having us today. Yeah, so this talk's entitled Exploration for Critical Minerals in the Ravenswood Batholith. And really just wanted to use the talk as a bit of a very brief summary of Ravenswood geology, touch on very lightly on the deposit types that we expect to see out there, and what a junior explorer like Sunshine Gold is doing to explore for those commodities out of Ravenswood. So just a bit of a background on the company. So we're Townsville-based junior explorer. We've been listed for about 18–19 months, and we've got 4 projects all in Queensland. And really, for someone sort of new to the Ravenswood area, we sort of think that it's got the potential, I suppose, to be a bit of a game changer for the company. So as you know, all you guys are going to know, the batholith is situated in the Charter Towers province, and there's 6,000 square kilometres that it encompasses. And as someone very new to Ravenswood, I suppose, myself at least, I was very surprised how underexplored it is, particularly with the drill bit. And this is despite being an area that produced over 20 million ounces of gold, mainly with Ravenswood, Charters Towers, Mount Latham, Mount Wright, and so on, and a vast amount of silver as well. But it's also prospective for copper and moly, lead, zinc, and possibly even a few other things such as rare earths as well, as we'll see. So just to give a bit of a summary on about where we're located and the geology in the area. So the older rocks, I suppose, are the sediments, Cambrian to early Ordovician, of the 70-mile range group. Is primarily outcrop on the southern side of the batholith.
The first phase of the intrusive history was of early to middle Ordovician, primarily granitic rocks. Those tend to outcrop in the north, I suppose, from where we are at least. And some of those can be fairly strained and recrystallized as well due to subsequent deformational events. The mid-Silurian to early Devonian intrusives, primarily granodiorites, tonalites, and the like. The area. And finally, the final stage was late Carboniferous through to the Permian, plutonic through to volcanic rocks. And again, these are, I suppose, associated with mineralization in some of the places as well, such as Ravenswood, right? Only a small percent of outcrop in that area, it's around 6% or so. But notably as well, we do have two of these larger outcrops of the Permo-Carb, the Buri Igneous Complex and the Tugger Range Igneous Complex, outcropping on some of our tenure. And finally, there's sediments around as well. In terms of just a very generic structural history, four main stages in the literature. The first sort of owing to ductile deformation structures such as Mosgadi shear zone. Later, the second event, also brittle deformation structures. A number of those are reactivated during mineralization events. Timing in terms of gold, Charters Towers, I think it's dated around 14 of Silurian. Whereas Ravenswood and Mount White more so around 3 or 5 Permo-Carb age. Oh, and I should say as well that potentially porphyry mineralization around the Silurian as well. So where are Trundle located? We're predominantly located on the east side of the batholith, so very close to the Ravenswood gold mine. Mount Wright, so we sort of use a lot of those deposit models, I suppose, from that neck of the woods while we're exploring our tenure. But as well as being prospective for gold and silver, we also do have exposure for copper and moly, porphyry style deposits, as well as a few other things as well. So we only picked up this tenure just over 12 months ago, so we're very new to the area. But I suppose the first thing that we did was really lean on the open file database a fair bit, and what was available in terms of geophysics, geochemistry, and the like. This is a little geological map that we made up on some of our tenure. That's purely based on magnetics that was available open file. And here is that open file magnetics image. This is a composite of a number of different surveys that was reprocessed for us by SGC. It's an amazing cost when you think about how much you're going to use a data set like this. And yeah, we found it invaluable really for delineating different intrusions and structures, and coming up with geological ideas on structural offsets and all that sort of stuff. So I have a lot of fun with it. I usually have that open every day. In terms of the open file geochem data, again, we sort of relied on that a fair bit as well. We still do. As with any geochemical data, you have to ensure you do the background work to validate it. But certainly lots and lots of samples that we could lean on, particularly within our tenure, Dracorn area, and up through some of the copper prospects too.
But this map, I suppose, is quite a bit of a contrast, and it shows the open file drilling data. You know, this map tells me two things. One is obviously what Dom alluded to earlier, in the sense that there's a number of open file data that's missing from this database. Things that are just hard to register because they're so old. Things that have been done on mining leases, which we don't have access to, unfortunately. But even when we brought in all the data that was available to us from the open file, it really didn't change the picture that much, to be fair. And so the main thing is showing me that it's fairly underexplored with the drill bit. And that's the long and short of it. You know, I think we've averaged out at probably about 100 holes for about 600 square kilometers of tenure. And most of those are well below 100 meters hole depth as well. So what deposit styles are we looking for? This is obviously a very broad generalization here, but gold deposits such as what you see at Mount Wright, what you see at Ravenswood and Charters Towers and the like, I won't go into any detail on those today. The main two that we're currently exploring for, I'll go into a bit more detail on, is intrusion-related gold and silver, and also these porphyry style copper moly shows. And also there's potential as well to get some other base metals and some rare earths. So the intrusion-related targets are one we're having a look at in a bit of detail at the moment. This is a cross-section here of Mount Wright. Mount Wright, I think at its nearest point is about 7 kilometers from our tenure. Or probably even closer to its nearest point, actually. And these are generally hosted within their causative intrusions, within rhyolites, fractured to brecciated, and typically a permo-carb age. They're hosted with the gold tends to hang around with the marcasite and pyrite, so that's always a good pathfinder. What's notable, and with Mount Wright, I suppose, is that the main ore body was blind and didn't poke out at the surface, although there was a little satellite deposit called Mother Lode. But the chance of finding a blind deposit and knowing that there are blind deposits out in the Ravenswood area, so it's an encouragement for a junior explorer or any explorer that's coming into a new area where you know, lots of people have walked over the ground before you. You know, if there was something obvious poking out the ground, generally they would have found it, particularly if it's gold and silver. So it really gives us good sort of encouragement to go out and try and find some more of these sorts of things. Notably as well, Mount Wright was vertically zoned, so there's base metals, particularly lead and zinc, towards the surface, giving you a good soil anomaly, and also into you know, gold and the pyrite, and then pyrrhotite at depth. One of the targets that we're looking at in terms of the style, this style of mineralization is Wilbur's Hill, which just sits about here. And it sits on the periphery of this magnetic low, and that's a permo-carb intrusion known as the Bouri Igneous Complex. And Wilbur's Hill, we're very encouraged by what we're seeing on surface there. We are seeing the right type of rocks. We're seeing rhyolites. They're flow banded in places, brecciated in places. There are variable amounts of sulfides, predominantly pyrite. But it also has a good geochemistry on surface as well. So there's small amounts of gold anomalism. There's lead, zinc. There's also bismuth and tellurium and a few other things kicking around on the hill itself as well. So we were fortunate enough as well to explore for the gold and silver using a Titan IPMT survey. We got a partial funding for that through the CEI. That should be kicking off within the next week or two. And that'll cover pretty much from the south of Wilbur's Hill up to this area called Smiths. And it will hopefully,
we'll be able to delineate some high chargeability and conductivity zones that could be potentially below surface. Touch on the porphyry related story here. So this is an area that I think, in my opinion, probably needs a bit more due attention. It hasn't really been looked at in any detail since the 1960s. And yeah, I personally think it does hold fairly significant economic value. Yeah, I think with a bit more love, I think we can find something quite interesting here. So we've delineated, as it stands, about a 15-kilometre long corridor of porphyry targets, starting from Titov in the north and down to the bank in the south. And they sort of run along a northwesterly trend, I suppose, that's fairly common in that side of the batholith. We've got a few faults called the Podolsky fault going up through that way. You've got the Boreal igneous complex just out to the west, which sort of follows along the same trend. And we drilled one of these targets, Titov, up in the north there, in late 2021. It was an obvious target for us. There was some historical drilling that had some broad copper and moly intercepts, although they didn't assay for anything else. And also, it's on surface, it's a very obvious target. There's quartz veins popping out the ground, there's malachite, there's moly, all on surface there. There's a vegetation anomaly, there's nothing growing there. So it was an obvious one for us to do, and we managed to sort of validate some of the historical drilling numbers. We assayed for some other elements as well, such as silver and gold. Yeah, we tested a sort of a bit of a theory of a southerly dip, which seemed to work out reasonably well as well. So yeah, what we were seeing, I suppose, was granodiorite, I suppose, with varying amounts of copper moly disseminations. In the core of this southerly dipping structure, there's a lot of quartz, fairly big quartz veins with a cerussite halo. We are seeing enriched, locally enriched, I suppose, moly and chalcopyrite as well. And that's from one of those zones there. We did some preliminary met work, mainly so we could sort of, we have to report all our results, obviously, to the ASX. And we wanted to sort of see the sort of value that the moly is holding as well. And we got that allowed us to report a recoverable copper equivalent. So the best result was 66 meters at 2.1% copper equivalent. That's primarily just copper and moly, with a tiny bit of silver. So yeah, I think it's very encouraging, and we're just heading back there at the moment with the drill rig. I do think these targets do hold some value coming into the 21st century for sure. We also did a little IP survey over Titov, mainly to try and chase. There's a gold in soil anomaly up through here as well. And the main mineralized zone just runs up through here and did respond well to strong chargeability. So we've also extended the survey out to the west now as well. We're just waiting on the results for that. Open to the south as well, whether this is part of an edge effect, but we are going to follow up on that. Another target up through here is the bank. This is registered from basically historical reports. And this is soil geochemistry, 700 ppm copper anomaly surrounding a porphyry intrusion. That's only had minor drilling as of the 1970s. And those results are yet to be found. I'll only touch on these very, very briefly, but VHMS, there's potential for that in our tenure right to the south. This is a little prospect here called Bowerbird, and it just sits to the west of another prospect called Magpie, which is on a mining lease, separate mining lease. But we do have a good soil anomaly there for lead. And again, this area has never really been drilled apart from a few little spotty holes out to the east of the main anomaly. So Again, we would like to have a little look at that at some point as well. And finally, the last couple of slides I'll just talk about is potential for other elements, notably rare earths. We were supposed to drawn to this area initially, Elphinstone Creek, due to anomalous gold in stream sediment samples. We also noticed, as well as the previous operators, that there was elevated rare earths in some of these stream sediment samples as well, up to just over 2% total rare earth oxides. And this image that you're looking at here is a radiometric image, and the dotted line, potassium radiometrics, and the dotted line picks out an obvious separate intrusion called the Barabbas adamelite. And that's also visible on magnetics and other radiometrics as well. And we undertook a soil sampling program just in the north and sort of brought it down just into the top of the adamelite. And as you can see with the rare earth elements, it does highlight that pretty well. You can pretty much pick out the contact based on rare earth content. So soils generally go in between 400, I suppose, to 800 ppm, and increasing in places over 1,000 ppm. We were fortunate enough as well to get another CEI to continue the soil sampling over this intrusion, just to see whether there's any areas of enrichment or whether it's just a weakly elevated broad intrusion that is just enriched in soils. So we're actually almost finished that survey at the moment. So we'll have that report out in the CEI Round 6. So yeah, this is basically just a snapshot of what Sunshine Gold are doing, exploring for these various elements in Ravenswood. I think it's highly underexplored for such a well-endowed region, and that gives us opportunity, I suppose, as a junior explorer through there. The open file data sets have been really useful for us, and as well as the geological models that have been built based on the mines around that area. But we would like to try and think outside the box in some places as well. And that may even be just drilling a couple of holes in an area that hasn't been done before. So that's about it. Thank you.
Thanks, Matt. Any questions? Johan.
Thanks, Matt. The question is from the pictures from the teeth of the molybdenite.
Yep.
They seem to look like they are veins within a quartz vein or something like that.
Yep.
Did you measure their orientation? Is the orientation of the molybdenite veins the same with the orientation of the quartz veins?
Yes, so they're dipping towards the southeast, and yeah, they seem to be correlate to the quartz veins that they're hosted in. That's right. You also do get molybdenite in disseminations on the outside of that as well, but certainly with the veins that you see there, they seem to be sort of almost embedded within the veins themselves.
There's a couple more questions, Stu.
Thanks, Matt. With regard to the stream seds in the rare earths,
Yep.
How were they taken?
I believe they were done 80 mesh off the top of my head, and fairly recently, so that was 2016, 2017. But yeah, they were stream sediment samples. They were taken as basically a soil sample, I guess.
So any idea what the source of that is?
I suppose looking at the soils that we've taken since then, and the fact that you can sort of almost draw a line between the adamelite and the depleted zone, you have to assume that the adamelite is the source. I suppose from an economic standpoint, whether there's any areas within that, like a zonation or anything like that within that, I don't know at this stage. We're still waiting on more results, but yeah, you'd have to assume that big intrusion is the source there.
Have you looked into which minerals host the REs?
We're currently doing that at the moment. So we've taken a number of samples and we've sent them in transit to ANU at the moment. So yeah, your mate Ross is going to have a little look for us.
Any more questions in the room? Do we have any online? Excellent. All right, you're free, Matt. Thank you.
Thank you.
And yes, so unfortunately, we did have some COVID casualties in the latter part of the program, but we knew that this would happen. It's the way things are at the moment. So we did prepare a couple of spare presentations. So huge thank you to Dan Killen, who's going to stand up next from GSQ for being one of our backups. So it's sort of a lot of work to do to prepare a talk and then possibly not give it. So I really appreciate that. He's going to talk about some of the work that he's been doing on spectral data, high logger data at the Mount Carbine deposit.
Okay, thanks for that. The purpose of this talk really, it's not really a comprehensive look at Mount Carbine. It's a look at one particular vein system that occurs there. But what it does give a good look at is what we use high logger for at GSQ and some of the things that high logger can do that you may or may not be aware of. Okay, so just in summary, yeah, the vein system we looked at there was Talus. Well, that's the vein system I looked at. There are some other systems there too that others have looked at. But so the summary here is that, yeah, so there's deep and shallow, and there's moderate amounts of tungsten mineralization visible in veins deep. Both scheelite and wolframite can be seen. Around the veins, there's mineral assemblages that tend to be tourmaline, iron-rich tourmaline, biotite, white mica. Sometimes the tourmaline might be missing where the biotite is really prevalent. In the shallow, you see smaller amounts of tungsten mineralization. Some of that's visible, and it's most likely wolframite. You also see white mica, chlorite common. Some iron tourmaline may be present, but it's seemingly less of it. Small veins, yeah, have mostly white mica and chlorite proximal to them. Biotite is notably less common in close proximity to those veins. Some tungsten minerals are actually present in high enough amounts to be seen in the thermal infrared region. So the tungsten minerals that we look at in this aren't actually in the spectral geologist library, but they do have distinct signatures. And we've been able to measure those, and they probably will be in future libraries. So the spectra can be matched using AUX matching. So AUX matching is just bringing in the spectra and using it in the library, just like you would for a mineral that already exists in the library. The auxiliary match technique has been used for other drill cores, such as Wolfram Camp, where wolframite crystals are sometimes significantly big enough to be detected spectrally. Okay, that's a high level summary screen. So at the top there, you've got your shortwave infrared beam data, and at the bottom, you've got your thermal infrared or TIR beam data. I think it's to say there, the bin size there is about 0.5 meter. So what we have here, so what I've done here is these are just some images of the veins, and corresponding to that is the associated high logger data. So you can see that that's the vein we're looking at there, and there's the high logger data over here. So you've got your shortwave infrared on this side, thermal infrared on that side. Put a drill core in there. So this is downhole. It's the same just here. You can see there's some mineralization just out. Some mineralization here is actually just outside the line scan. Okay. Some mineralization within the core. Yeah, okay. So this is a shearite spectra. You can actually see the shearite spectra appearing. That part of it there is shearite. We'll get into that in a little bit more detail. Okay, so there was a hand sample that we managed to get from Mount Carbine. I ran that through the high logger. It was a big enough sample that I was able to run that through the high logger and not get any interference from quartz or anything else. So what we're seeing there is pretty much pretty well close to a pure shearite spectra. Okay, so there's an example of shearite occurring in a vein at Mount Carbine. And you can see, because shearite's not in the library, the thermal infrared PSA is actually correctly identifying quartz, but then it's also trying to throw in another mineral there. It's trying to throw in goethite, because goethite just happens to have some features out in that same area out to the far right there. So this is AUX matching. So this is just an example of me pulling that measured shearite spectra into the library and displaying it in a way that you would display normal minerals that are in the library, like say chloride or quartz. Okay, this is just another summary screen from a different Mount Carbine drill core. You can see there's a little bit of the drill core missing there, so that's the dark bit in the middle. Okay, so what have we got in the vein? Vein surrounded. So this is just some more observations based on the hyperspectral data. So here in this drill core, we've actually got a vein surrounded by chlorite, white mica, tourmaline. There's some microcline there as well. Visibly, there is a little bit of scheelite. Some of it just outside of the line scan, and in the bottom one there, we've got some more visible mineralization, vein surrounded by chlorite, white mica, tourmaline, and some biotite. Okay, so this is looking more at the specific spectra for wolframite and scheelite. So the wolframite we've got there, that was actually taken from Wolfram Camp, and that was acquired using an Agilent handheld spectrometer down at CSIRO in Sydney. The bottom sample is the scheelite that we took from our hand specimen under the high logger, and that's from Mount Carbine. So what you notice about the measured sample there is that out here it's kicking up. So that's very, very much similar to wolframite where it's kicking up, but it's also quite broad. So it's quite broad. So there's such broad like scheelite there. So what we're probably looking at there is a mixture. So what have I said there? Yeah, so it's wolframite with possibly some scheelite due to the broad nature of the feature occurring between 11,380 and 12,150 nanometers. So right in the middle of that, you've actually got a quartz. That's a quartz feature, but it's a little bit distorted by the presence of scheelite. Okay, so here's another example. We seem to be recording scheelite again. Not quite in as much abundance as some of the previous slides, but the distinct horn feature can be seen around the 11,300. Up here, there's the horn feature, and down here is the sample comparison. So we can see the horn feature. We can see the quartz as well, because it's correctly identifying quite a lot of quartz there. So that's the main quartz feature, and out here is the secondary quartz feature. But what we're not seeing here is we're not seeing this kick up at the end there. So there's probably little, if any, wolframite there. So what you're probably looking at there is mostly scheelite. And in this area, the vein's surrounded by mostly chlorite, white mica, and iron tourmaline. So this is another summary screen from another Mount Carbine drill core. This is in the shallow part of the Talus vein system. And what we're seeing here is quite a good tourmaline signature. So in the shortwave infrared, that is a very distinctive tourmaline signature where you've got the two features here and this shoulder here as well as coming down like that. And over here, it's a pretty good match as well. So you've also got some chlorite and white mica surrounding that vein. Here's yet another summary screen. This up here actually shows where the tourmaline, that's tourmaline. So it's quite a lot of it around. So here there's a very subtle, however, a slight rise can be seen after the 11,000. Was it the 11,000 nanometers? So yeah, there's a very subtle hint here of mineralization. Now the high base level reflectance after that set, before a little bit before as well, but after that secondary quartz feature at around 12,500 to 12,800 nanometers is probably indicative of wolframite because it does seem to be kicking up a little bit there. Here's just some other images of some of the veins that are occurring in that Talus shallow area. You can see that they vary a bit in size. So other observations I made using the spectral data is that the carbonates are overwhelmingly calcite. The tourmalines tend to be iron tourmaline. Amphiboles can be present, but maybe more prominent in some places and absent in others. Microcline appears to be the dominant potassium feldspar, and the dark mica is overwhelmingly biotite. There's a fair bit of chlorite around, but most of that is iron or iron magnesium chlorite. There doesn't seem to be much at the magnesium end. The veins of the Talus deep system seem to exhibit more mineralization, both visibly and spectrally, than those of the shallow type. Some scheelite from Mount Carbine does exhibit signs of light rare earth elements that can be observed in the visible and near infrared region. So if we go to that, so this here is actually the visible, near infrared and shortwave infrared all as one. This end of it here is the visible and near infrared region. So these distinctive features that occur in the visible and near infrared region are actually indicative of rare earth elements. Now, they're probably light rare earth elements, and I can't say exactly which one based on that, but it's also interesting how that works because normally with most spectral data that we look at, it's vibrations and bending and stretching of molecules. So when we're looking at the shortwave infrared and thermal infrared, you're actually looking at the vibrations or bending and stretching of the molecules that give you the spectral signatures. But what's actually happening here is the electrons are jumping shells, and it gives you these very distinct sharp features. So that's some sort of rare earth element. I'm not sure if people knew that high level could see rare earth elements, but sometimes it can. And that's it.
Thank you, Dan. Helen's just had to step out for a moment, so I am looking for questions from the floor.
Thanks for the presentation. My question is, this type of work is probably really good to be automated in the sense like the previous presentation with deep learning, because it deals with spectra, with peaks, with dips and so on, and can be probably quite readily read by a computer and speed up a result. Is there any work trying to automate this type of process?
People are looking into it, particularly with domaining, I understand. Recently, there was a presentation about this, but unfortunately, I missed that. I was sick. But people are definitely looking into applying machine learning and to this sort of data.
All right, thank you. Any other questions? What about online? Anything there? Do you have a question from Emma?
Thanks, Dan. I was just wondering, so are you saying the light rare earths are actually substituting into the scheelite? You can actually figure out which mineral it's sitting in from.
Yeah, well, there would be some substitution going on there. The paper that I looked, the paper where I got this information about the rare earth elements from actually looks more at things like monazite and alanites.
Oh, okay.
But it appears that you can see it in the scheelite as well.
Oh, that's really cool. Thank you.
All right, unless there's any more questions. Doesn't look like it. I'm not sure who's next. Vance Kelly. All right, thank you very much, Dan. And our next speaker is Vance Kelly.
Very good. All right, afternoon all. I'm the man who needs no introduction because I don't get an introduction. Thankfully, it's on the screen here. I'm the principal data manager. I'm a lapsed petroleum geologist, so I know nothing about minerals. So if you throw me a minerals question, I'm just walking out the room. So we're taking a big step to the right here. I'm going to talk about the data portals. This is not about mineral systems. This is about data systems. It's about a lot of the things that the people in here will probably find a little bit esoteric, perhaps. Let's go on. Now, I'm in a room full of minerals explorers. So why do we care about the fact that we're upgrading a couple of data portals that we upgraded recently? Now, there's a fairly simple answer to that. There's a statistic out which keeps cropping up again and again about our data projects taking up to 80% of our time just cleaning the data. So this has been a common theme that has recurred throughout this day. Everyone keeps coming up here and saying, we've had a problem with historical data. There's tons of information out there. It's not in a format we can use. So we're on this continual journey to improve our data environment. That's both the way we get data in and the way we serve it out again. So there's a lot going on in this space. So back last year, we took the opportunity to review a bunch of the regulation, the applications, the way the data is reported to us, and we identified a number of opportunities to improve it for both us and for industry. Or I should say that this is, I'm gonna go back a step. Sorry. We have two portals, one of which has been illustriously, or very well illustrated by my colleagues today, pointing to the various open data portal links that you've used in the workshop and to all the wonderful publications that I've put out detailing some amazing work. The other side of this is the lodgement portal where we receive data in. Two different things, all part of a big, nice ecosystem. I'll talk to the open data portal a bit later. The lodgement portal, though, has some opportunities. Relies on a lot of unstructured PDF reports, and that includes data buried in PDF reports. It's not data as data. So again, we've had a lot of people digging through old historical reports, pulling out data, trying to tabularize it, put it into their own systems, which, let's face it, is less than ideal. We found there has been some inconsistent understanding of the requirements, so we're taking the opportunities to tighten that up as well. Again, consistent data. And that's kind of led to some variable adherence to different data standards that we've put in place. Lots of double handling of data, lots of manual handling of data where people take stuff out of databases, they shove it into a spreadsheet, they throw it through some tools to put into another spreadsheet, to send it to us to go into another database. Again, lots of room for optimization. And that means that there's not a lot of time left to actually do anything. So much time is spent trying to validate data that you don't actually do cool stuff. So the geoscientists aren't doing geoscience, and the data scientists aren't doing data scientists. We're spending most of our time trawling. So what we've done is we've started small with just the production and sales statistics for coal, minerals, and extractors. Now, I know this isn't the gig for everyone in the room. I know people don't really care, let's be honest. But really, this is about establishing a framework that we're going to roll out across a broader system. The production and sales statistics for coal, as thankfully I have some gentlemen in the room from the Minerals Hub have helped me extensively with. It's a relatively well-known data set, so the variables are fairly controlled. It's not as complex as the geochemistry data. We kind of know what we're dealing with, so it's a bite-sized chunk that we can get across the line. Proves that we can do it, puts in place the framework, we can expand it out later on. But essentially what we've done is, first step, standardize some templates. So it's just simple Excel and CSV formats. So available to everyone. You can export them from a database and manipulate them pretty easily. But what they do is they come into our lodgement portal. They get read automatically because we have set these standards so they can be read by our system. And it means that at the very front door, the data's not right, it doesn't come in. So it gives people live, this is the first time it's happened, actual live feedback on any errors or inconsistencies in the data as it enters through the doorway. It means that we're not changing things down the track, it's just right the first time. Now you'll see on the slide here, this box here is essentially a web form version of the templates that we've got. So because we know that a lot of people aren't really wanting to export from databases, they want a nice human interface, we've taken exactly the same inputs, exactly the same validations, all of those things, built them into a nice, friendly web form with big don't panic lettering everywhere. We control our lists, so you can't call it something that it's not. If you do, then it will say, no, try again. It's just a mapping exercise. It's relatively straightforward. Also, like I said, gives some live feedback. So if you try and say that it's a negative grade of copper in your ore, it's going to say that's not a thing that's possible. So you should be looking out for that on your own data, hopefully. But if you don't and you try and put it in, the system's going to tell you that it's wrong before it gets to 6 months down the track, and we have to give people a call to say that's not correct. They're all based on vocabularies of terms, every input. So those are widely available. They're online, directly to them. But it means that when I say sediment, you say sediment, we mean the same thing. And when anyone else says sediment, it has exactly the same definition. Pretty simple stuff, should be obvious, commonly really isn't. Now, this brings me to everybody's least favorite topic, which is data standards. Now you can see this table on the right, it's just one I've pulled offline, right? It's nothing new, nothing spectacular, but there's a trick here. We all look at this as humans and go, we know there's some missing data in here. We might know how to infer that data or where to look it up because it's missing. Not a problem. We know that if your age is 200, then something's either gone horribly wrong or horribly right for you. So we just know to ignore that. And then we've got inconsistent data, so things that clearly don't fit the patterns. We know that SR is a senior as a human, not a sophomore. We know that JR is junior. The computer doesn't. So in the time that I've just spent explaining something pretty simple and probably pretty obvious to everyone in the room, the computer could have gone through probably 100,000 lines of data, but the trick is the systems do what they're told. The coding is correct because you tell the coding what to do. But as soon as it hits one of these errors, it goes, what? I don't know what to do with this. So the whole system breaks down really quickly. And why I bring this up is the volumes of data that we're all starting to deal with are immense. So trawling through historic data is not a viable option unless you're going to hire 1,000 grads, which I strongly advise you not to do, given some of my previous petroleum industry experience. Not a good idea. But it does mean that we have to lift our data standards and try to align them. So if your data is inconsistent year on year, or your data is not consistent with what everyone else is doing, and it only makes sense to you, it's not consistent data. So I hate to break it to you, but it's only ever going to be usable for you, and that's vice versa. Everyone's in their own silo. Everyone's in their own silo. You give up ground, your data goes open file, nobody else can use it, but you can't use anybody else's as well. So unfortunately, we're in a state where the discoveries are harder and some cooperation really, really is required. And as a regulator, we're going to do what we can to enable that. So standards, 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 and more standards. Now, this brings me to everyone's even less favorite topic, if it's even possible, actually, the terrible state of some of our standards. Now, one of our data scientists ran a project recently looking at a fairly basic, what should be a fairly basic data set of copper analyses across the state. There were 7,000, and I repeat, 1,000 variations on potential ways that copper was recorded in input fields. And this is just a few that I imagined up because my imagination ran out pretty fast and my attention span even faster. So some of them were typos, some of them were pretty legitimate, but you tried telling the computer 7,000 variations, times that by every major trace, all your isotopes, you know, all that. You're not going anywhere, and you're not going anywhere really fast, and that's us as an industry. So again, sorry, but we're going to have to align some things here. Now, this is a slide that has been contentious in the past. We're going to try and say why it really shouldn't be. Whenever you talk about bringing in reporting standards, setting up standards for the report, people have a bit of a gut reaction because they're pretty used to the way that they see things. People are used to human readable formats. They like seeing things in a particular way. Geoscience is quite traditional and conservative in the way that it deals with data. Let's be honest, but there's a real issue here that I think we all need to get past collectively, and that's that the formats don't need to be the same, and in most cases they shouldn't be. So the transfer formats are what we send information between organizations, when you're changing it between teams. These are the things that should be relatively flat, they should be machine readable. They need to be optimized for the systems to do what they do. So capture the data, send it across, every system knows exactly what's coming in, exactly what to expect and what to do with it. Now your database schemas can be whatever you want. They are organizationally focused. So the data schema and the database that we house our data in with GSQ, we have some really strong opinions on because we deal with petroleum, we deal with coal, we deal with minerals, we deal with extractors. We have to exchange this information to completely different departments and government who have no clue and no care really about what geoscience is other than it gets some money for the state. So our database structure is not going to look like yours. Yours will be optimized for geoscience and in the room, minerals data. Doesn't get away from the fact that the transfer format should be interchangeable between all these systems. Doesn't dictate what you should do in your own house. The next thing is the presentation. This is how humans want to see this. This is where we've tripped up a lot in the past because we've tried to make transfer formats look like a presentation format. And this is where there's great visualizations that are tried and tested that you may want to stick to tradition, And it's also where you've got some scope to be creative and think outside the box, especially as we move into data visualization based on data visualization principles rather than geoscience principles, strangely enough. But it really is important to delineate these things. And I know it sounds obvious, and I know I'm harping on about it, but please come with us on this journey to actually push data where it needs to be in the format it needs to be at its stage in its life cycle. Really does, really does make things a whole lot easier. Now, we do actually want to do something with this data we get. We're not just here to talk about data only for data's sake, as much as I would, because like I said, I'm not a minerals person. Now, we've got some current data science projects, mostly as proof of concept, to show what we can do. So Kate up the back of the room here is talking tomorrow about one of her projects, but she's worked on essentially an OCR project for reports. Now that's optical character recognition for anyone who doesn't know. This is where you have some good tools, which I'm not going to talk about really in depth, that will scan over your old reports as images, pull out the text from them, and make them into essentially a Word document file. What we've done with that, or what Kate has done with that, is actually create a Word index for all of those reports. So you can search for hydrothermal gold, or you can search for copper deposit, or you can search for local pub. And if it's in the reports, it'll bring you back the list of those reports that those terms and phrases appear in. There will be a link to this at the end of the presentation. The next one is a geochemical result mapping, which essentially has taken all the surface sampling and the subsurface drill hole sampling, put it into a single layer for display, fill in a whole bunch of the gaps of where we're actually missing drill hole samples in our own database, which has been quite illuminating and terrifying. But essentially, that's gone through a fairly rigorous process to come up with a result, and I beg you, please do not ask me about it. Didn't do the work, don't know it. But I'm sure it's valuable to everyone out there. So the next project is what we're calling the LPX Plus, which is expanding that validation that you saw before. Essentially, what it's going to do is take the same treatment to the minerals and coal miners and put it on the petroleum guys. And again, seems a bit esoteric to everyone in this room, but because petroleum is both spatially and stratigraphically bound, it builds out this foundational piece of work to get to the geochemical analysis, which really is the complex kind of golden point we really need to get to. Incremental change is good. If we try and solve all the world's data problems at once, we inevitably fail. We have probably all seen it happen time and time again. If you try to eat the elephant in one bite, it doesn't work. So we are very deliberately taking very careful steps on this pathway to make sure we actually get this right at each step. So a little bit esoteric at the moment for this crowd. It is getting there, I promise you. That is our ultimate goal. But the other part of that is we've seen people use petroleum drilling globally as proxies for scout and exploration drilling anyway. So this is about getting cross-commodity integration. It's about making sure that what you call something is the same as what the petroleum people call it, or at least you know what that language is between the two groups. The data doesn't care that it's geochemical data. The data doesn't care that it's petroleum data. To be honest, everyone thinks their data is special, and it never is. So, sorry, it's controversial, I know, but the data is the data, and it really doesn't care who's using it or why. The data principles are the same whether you're doing mineral exploration, health, spatial, whatever. So eventually we want to get to the assay reporting standard. We want to uplift that. We want to make sure that that's in really good shape. Do the same process basically. So we want to consult with the people getting the results, make sure that everyone's happy with formats that work, formats that could transfer and be effective, and make sure the terminology is the same so we don't get 7,000 ways to represent the same thing, please. And eventually we'll get to the modernisation of all of the annual report activities. The whole point being, we don't want you cleaning data, we want you doing geoscience. And that really is the goal here, right? Want to make life easier as much as we are the regulator, and sometimes that seems like it's a long-term goal. A bit strange. Now, the GSQ Open Data Portal, like I said, my colleagues have done a great job pointing to all through the session. What we're doing with this is we're building what we call a content management system in real language that you care about. That means that we're going to be able to provide news and articles to you of our latest data releases. So the things you've heard about today will appear on the site. We'll be able to manage features a little better and essentially communicate. It'll be a channel of communication that you'll get the latest and greatest on the day. So news and releases, events and other happenings, any outages that we're getting, any system upgrades, anything you need to know about. Helen standings, I'll hurry along. Look, the whole point of this is we want to get tabulated data in. We want to be able to validate it before it goes into our secure storage. We want to have a clear filter so everyone's confidentiality is protected up until the point that it's not, and then things are live. So the open file data that is available is actually available. It's not just sitting there waiting for you to send a request, it's online. We translate it into things that make sense and actually mean something. And then we give you the compilation. So the whole state's data in tabular format in exactly the same format that you put it in, or it's available through a web search, or you call it via an API straight into your system if you know how APIs work. That's really the goal. You give it to us and you get it to us in the same way, because that's really what drives this data actually being able to be used. So lots of questions. That was me rabbiting on quite a lot. That's not mineral systems. I'm sure you've all tuned out by now and you're waiting for the networking event. So feedback's always welcome. Send us an email, ask me questions now, as long as it's not a minerals one. And there's some links here for some exciting YouTube talks on data science in minerals and our OCR word index.
Vance, you are awesome. Thank you for making everybody sit up and listen about data, because it's important. And we actually have questions piled up for you online. Actually, only one, but
Someone come up with a
Rebecca Farrington says, I love a good talk about data. So she's your friend. She's given you her email address. She's saying, can I ask about standards? What vocabularies are you using, requiring or prescribing? Are they international?
Good question. So for our people online here, if you go to vocabs.gsq.digital, it lists all the vocabularies that we use throughout our systems, both internal and external. We have a general guiding principle where if there is an international standard, we will use it. If there is not, we will use a national standard. If there's not one of those, there's usually some regulation we copy. And once all those options are exhausted, we get creative and we do our own thing because we're great. Now, I do say this, that we're actually actively looking at the moment to pass some of the custodianship of our vocabularies to national bodies like Geoscience Australia. We don't think the GSQ should be the arbiter of lithotypes in the world or minerals. It's not a thing that should ideally eventually go up to people like the IMA, the Minerals Association. So we've created them from a needs base. We want to hand them over. And all of these vocabularies are what they call persistent. So you can always look them up. It's always the same thing. But what it doesn't mean is that they're static. If you get in touch with us, you read something in our vocabularies and you go, that's not right, there needs to be an addition, I don't agree with the hierarchy, you can make the argument to us. And if it's a good argument, we can change that. So this is a collaborative opportunity here to align what we do, what industry does, and what academia does. And it's kind of a golden starting point because it really underpins everything we do.
Awesome. Ultimately, we all deal with data, so it is important.
So when dealing with data in WA, there's 1,000,001 different coding systems. Are you going to, have you got capacity just to store lithologies as words instead of codes? Like we invented words to deal with rocks, and then we went to codes because databases weren't big enough, and they're big enough now.
Yeah, so our preference is to actually store the rock types as their resolvable web address. So there'll be linkdata.gov.au/granite, and that actually resolves to not only a word, but the definition of what we consider a granite, which is generally the IUGS standard. So it goes beyond just storing the word. It goes to an actual entity with definition and context and metadata about it. So we're meeting minimum metadata standards.
And I think we also are able to, you're able to include a library. So if you use particular company codes for a lithology, all you've got to do is give us the definition of those codes, and we can translate it then to our, is that right? Or am I making stuff up? Yeah.
Yeah. Short answer is yes. Long answer is buy me a beer.
Danny will do that later. Any more questions? Have we got any more online? No. Okay. Now, we were going to subject everybody to a feedback session now, but Vance talked so long that, you know, we're just going to go and have beers instead. I want to say thank you to Vance for bringing up the rear. You did a good job. And now, thank you all for sticking with us for the entire day. I know I'm exhausted. We've heard some good talks, and we will now convene over, thanks to South 32. Danny, you're everybody's friend this evening. We're going to head to the quarter deck at the Ville. We'll meet there from 6 o'clock, but feel free to head over earlier. It is a little bit too far to walk, I think, is it? Or, you know, I don't know, I'm not really, it is, Johan's not, it's a bit too far to walk. So we can organise some maxi taxis and that kind of thing for those who are sticking around, or if you have cars, try and take people and then drive responsibly when you go home, of course. All right, everybody, thank you so much for making this a great day, and we'll see you for drinks, and then we will see you back here again tomorrow morning. Thank you.